keanekaragaman hayati. Menerbitkan tanda pengenal unik publikasi ilmiah terbitan berkala, membuat repositori ilmiah skala nasional, dan memiliki kewenangan sebagai pembina Jabatan Fungsional Peneliti Nasional, serta melaksanakan proses pengukuhan profesor riset di Indonesia. Kini, LIPI juga mendukung percepatan penanganan COVID-19, baik melalui riset berupa kajian maupun produk, maupun pengembangan SDM melalui program Indonesia Memanggil. Untuk mendukung riset, LIPI memiliki 5 kebun raya sebagai pusat konservasi flora ex situ. 2 museum yang memiliki koleksi flora, fauna, dan kesejarahan alam Indonesia, Indonesia Culture Collection yang menyimpan koleksi mikroorganisme terbesar di Indonesia, infrastruktur riset strategis, dan beberapa pusat berskala internasional, yaitu Asia Pacific Center for Eco-Hydrology atau APCE. LIPI telah menghasilkan hasil riset yang berkualitas dan bermanfaat bagi masyarakat, meliputi keanekaragaman hayati, lingkungan dan maritim, ketahanan pangan, pertanian, dan peternakan, kesehatan dan farmasi, material maju, energi, teknologi, informasi dan komunikasi, pertahanan dan keamanan, dinamika sosial, kemanusiaan dan kebudayaan, kebencanaan, inovasi teknologi dan pendayagunaan iptek, pelayanan, pengujian dan pembinaan ilmiah, serta peningkatan kualitas SDM iptek. Kerjasama keilmuan LIPI dalam negeri meliputi kerjasama penelitian, lisensi teknologi, pengembangan, aplikasi dan komersialisasi hasil penelitian, kerjasama non-penelitian, dan konsultasi kepakaran LIPI. Sedangkan kerjasama luar negeri, LIPI melakukan joint research, workshop, pertukaran peneliti dan beasiswa mancanegara, selain aktif menjadi anggota dan focal point di berbagai organisasi internasional. Melalui kolaborasi bersinergi, menghasilkan riset yang berkualitas, LIPI terus memberikan manfaat nyata, kontribusi berarti, dan turut mewujudkan cita dan asa membangun negeri kita tercinta, Indonesia. Berawal dari cita dan asa untuk membangun negeri, memberikan segenap rasa dan tenaga untuk menghasilkan pemikiran terbaik bagi negeri tercinta, kami ada untuk Indonesia. Mewujudkan diri sebagai Lembaga Ilmu Pengetahuan Indonesia yang andal, profesional, inovatif, dan berintegritas dalam pelayanan untuk mewujudkan visi Presiden dan Wakil Presiden. Indonesia Maju yang berdaulat, mandiri, dan berkepribadian, berlandaskan gotong royong. LIPI memiliki berbagai pusat penelitian tersebar di seluruh Indonesia yang berada di bawah kepala LIPI, Deputi Ilmu Pengetahuan Hayati, Deputi Ilmu Pengetahuan Kebumian, Deputi Ilmu Pengetahuan Teknik, Deputi Ilmu Pengetahuan Sosial dan Kemanusiaan, Deputi Jasa Ilmiah dan SDM Pendukung Iptek di bawah Sekretariat. LIPI berperan dalam proses penyusunan dan kelahiran berbagai regulasi dan kebijakan pemerintah terkait aspek ekonomi, politik, sosial, dan budaya. Selain itu, LIPI juga mengelola data dan timbangan ilmiah dalam rangka konservasi keanekaragaman hayati. Menerbitkan tanda pengenal unik publikasi ilmiah terbitan berkala, membuat repositori ilmiah skala nasional, dan memiliki kewenangan sebagai pembina Jabatan Fungsional Peneliti Nasional, serta melaksanakan proses pengukuhan profesor riset di Indonesia. Kini, LIPI juga mendukung percepatan penanganan COVID-19, baik melalui riset berupa kajian maupun produk, maupun pengembangan SDM melalui program Indonesia Memanggil. Untuk mendukung riset, LIPI memiliki 5 kebun raya sebagai pusat konservasi flora ex situ. 2 museum yang memiliki koleksi flora, fauna, dan kesejarahan alam Indonesia, Indonesia Culture Collection yang menyimpan koleksi mikroorganisme terbesar di Indonesia. Infrastruktur riset strategis. Dan beberapa pusat berskala internasional, yaitu Asia Pacific Center for Eco-Hydrology atau APCE. LIPI telah menghasilkan hasil riset yang berkualitas dan bermanfaat bagi masyarakat, meliputi keanekaragaman hayati, lingkungan dan maritim, ketahanan pangan, pertanian, dan peternakan, kesehatan dan farmasi, material maju, energi, teknologi, informasi dan komunikasi, pertahanan dan keamanan, dinamika penelitian, kerjasama non-penelitian, dan konsultasi kepakaran LIPI. Sedangkan kerjasama luar negeri, LIPI melakukan joint research, workshop, pertukaran peneliti, dan beasiswa mancanegara, selain aktif menjadi anggota dan focal point di berbagai organisasi internasional. Melalui kolaborasi bersinergi, menghasilkan riset yang berkualitas, LIPI terus memberikan manfaat nyata, kontribusi berarti, dan turut mewujudkan cita dan asa membangun negeri kita tercinta, Indonesia.
Bismillahirrahmanirrahim. Okay. Assalamualaikum warahmatullahi wabarakatuh. Good morning to all participants. Welcome to the International Seminar on Metallurgy and Materials 2020, held by LIPI. And for today's session, I would like to remind to all the participants to fill in the attendance list for plenary session day 1. And for today, we have a photo session that later on will be taken by the committee. So I would like to remind to all of the participants to activate all your cameras. And before we begin the conference for today, I would like to remind you all of you again to read carefully the presenter guidelines that are provided by the committee. Excuse me, that already provided by the committee. So you can read all the guidelines thoroughly and make sure that you fill in again the attendance list and before you presenting your topic for the seminar. Okay, so I think we can begin our first session of today by opening with the national anthem of Republic of Indonesia. Thank you. Okay, and next on the list of our today's schedule is the opening speech from the head of the International Seminar on Metallurgy and Materials, Dr. Nono Darsono. Please, Dr. Nono Darsono, to start the speech.
Okay, thank you. Can you hear my voice?
Yes.
Okay. Yeah. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Welcome, ladies and gentlemen, the honorable keynote speakers, respected guests, Deputy of Engineering Science, Dr. Agus Haryono, Director of Research Center for Metallurgy and Materials, Research Center for Physics, and Head of Research Unit for Mineralogy Technology, Indonesian Institute of Science, and all of our other guests. My name is Dr. Nono Darsono. It's a pleasure to welcome you all to the 4th International Seminar on Metallurgy and Materials 2020. We are grateful to the organizing committee, the members of the organizing committee who have arranged such a beautiful program. I heartily welcome all the keynote speakers, Professor Dr. Hirofumi Tanaka from Kyushu Institute of Technology, Professor Takeshi Kawai, welcome, Professor Byung-Il Hwang from Chong'an University, Dr. Fatwa Firdaus Abdi, Deputy Director of Institute Solar Fuel, Helmholtz-Zentrum, Berlin, Germany, Professor Dr. Insinyur Ane Zulfia Syahrial, Magister of Science from Department of Metallurgy and Material Engineering, University of Indonesia. Welcome. Professor Dr. Ing Andika Widya Pramono from Research Center for Metallurgy and Materials, Indonesian Institute of Science. Welcome. And Dr. Insinyur Bambang Prihandoko, Magister of Engineering from Research Center for Physics, Indonesian Institute of Science. Welcome. We are also fortunate enough to get supported by Indonesian Institute of Science and also from our quad management, and thank our media partners. In this opportunity, I would like to report the fourth International Seminar on Metallurgy and Materials, which will be held on November 2 days from 19th to 2020 is the fourth Scientific International Seminar organized by the Research Center for Metallurgy and Material, Research Center for Physics, and Research Unit for Mineralogy Technology. We report that total full paper submission around 70 paper, 63 paper accepted, 6 paper is rejected, and 1 paper withdrawn. The accepted paper will be considered for publication in IOP conference series indexed by Scopus. It will be researcher around 53 participants, students 7 participants, and academia from the 3 participants. We will also have participants from other country, from Philippines and other from other country. We have arranged a plenary session for lecture from keynote speaker and oral presentation opportunity for accepted paper to put forward their reforming to in the fast field. I want to inform our speaker, moderators, and participants to be very strict about the schedule and don't let overrun any session. This event will be widely broadcast from Indonesian Science Expo 2020 website. I hope you all find the seminar highly engaging, fruitful, and beneficial for your future venture. Thank you. Thank you all. Waalaikumsalam warahmatullahi wabarakatuh.
Waalaikumsalam.
Thank you to Dr. Nono Darsono for that opening speech. And next on the list is also the speech that will be delivered by the chairman of Indonesian Institute of Sciences, Dr. Laksana Trihandoko, Master of Science. Okay, so please, Dr. Laksana Trihandoko, to begin the speech.
Hello, I am Handoko, the chairman of the Indonesian Institute of Sciences, LIPI. It is a great honor for all of us at LIPI to host and to organize this international conference. On behalf of LIPI, I would like to welcome you all at this international conference. We hope this international conference would open an opportunity for all of you not only to know each other, but also to open future collaborations. I would like to thank to the distinguished invited speakers and all participants for your contribution. Have a nice, fruitful, and productive discussion during this international conference. Stay healthy. Thank you very much.
Okay, thank you, Dr. Laksana Trihandoko. And next one is another speech that will be delivered by Deputy for Engineering Sciences of Indonesian Institute of Sciences, Dr. Agus Haryono, Master of Science. Time is yours, Dr. Agus Haryono.
Welcome, ladies and gentlemen. Thank you to each and every one of you for being here virtually today at this important fourth International Seminar on Metallurgy and Materials 2020. My name is Agus Haryono, Deputy Chairman for Engineering Sciences, Indonesian Institute of Sciences LIPI. It is a such great honor for me to speak on behalf of LIPI. Let me begin by giving you a warm welcome to this virtual conference. Before we get started, I would like to express my appreciation to the Honorable Chief Guests, respected directors, speakers, and all our other guests. We could not have done this conference without your participation. I am also grateful to all organizing committee members and all the volunteers to have arranged this program. I will kind-heartedly welcome all the participants from academia, students, industrial practitioners, and researchers. We are also fortunate enough to get supported by our partners whom also organized this scientific conference. This conference is a part of Indonesian Science Expo 2020 and aims to bring together researchers, academia, and industries to share information and their research results. I do hope this event will also reach its objective of this conference on accelerate research and innovation on metallurgy and advanced material for inclusive and sustainable industry. As you all are aware of the current situation of COVID-19 pandemic, this event should be conducted virtually. The speakers in this program are uniquely placed based on their topics in advanced material and functional material in the field of energy and metallurgy. I hope you will have the most productive 2 days of interesting and stimulating discussion. I hope this conference will success not only as a chance to share knowledge and experiences, but also discover new opportunities to the still growing area of research on the future metallurgy and material technologies, as well as its collaborative inter-institutional research opportunities. I wish you all the fruitful and productive discussion. Last but not least, I would like to sincere thanks to all of you for being able to join this virtual conference. During the pandemic COVID-19, please stay healthy and happy during the long pandemic. Again, thank you very much and enjoy the conference.
And thank you, Dr. Agus, for that opening speech. Ladies and gentlemen, all participants of the International Seminar on Metallurgy and Materials 2020, again, I would like to remind you to fill in the attendance list provided by the committee for the plenary session day 1. This day 1, we have 3 plenary sessions that already provided in the presenter guidelines that you have probably already read. And before beginning all the sessions, make sure you fill in the attendance list. And another reminder for all participants to activate all your cameras for the next photo session that will be taken around plenary session keynote 3. So make sure you activate all your cameras. And for the schedule on our seminar for today, as written on the guidelines, will be started with plenary session keynote 1, Professor Takeshi Kawai. So, and please prepare for the presenters and all participants. And thank you. I think for today's opening, we will start shortly on the plenary session. Ladies and gentlemen, all participants, enjoy your seminar. Thank you.
Okay, thank you very much, MC. So for this morning session, for the day one of our conference, I will be the moderator for our plenary session. So this morning we will have four great speakers. The speaker number one is Professor Takeshi Kawai, and then Professor Andika. The third one is Dr. Bambang Prihandoko, and the last but not least is Dr. Fatwa Firdaus. Okay. Okay, before the speaker begin, I would like to say hello again to all of you. Honorable Deputy of Engineering Science of LIPI, Dr. Agus Haryono, the Director of RCCM LIPI, Professor Nurul Taufiq Rahman, all the guests of ISMM or the representative, the distinguished keynote speakers, and all respected participants, I would like to say welcome to our ISMM 2020 or the fourth ISMM. Okay, before we go to our first keynote speaker, Professor Takeshi Kawai, I would like to read his his biodata. Okay, Professor Takeshi Kawai, his affiliation now is from School of Electrical and Computer Engineering, College of Science and Engineering, Kanazawa University. And Professor Kawai got his doctoral from 2003 from Tohoku University. His professional career starting as the postdoctoral researcher since 2003, and he already joined several postdoctoral researcher from Tohoku, and then joined again to NIMS, National Institute of Material Science, and then continue as the research associate at College of Science and Engineering at Kanazawa University, and then become lecturer since 2009, and now as the associate professor at Kanazawa University. Okay, without further ado, I would like to invite Professor Kawai. Professor Kawai, please, you can share your PPT now.
Thank you, Professor Denis. Now, I will share my presentation slide.
Okay, maybe I'm sorry. I would like to say the time is about 40 minutes. Okay.
Yeah. Okay, thank you. I understand.
The slide is already in the full mode. Hello, Professor Kawai. Is it okay?
Hi. But now, can I start my presentation now?
Yes, you can share your presentation now. You can start now.
Already? Yeah, I'm
Yeah.
sorry. I forget my presentation time. Yeah, I'm sorry, dear.
Maybe the time is earlier than our schedule.
Yeah. Okay.
Yes.
Thank you, Professor Denis, for my introduction. And also, before my presentation, I would like to greatly thanks for all of the professor of this conference to invite me to that hot international conference. Very thank you. ありがとうございます。And this is today's my presentation title. Yeah, and this is the outline of my presentation. Firstly, I would like to explain the background, introduction, and the background of my research. This research, and I have the two topics. One of them is the fabrication of the ferroelectric gate diamond field effect transistor, and also the possibility of its pseudo-anomaly of operation. Yeah, let's start. Yeah, as you know, the diamond is the king of jewel. Yeah, and also the maybe the you know the diamond is the candidate next generation power semiconductor material due to its high electric breakdown field and high thermal conductivity and high carrier mobility. This table is comparison with those typical property of diamond with those of the other semiconductor material. As you can see, the diamond has a high thermal conductivity value and carrier mobility and breakdown field. So these excellent property is by considering those excellent electrical property, diamond is a promising candidate for next generation of power device application post silicon carbide or gallium nitride. And also about the diamond semiconductor, there are two kinds of the channel structure. One of them is the hydrogen terminated conductive surface conductive layer. So this surface conductive layer has a high hole density p-type semiconductor material, semiconductor working, and its low density of surface state. So it means it is very easy to create the good, smooth, the pure semiconductive layer. But however, there's the serious problem. It is really sensitive for high temperature or plasma process. So it means it is really weak for active species. So about this problem, Professor Liu, Dr. Liu of NIMS, they tried to create deposit to create the gate structure by depositing the hafnium dioxide using sputtering method. But they oxide only hydrogen terminated diamond semiconductor layer. So it means we must suppress the process damage for creating the device semiconductor device structure on hydrogen terminated diamond. And also, this is one of the ultimate demonstration by Dr. Yamaguchi from NIMS. They tried to transfer the hexagonal boron nitride, two-dimensional hexagonal to boron nitride as a gate insulator on the hydrogen terminated diamond. And also they succeed to create the those field effect transistor structure. And also they investigate its carrier mobility. And as you can see, in case of their ultimate structure, they can obtain the highest carrier mobility compared with that of the other created hydrogen terminated field effect transistor. So it means that by improving the device process, especially the gate insulator fabrication of the gate insulator process, hydrogen terminate diamond can be probably winner for high frequency or high power field effect transistor application, we believe. So nextly, I would like to explain what is the ferroelectric gate insulator, gate insulator field effect transistor. About the another semiconductor diamond channel, it is the bulk channel, bulk diamond channel. But in that channel, there is serious problem. So it's deep, really deep dopant level. For example, the phosphorus 0.6 electron volt or the 0.37 electron volt. This is really difficult to activate the carriers at room temperature. Yeah. So in order to solve this serious problem, we consider the ferroelectric gate structure might be suitable. Yeah. Because this is the one of the demonstration of the ferroelectric gate structure by Professor Tokumitsu of the JAIS. They create the ferroelectric gate structure on the some oxide, conductive oxide channel, and also they try to activate the huge amount of carriers for conductive oxide semiconductor. And they conclude it is possible to modulate the huge amount of the carriers by using the ferroelectric gate insulator. So we consider by using this gate structure, maybe it is possible to activate the huge carriers for the bulk diamond channel at room temperature, we consider. So to investigate this possibility, as a first step, we use the ferroelectric, organic ferroelectric material, VDF TRFE, as a gate insulator. So this is this material is organic ferroelectrics. So, and also to deposit this one, we don't need the high temperature. Around the 100 degrees C is enough. And also this is most important parameter fact. This VDF TRFE material has a large band gap than that of the diamond. So it means that we can use this ferroelectric material as a gate insulator for diamond. And also by using the ferroelectricity, we would like to we hope the high current on-off ratio for diamond channel, and also maybe we can operate the pseudo normally off operation for diamond field effect transistor. So this is our past demonstration. As a first step, we create those simple field effect transistor structure on diamond by using the VDF TRFE gate insulator. And this is the basic electrical property, drain current versus drain voltage property. As you can see there, we succeed to create the field effect transistor with ferroelectric gate insulator on the diamond semiconductor, like distance versus gate voltage property. This typical property indicates in our prepared gate ferroelectric gate structure, there is no interfacial layer. So it means that we succeed to obtain the ideal metal ferroelectric semiconductor structure. Yeah. And also, this is serious problem. Although we can modulate its drawing current by using the remnant polarization like this. However, its deflected current level is still 10 to minus 2 power milliampere per millimeter. We consider this is not really deflected states. And also this is drawing current versus DC gate voltage property. As you can see here is really deflected current level, but there without gate biasing we can not deflect, still deflected its current level. So it means not normally of operation state. Yeah. So in this time, in order to solve this problem, we would like to we have tried to improve this property for our structure. Firstly, we must consider why we cannot obtain the normally of pseudo normally of operation for our device structure. Its answer is really simple. Carrier density of surface conductive layer is still higher than that of the gate remnant polarization value. Yeah, so it means that we cannot modulate the all of carriers of surface conductive layer by using the remnant polarization. Yeah, so it means that should we should we search the other ferroelectrics with huge remnant polarization value or not? The answer is no, because it is very difficult to find out the other ferroelectrics with large bandgap. This is most important parameter. Yeah. So with considering this current situation, we think that it is really difficult. Maybe it might be impossible to solve this problem. But there are the another approach for normally of operation of the surface conductive diamond layer. Professor Kawarada, the Waseda University, they recently they support the other process approach. It is the partially oxygen terminate structure by using the some nitrogen ion implantation technique, and also by using this process technology, they obtain such normally of operation like this. this is the IDS versus gate voltage property. As you can see, they can operate the normally of action by using the ion partially ion implanted device structure. So we consider by using this process technology, maybe we can create the smooth normally of operation for our ferroelectric gate diamond FET. So in our study, we use the UV ultraviolet lamp irradiation for hydrogen terminal diamond structure. So by irradiating the ultraviolet lamp, we can create the active ozone species, and we can send those species on the hydrogen terminal diamond structure, and also the we can obtain the partially oxygen terminate structure. So by using the this process technology, firstly we check the can we control its carrier density with locally controlling. This is experimental procedure. This is a rough image of our device structure. Firstly, we create the surface hydrogen terminate surface conductive diamond channel like this, and also the for this prepared channel structure, we try to create the thin, narrow, partially oxidation area by using the ultraviolet irradiation. This is the basic experimental result. This data is ultraviolet irradiation time versus current density of the hydrogen terminate structure. As you can see there, by increasing the ultraviolet irradiation time, we can control its current density from 10 to 10 milliampere per millimeter to 10 to minus 8 power milliampere per millimeter order. Yeah, and we conclude its current density can be controlled by changing the ultraviolet irradiation. And also this is the Kelvin Horse microscope image of our prepared channel structure. As you can see here, we can control its carrier density on the implant area. Here is a hydrogen terminate. Here is a completely oxygen terminate. And also this brown area is partially oxygen terminate area. So, and by using this such specialized channel structure, we create the ferroelectric gate FET structure. This is the basic electrical property, drain current versus drain voltage property. As you can see here, we can this prepared device can work without a serious degradation, such as the degradation of the current density value. And also this is the IDS versus gate voltage property. As you can see here, with ultraviolet irradiation, we can shift its aesthetic property like this. And also could you see around here? So it might be possible to operate the normally off operation for our devices. And also this is the drain current versus gate voltage property for various ultraviolet irradiate device structure. As you can see there, with increasing the ultraviolet irradiation time, its curve, those curves are shifted to negative bias region. And could you see there, this accumulate region by irradiating the ultraviolet irradiation. Due to the ultraviolet irradiation, there is no serious degradation of the accumulated current density, as you can see here. And also now we roughly decide this lower current level is roughly deflected state for each device structure. And also we roughly decide here is a threshold voltage or a typical voltage. And also this 20 minutes, maybe we can obtain the pseudo normally of situation. So based on the past basic experiment, we create the optimized device structure. This is these data are the conventional result. Firstly, in this result, we can obtain the good device operation without this serious degradation. And also, this is a drain current versus a gate voltage curve. And as you can see there, by using the ultraviolet irradiation, we can obtain the clear on state and off state without the DC gate bias. We consider this is one of the results for the possibility of the pseudo normally of operation we consider. So, in order to investigate its detailed electrical property, to investigate its possibility of the pseudo normally of operation, we try to measure those typical measurements. I'd like to explain this measurement method. Firstly, we ground the source and the drain electrode were grounded, and also the gate voltage was applied to the gate structure, and to generate or write the remnant polarization value in the gate insulator. And also after that, we opened gate terminal and measure its current level of the created channel structure. This is the first result. This is the drain current for accumulated channel without DC bias and deflected channel without DC bias. So, as you can see here, we can obtain the higher current on-off ratio over the 10 to 7 power without DC gate biasing. And also we check its retention property. This x-axis is the retention time. As you can see here, by using our structure, we can keep the off state until the 12 hour by using the remnant polarization. And also this is the other specimen result. By improving its both gate and channel structure, until now we can keep its off state over the 60 hours. So maybe my conclusion is maybe this is the pseudo normally of operation for diamond field effect transistor we consider. But in your future we must investigate the other parameters. This is first success. So we must investigate the other parameters such as the breakdown property and the off state. Yeah. So finally, I will conclude my presentation. In this time, we have prepared the diamond ferroelectric gate field effect transistor with improved partially oxygen terminated channel structure and investigate its electrical property. One of our result, the current density of the hydrogen terminated surface conductive layer can be controlled by using the ultraviolet irradiation time. And also the diamond ferroelectric gate FET with partially oxygen terminated structure can indicate the clear device property without the serious degradation for device property. And also the off state, deflected state, due to the remnant polarization, it means that without direct DC gate biasing, can be held over the 60 hours now. Yeah, this is that's all. Finally, many thanks for your attention. Thank you. Yeah.
Thank you very much, Professor Kawai. You are very on time. Wow. Okay, it's very great sharing session. Professor Kawai already shared to us about the diamond field effect transistor with ferroelectric or FET, and many things that he already explored, many novelty that already shared with us. And I think that novelty will have the revolution for the electronic or the electrical material. Okay, to all participants, please, if you have any question, you can write down your question to the chat room. And then, for the Q&A, we will have after the second keynote speaker deliver his speech. But in the meantime, you can write down your question into the chat room. Okay. Thank you, Professor Kawai. Please wait a moment. After the second speaker, we will have the Q&A session. Okay. Okay. Thank you for your presentation. Okay. We will continue to our second presenter. Professor Andika. I would like to say hello to Prof. Andika. Okay. Hello, Prof. Andika. Can you hear me?
Yes, I can hear you. Thank you.
Okay. Prof. Andika, you can share your PPT now. Your slide now.
Okay. Wait a moment. Okay. So,
okay, before Professor Andika deliver his presentation, I would like to brief his bio, his curriculum vitae. Full name, Professor Dr. Ing Andika Widya Pramono, MSc. He is a full professor since last year, Prof, if I'm not wrong. And then, he's, wait a moment. He has involved in many workshops, both the national and the international workshop regarding the managerial workshop, including the managerial workshop as well. For the overseas workshop, he already joined with the LIPI GSPS research training program, and then bio and many other related with material research training on microtext analysis of S-Drown and in the 2018. And then for the managerial history, for the last, at the 2010 to 29, Professor Andika is the director of the Research Center for Metallurgy and Materials. And he also active in the organizational, like the Himpanindo, Indonesian Research Union, and then the Society of Biomaterial of Indonesia, and also the Material Research Society. And he also is the alumni of Ikatan Alumni, the Habibi program, or IAB. Okay, Professor Andika, you can deliver your presentation. So the time is yours. It's about 40 minutes. Please.
yes. Thank you very much, Dr. Denny Siti Harun. Okay, Assalamualaikum warahmatullahi wabarakatuh. Good you all.
Waalaikumsalam.
Yes. First of all, I hope my voice is clear enough for you, because I'm using two devices, smartphone, and I use my smartphone to come out with my voice. So okay, it is very very happy for me, to be able to talk presentation. I don't know, most of you already know about the definition or the meaning of the energy harvesting. So I think I just maybe just put some more emphasis on it, because could be some of you think that energy harvesting is like we are talking again about what's that, solar energy, and then the water energy, the ocean wave energy, but actually it's not like that. In case some of you think energy harvesting is something like that. So the energy harvesting is actually something different, and we will discuss about it today. And I will begin with the definition of the the knowledge of the superconductor. This is my outline, my presentation outline, the introduction, and then the wearable electronics, and then wireless sensor network, conclusion, and then the near future advance. Okay, I begin with the introduction. So, as we know that in Professor Mans discovered the great behavior, but when it is superconducting material, I'm sorry, it seems that my maybe it's because of okay, there's some trouble in connection in my laptop, in my presentation, not in my voice. Then at a certain point of temperature, suddenly drops. As you see, the green one, it suddenly drops. So there is a so-called the critical temperature to define or to make a borderline between the normal condition and the superconducting condition. And Mr. Heike Kamerling Owens tried that for the first time for the mercury. So his discovery was actually in the mercury. Okay, wait. So I hope, I don't know what happened, but okay, I continue. So this is the timeline of many attempts, hundreds attempts since the beginning of the 20th century regarding the research and development in superconducting material. Okay, so I don't know, is this a movie or my presentation? I don't know, but I try to have a control of my laptop, but it doesn't work. So I just continue. Okay. Yeah. Okay. As you see, this is the timeline of the superconductor, and you see that in the borderline of the liquid nitrogen, this is a very significant border that delineates the difference between the low temperature superconductors and high temperature superconductor. There's another definition of the low temperature superconductor and high temperature superconductor. There's what usually people think is by the temperature of the liquid nitrogen that evaporates into gas. So as you see that so far the low temperature superconductor still more than the high temperature superconductor. So as you see in the beginning, 1900, you see there is a mercury, there is a lead, okay, and then there's a niobium. And not until 1950s, when the researcher from the I think the University of Chicago discovered the magnetic horseshoe in the form in the shape of the superconductor that had applicative. Around 1950 or 1960, there was a discovery of niobium tin and then niobium germanium. Niobium tin is the very first or one of the first technical superconductors that can be implemented. The definition of the technical superconductor is that it can be or it could be implemented into wires and cable. Mercury led the first discovered superconductor, was not technical superconductor. And then as you see, all the research and development attempts around in the period of 1985 to 1990, in the late 1980s, the beginning of 1990, there's a cuprate superconductor. This cuprate superconductor can use the liquid nitrogen as the cooling medium or the cryogenic medium. As you see, the first one that reached for the cuprate is the barium copper oxide with the addition of yttrium. And the TC, this is as you see, this is about 75, 80 Kelvin, as you see in the diagram. And then, but not until 2005, in the period of 2005 and 2010, then the iron-based superconductor with the addition of arsenic and strontium reach the temperature of the evaporation of the liquid nitrogen, as you see in the period 2005 until 2010. After that, people start dealing with the high temperature superconductor. There is one interesting point about the magnesium diboride. As you see, from the year 2000 until 2005, there was a discovery of magnesium diboride by the Japanese professor. And this is actually a very good low temperature superconductor so far. And magnesium diboride is actually still in the investigation, but the tendency is to increase the performance to be applied for the high current, high voltage application for the power line and the other high voltage or high current electrical component. So okay, now in the high temperature superconductor, the latest attempt empirically, not theoretically, empirically, has been the discovery of the lanthanum decahydride, LaH10. And this lanthanum decahydride has the TC of the minus, only minus 23 centigrade. So it's it can be functional in the very normal cooling device. But theoretically, through the density functional theory, the higher TC is predicted to be happening soon enough, hopefully, in the yttrium decahydride, YH10. So so that's the timeline of the superconductor. I don't know, am I getting help in moving forward or backward in this PowerPoint presentation? Because I cannot. Okay. Okay. I try to mute it. Okay. Okay. So the room or near room temperature superconductor that is happening in the yttrium hydride, and then still in the experimental state, use it and fill. So this is a very micro size. The lanthanum decahydride is pressed at very high pressure by diamond anvil in the micro size, and then with the hydrogen and I'm getting help. Then next, okay. So this is the lanthanum decahydride crystal structure. Okay, mainly it's actually cubic. Initially, it was discovered having the cubic structure, but then the attempts of it has very upon pressure, as you see on the right side of the slide in front of you. So, if we can, presumably, when we can, through the scalable, then when you structure, so it is synthesized at 730 centigrade. Okay, next. Okay. Now, what you see in front of you is the PC prediction. As I said before, that the yttrium decahydride, not lanthanum decahydride, still theoretically predicted using the density functional theory. But the theoretical approach has been such that it can form this diagram, the values of PC as a function of various pressure. This is theoretically, not empirically, through the density functional theory. So it is very, very, as you see, very interesting, the TC of this yttrium decahydride. Very, very interesting, because as you see, let's say 300 Kelvin, you subtract it by 273, then we are dealing with the room temperature application of the yttrium decahydride. Okay, next. Okay. Okay, so lanthanum decahydride and yttrium decahydride, or lanthanum, or okay, lanthanum and yttrium come from the red earth element. Okay, this is the country that domination of the red earth element, and what I circle there with the yellow circle is the yttrium and lanthanum. Of course, since superconductivity in yttrium decahydride and lanthanum decahydride is not popular, so the application is still written as spark plugs, cancer treatment, camera lenses for the lanthanum, and the back. Okay, next. I'm sorry if I realized that I'm getting help in the presentation. I thought I'm doing myself. And if I mention about rare earth element in Indonesia, then the rare earth element very abundant in this, at least these two minerals, monazite and the xenotime. And these two minerals are abundantly available in the Bangka Belitung Island. Lanthanum comes from the monazite that has been by PT Tima, has been now available in the form of lanthanum hydroxide. Yttrium comes from xenotime and available in the form of phosphate. So actually, it is very, very interesting. If we can make use of this lanthanum hydroxide and yttrium phosphate. Okay, next. Okay, if we talk about the main application of superconductivity, then this is a very, very popular one. And I think some, or let's say most of you already know that this is not the application without price. It is very, very commercial application. For example, superconducting magnet. And then on the right side, you see this is MRI, magnetic resonance imaging. That's already available in many, many hospitals throughout the world. And then some application in the magnetic levitation train, maglev. And then there is also some prototyping and scaling up of the superconducting transformer. Okay, next. Yes, next, please. Now, how about in energy harvesting? So energy harvesting is actually, we make use the existing condition that is realized or unrealized producing energy. But usually energy harvesting is not as a resulting, it's not a big energy, but a very small or medium scale. Okay, next. The energy harvesting, by definition, refers to any attempt to acquire, derive. So you get it, you derive it, you develop it, and store it from external sources. Could be a solar power, wind energy, thermal energy, and etc. Etc. is many, actually many. Okay, into autonomous devices. Autonomous devices. Energy harvesting is also known as the power harvesting, energy scavenging, or ambient power. And with that, what I said, it provides a very small amount of power for low energy electronics. That's the definition of this energy harvesting. Next. So the objective of this, our discussion is what happened with the energy harvesting through the superconducting material for the wearable electronic devices and wireless sensor network. Next. Yes, please, next. Okay. This is the timeline of the Internet of Things. This is the Internet of Things that's already began in 1969 in its development. It's very, very potential to use the energy harvesting. Okay, next. Okay, now we talk about the wearable electronics. Next, please. Okay. One of very important attempts is the use of the gallium indium tin nanodroplets. This gallium indium tin material is a superconducting material. So what these people do, this is from the three-party in Australia and China. They developed this gallium indium tin nanodroplets by using this method, the sonification from the bulk liquid metal. Okay, and then they form this nano size or near nano size nanodroplet. And then this nanodroplet of gallium indium tin is or has been lithographed into flexible electrode or circuit. As you see in the photos in front of you, that it can be lithographed or it can be painted into this electronic circuit. So, and as you see, the application is in the small size, and it could be useful for the wearable electronic. Okay, next. Yeah, and then the second one is the application or the implementation or the combination of carbon black and graphene for this composite for the application for the flexible supercapacitor. Graphene, actually, if you combine two layers of graphene with making the degree of 1.1 degree, then it can act as the superconducting material. So this is the combination of graphene oxide and then carbon black, and then reduce, and then they make into the composite, and then apply that for the supercapacitor. Okay, next. Now this is the property of the supercapacitor, that using the carbon black and graphene at a very, very optimum, okay, based on this paper, this is very, very optimum condition can be or could be attained by this graphene and carbon black. Next. Okay, the third one is the waveable asymmetric carbon nanotube, which is doped or infused by manganese oxide particles and reduced graphene oxide. And this is application for the electrotextile, and for the application, the application or implementation is in the wearable electronics. Yes, next please. Okay, so this is the property of this electronic textile. Okay, next. Now I'll talk about the wireless sensor network. Next, please. So when I talk about the wireless sensor network, it is very good to begin with. The so-called disjuntivity can move very easily through the tunneling effect in the insulator part. Josephson effect is the supercurrent that flows indefinitely long without any voltage applied. That's the significance of it. And in the decade of 1990s, many attempts were conducted to fabricate high-performance Josephson junction based on never with the low temperature superconductor, but directly with the high temperature superconductor. Next, please. The development based on Josephson junction, the next one is the so-called SQUID, the superconducting quantum interference devices. As you see in the picture in front of you, this SQUID develop or generate the magnetic field. As you see, there is also a part of it. This is that has the Josephson junction, and this device may be configured as a magnetometer to detect incredibly small magnetic field, small enough to measure the magnetic field in the living organism. Okay, next. Okay. In 1990s, there was a SQUID receiver, which was developed based on the diagram in front of you. There is a SQUID magnetometer inside the liquid nitrogen. As you see, this is high temperature conductor. There's a probe, and then connected to all the system. Okay, next. Yes, next, please. So this is the application. As you see, the box on the left side with the dash line is the SQUID hut, and then it acts as a sensor, and then it connected to the control room, and then nowadays it connected also to the network for the remote sensing or remote detection. This is the SQUID geomagnetic signal analysis and modeling based on Schumann resonance in the Earth ionosphere cavity. This is the application in the geology. Okay, next. So the network for monitoring structural health. It is bridges, building, human, automobile, machine, even the aircraft. So this is using the wireless sensor based on the superconducting material. So this is what I call this Internet of Things, getting into impact in this situation. Next. Yes, please. So the maintenance-free energy for this sensor comes from the energy of vibration collected by levitation-based energy disperser system, the sensor. So when we talk about levitation, it can come from the superconducting materials, Meissner effect, DC electromagnets, eddy current, permanent magnet, and diamagnetic. What's very popular is using the superconducting material and the electromagnetic system. Okay, next. So this is the what as mentioned before, the wireless sensor based on the magnetic levitation. As you see, there is a magnet, there is a copper coil. Okay, this is the basic principle of it, and there's another magnet in the center of it. So there's a challenge when you use the copper coil. That is when you have to connect it with the MEMS, micro electromechanical system, and the electrical resistivity of the copper. Then the solution is the use of low resistance conducting wire or even superconducting wire. When we use the superconducting wire, then there's a double function of diamagnetic levitation as well as zero resistant electromagnetic transduction. Okay, next. Okay, the conclusion of it, please, next. So superconductors were empirically verified to be suitable for the application of energy harvesting in the form of wearable electronics and IoT-equipped wireless sensor network, or WSN. And then the superconducting material may provide alternative solution for the energy harvesting of WSN by acting as double diamagnetic levitation and zero resistant electromagnetic transduction. Next. The future attempt. So actually, yes, please, next. The future attempts is actually going back to this timeline. What will happen? What will happen? Now we should focus ourselves to the high temperature superconductor, especially the lanthanum decahydride that's already empirically discovered, and then continuing on this cobalt superconductors, and then empirically proven the deuterium decahydride that is already invented theoretically by density functional theory. I think that is from me. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Prof. Andika, for your delivering your presentation about the superconductor, about energy harvesting material based on superconductor. Okay, we already have two speakers deliver their material, and now is for the discussion Q&A session. Please, if there is any question, you can put in the chat, or if possible, you also can just directly, and maybe I ask to the co-host to unmute or in the video mode. Please, anyone, if you have any question to who? To Professor Andika or Professor Kawai, like that, please. Okay. Meanwhile, Professor Kawai, can you hear me?
Yes.
Okay.
Yeah.
Okay. Meanwhile, we waiting the question from the floor, from the participant. Okay, I have some little question for you.
Oh, really?
I'm curious, based on mention about low temperature, yeah, and then the film is deposit on the diamond Fe ferroelectric FET field effect transistor, and actually for the FET for the FET application, So what is the range of the thin film, and what is the proper thinness of the film itself?
Firstly, I will share my presentation file, and about film fabrication, we use the conventional spin coating method. This is really simple one, and
spin coating.
To create this ferro thickness is around under 100 nanometer. Because its band gap, VDF band gap of the VDF TRF thin film is really high. So it means it's really tough insulator. It can work as a tough insulator. So it means we don't need the huge film thickness for gate insulator working, I think.
Yeah. Unfortunately, in your slide, you didn't show the SEM figure.
Actually,
that's also interesting.
Because its film thickness is very thin. Maybe there's no meaning to check the SEM observation. However, to consider the device operating, we must check its surface roughness of gate insulator, and to check we measure the AFM measurement at the same time of the KFM measurement. As you can see, this is three-dimensional image, but I'm sorry, there's no thickness information, but its film roughness, surface roughness is under the 1 nanometer. So it means our deposited VDF TFE thin film is maybe the angstrom level roughness, I think. It means it is really smooth. And also to create such smooth organic thin film, we don't need the specialized technique for our spin coating. Because this VDF TRFE is really easy treatment material, I think. If you have any interesting, could you ask us, or maybe you can try to use this material for various device application, I think.
Oh, very interesting, Prof. If you say that the technique is not so difficult, not so advanced, I think it's scalable, right? For the industrial scalable, when you have the proper performance.
Thank you.
And you want to make scaling up. Congratulations, it's very, very good performance. Also, as I see from your PPT. Can I have another question, Prof? Hello, Prof. Kawai. Hello? Hello, Professor Kawai?
Hi.
Okay. I still have another question. I see from your list of your CV that you also developed the perovskite oxide material, right?
Yes.
Like strontium, ruthenium oxide, bismuth-based ferro oxide. Very interesting. For that's perovskite oxide material. What kind of the application for the perovskite oxide that you develop in your laboratory? Only for capacitor or any other maybe? PV, photovoltaic also?
Of course, we investigate the other perovskite materials, not only the ferroelectric material, but also the high-TC superconductor. And in near future, I would like to, I already explained these perovskite ferroelectric material can modulate the huge amount of the carrier compared with other conventional gate insulator. So, and also, but their serious problem is its band gap is still lower. So, in the future, we would like to find out some candidate perovskite ferroelectric material with both large band gap and huge remnant polarization value. And by finding out those material, we can we can combine with our ferroelectric gate field effect transistor system, I think. And also the other different direction. I have now one idea by combining with the ferroelectric gate insulator and high-TC superconductor channel structure. Yeah, and maybe Professor Andika really know the high-TC superconductor has a huge amount of the carrier level, and also it is impossible to modulate such huge number of the carrier such as the superconductor. But I think by using the ferroelectric material with huge polarization value, maybe we can we might be able to realize such superconducting ferroelectric gate insulator transistor to modulate the really huge amount of the carrier, and also maybe we can apply such devices for future application for the really high power application. We believe. Yeah. Okay.
Okay. Yeah. Professor Kawai, I think I will go back again to you. I need to go to Professor Andika first. Professor Andika, can you hear me?
Yes. Yes,
Yeah.
I can hear you.
Okay, we have the question from Dr. Hendrik. So why graphene is not shown in the timeline of your superconductor? The graphene might be a superconductor when stacking between layers. Is it right? Maybe you can.
Okay, thank you very much, Dr. Denny, and thank you very much for Mr. Hendrik for a very good question. My answer is that it should be there. Yeah, this graphene should be there in this timeline. The reason it was not there is maybe it's because the discovery of the graphene as a superconductor.
Yeah. Okay. Okay. Maybe the next question is from me. This is just the very basic. I think just want to confirm. So Prof. Andika, so what is the best TC of the superconductor material now in the commercial level? Previously, you mentioned about the room temperatures superconductor that you already developed, right?
Yeah, right.
Yeah, maybe
so,
you can, yeah, please.
Yes, okay. The high temperature superconductor that have a very high temperature, okay, not low temperature, the high temperature superconductor that have been intensively investigated is the copper. The R&D attempt have already reached how to increase not only the TC, but also the GC, the current density. But as you saw in my diagram of timeline of superconductor, empirically, the highest superconductor so far discovered in the lanthanum decahydride. But I mentioned that, I showed that before, that it's in a very micro scale size. High diamond anvil in the hydrogen environment, very high loading. It is empirically proven, discovered, minus 23 centigrade with 150 gigapascal. But it's not yet commercial. This is still the invention of the TC and around that. I think it should be the next challenge is how to make it, this is higher TC, and then implementable. The process, the synthesizing method should be scalable. The next candidate, as theoretically proven, is the yttrium decahydrate. That's a room temperature, but still theoretically by density functional theory. And our challenge in Indonesia is that we have lanthanum hydroxide from monazite. It's commercially available from PT Timah. And then we have yttrium phosphate. So I think this is for us a very, very challenging situation. These two, lanthanum decahydrate and yttrium decahydrate.
Yeah. Yes, I agree. I'm very agree with you, Prof. That two material, lanthanum, yttrium, also usually applied for any other functional material. For instance, for the fuel cell, solid oxide fuel cell, also we using that material. Maybe I have the following question, Prof. Andika. Is it okay? Okay. Meanwhile, we have the source of the mining, right? From that material that you mentioned before. Maybe you have the vision for the next future when such of that material we use from the waste or the recycling existing one from the electronic material waste, or we can use, for instance, by other sustainable material. What do you comment about it? Okay, Prof. Andika?
Yes.
Okay, please.
Okay. Can you repeat again your question, because it's some technical communication?
Okay.
Okay. I'm sorry.
Okay.
Okay. Can you?
Okay. So the lanthanum nitrate, lanthanum phosphate form, or how in order to make the proper superconductor?
Okay. Thank you very much for the question. So actually, is it very possible if you use the secondary resource from the waste, electronic waste? It's very, very possible. The question is, the challenge is, if you can extract that, then that material which are superconducting, it's a high temperature superconductor or low temperature superconductor. So that's the basic question first. If you what we find, or if we can extract from the secondary resource or waste is the low temperature superconductor, then actually it is applicable, but it's very with the very low temperature. You have to use either helium or hydrogen. And if you talk about the low temperature superconductor, the challenge is how easy it is to be implemented in the normal daily life. The most popular, the most accepted application of the low temperature superconductor is so far is the MRI. And then there's one in the Research Center for Chemistry, there's an NMR. So actually it's just like that. So the question is whether you find it is low temperature or high temperature.
I see.
I personally have not known yet if we can find lanthanum or yttrium from the secondary resource. I haven't marked that yet in my mind. I still think about it from the primary resource, the monazite and the cenotype. That's okay.
Okay. Thank you. Very insightful, Prof. I have to go back again to Professor Kawai. Later, I will go back to you again.
Yeah.
Okay, Professor Kawai, we have one question here from the floor from Ahmad Ridwan Tresna.
Yeah.
Prof. Kawai, he gave his question. Sorry if my question is not relevant for your presentation. I'm wondering the isotope effect on diamond. We substitute by C12 or by C13, substitute C12 by C13. So can we get a change in the band structure if diamond? And can we make a heterostructure based on isotopic doping?
I
Yeah,
already answered that question by chat. I think that it is not easy.
By chat.
To modulate its band structure by using the irradiation, isotope irradiation, because as you know, the diamond, its chemical bond is really tough. And also, so based on such tough chemical bond of diamond, we can apply those material for the space application. For example, the space emitter system in the space. And also, based on those material property, I think that it is not easy to modulate them. But in the case of the doping level, maybe we might be able to modulate its band structure by changing the doping level, such as it is the famous specialized doping technique, the delta doping, homoepitaxial through the homoepitaxial grown, I think. Maybe.
Okay. Yeah, because Dr. Nugraha is usually he exploring on the theoretical and computational. Maybe he always have the vision, the future vision. He's very good on it. Maybe he interesting on to enhance your research. Okay, maybe later I'll go back again to you, Professor Kawai. In the meantime, I have another question for Professor Andika. Again, this is from Mr. Hendrik. So as we have seen the picture of magnet levitation in your slide by using the spring, so what determine the distance between the dust of two? Is there a way to control the distance? So if I want to make it separate several meters between the dust to spring, how could that be done? Prof. Andika?
Okay, thank you very much, Denny.
Hello, Prof. Andika, can you hear me?
Yes. Yeah, I can hear you. Yes, I can hear you. Yes, thank you very much for the question, and also for Mr. Hendrik. As I mentioned, I already answered that in the chat. It depends on the magnetic levitation, because the Meissner effect as the fundamental of the magnetic levitation is depend on first the magnetic flux that cannot go through the superconducting material when you are below TC. So it means the power to levitate it depends on the magnetic flux. And you can, in some paper, in the coprets and also in the magnesium diboride, they increase that by using the compositional design. So actually, it actually improved the magnetic flux property. But the challenge is that the fundamental challenge in the superconductivity is that this triangular shape diagram of VC, GC, and TC, if you increase GC, can sacrifice the TC. Well, actually, it is possible if you can widen or broaden this triangular shape of VC, GC, and TC. And compositional design, doping, and heat treatment may do that. I
see. Okay. Can I mention about the oral professor research oral presentation book in here? Because when I searching in the Google, it's already in the link open for everyone, right?
Yes. My oration, Professor.
Yeah, oration.
Yeah.
I just want to make.
Okay. I think if I cannot go too far from the superconductivity, then my specific answer for this specific question is that use the high temperature superconductor. It is very possible to do that if we can have the room temperature superconductor. Then there is no hush regarding the cryogenic cooling. So that's why the goal for this lanthanum and yttrium decahydride, it's very, very, we can do this technology if we can, let's say, I say that eliminate cryogenic cooling system. It's very, very complex and not practical. So first, in the aspect, from the point of view of superconductivity, to answer that, then use the high temperature superconductor, especially the room temperature one. Then from that, we can move on. You can imagine that if this happens in the room temperature, this effect and this levitating it's a development. And then the first one is how to attain the room temperature superconductor with the scalable synthesizing process technique. Not the use the diamond anvil is so very small, micro scale. It is not implementable.
Okay. Okay. Meanwhile, we waiting another question from the floor, from the participant. I have another question for you, Prof. Andika. Is it possible the superconductivity of the material is changed by the form of the material? For instance, we have the similar composition of the material. We develop the wire, the plate, and maybe another bulk form. Is it different with the different of form of the material to their superconductivity?
Yes, you mean in the form of your question in the form of wire or in the kind of material, the variation of material? Sorry, I didn't get
the shape, the shape of the
shape.
material.
Okay, yeah, the shape. Yeah. Okay, yes. So actually, if we talk about the shape, if let's say wire, and then wire, we talk about the coil, or we talk about the bulk material. So there's of course, there's a characteristic. There's a characteristic. It's not the same, but the fundamental property of this, I mean, the superconducting wire, have to be careful regarding. Actually, even though we already have the MRI using the superconducting magnet and coil, there's training. And when you coiling the wire, there is the strain that conduct. But if you use the bulk material, then the question is how in the aspect of how we manufacture that, when the scale or the size of it is already significantly big enough. I mean, the superconducting material is actually most of them is very brittle, and then especially when we talk about the high temperature superconductor, then it's very challenging when we shape it into the bulk material, either the straight or bend. That's actually the question in the manufacturing aspect of that. Even though it's still possible, what is still normal is using the wire and then coil.
Wire and coil.
Yeah.
So that's the most visible one, using wire form.
Right. That is the most until now the dominant of this superconducting shape. I mean, the superconducting commodity or superconductor commodity in the aspect of the shape. Still dominant is in the wire, or ribbon, wire or ribbon.
Okay. Prof. Andika, would you please describe about the harvesting concept based on the superconductor material? I still not clear enough before. Excuse me, if you
Okay.
please.
Okay. Okay. How to the energy harvesting of this based on this superconducting material. So actually, the energy harvesting that people talk about globally is something that happen in the daily life without people too much realizing it. Okay.
Yeah.
Of course, energy harvesting can be from solar energy, yes, wind energy, yes, but also like when we talk about the vibrational energy, sound energy, and then kinetic energy based on the small scale activity. So the difference of this energy that is developed and then applied for the autonomous device. When you apply that, of course, you can use copper wire.
Correct.
A circuit that is very conventional. The idea of this application of superconducting material in energy harvesting is to replace or to substitute this copper or the conventional material that acts as the conductor to become superconductor, so that the energy efficiency is getting higher. Now, in my presentation, one of the very good example is when you the gallium indium tin, when you make it into nano droplets by the sonification, and then you use the technology of lithography and make it to the circuit, something like that. That literature that I observed and I read, this three-party people that developed this gallium indium tin, they mentioned that they also already developed the prototype of this wearable electronic based on this gallium indium tin, even though I didn't see the prototype of it. But they mentioned, they claim that they developed also the wearable electronic. I believe it is prototype, that's not yet commercial, based on the lithograph gallium indium tin. So this is how to increase the energy efficiency based on the conducting property. So when you use superconducting material, it means R is 0. It means higher.
Correct.
So that's the position of the superconducting material in the energy harvesting system.
Okay. Now it's clear, more clear than before. Thank you, Prof. Andika, for your insightful replay answer. I'll go back to Professor Kawai. Are you still there, Prof?
Yes.
Hello? Okay, maybe this is out of topic from your slide, but I just curious about the perovskite application, the perovskite oxide of your material, like the bismuth ferrite oxide, for instance, for the PV interest, or are you also concerned on the solar energy application of your perovskite oxide?
I know there are many researchers who try to create a specialized solar cell using the fundamental ferroelectricity. I know the one of the some person, one of the my friend also try to create such a new solar cell system, but I think that it is not easy to apply those systems for real application, because as you know, the ferroelectric material is roughly work as a insulator. So it means by using the ferroelectric remnant polarization, maybe we can create some career and by photo irradiation, but it is really difficult to pick up those created career through the insulator like ferroelectric, I think. Yeah. Of course, it is the scientific interesting approach, but with considering the real application, maybe it might be really difficult, I think.
Yeah. Okay.
Yeah.
Thank you very much, Prof. Kawai and Prof. Andika, for the insightful explanation. Oh, we have still one question for Prof. Andika. Okay. For Prof. Andika, this is the question from Dr. Agung. So, do you have the calculation about the efficiency of energy harvesting by using superconductor compared to the conventional materials? For instance, from vibration energy, how many percent the efficiency using the superconductor? Please.
Okay. Thank you very much, Denny, and thank you very much, Dr. Agung. That's a very good question. If you ask me about the efficiency in the quantitative way, I haven't had the answer about it. Okay, but qualitatively, it should be very logical that the energy efficiency increase. Now, the question is, when we talk about the energy harvesting in this method, it's actually not no longer about the, for example, solar cell and a megawatt water energy and a megawatt. That's in the very small scale. In a very small scale, that's what people agree on the definition by energy harvesting in more common way. Now, of course, then if we can use the superconducting material, okay, which has a zero electrical resistivity without getting any complication or any trouble with the cooling system, then it should be very it has significant effect. I haven't had known yet about the quantitative value in statistical way, not as a by example, in statistical way, when we use the superconducting material for small scale energy harvesting. What is the energy efficiency? But I believe based on the logical aspect or logical property of this superconducting, it will increase the energy efficiency. But I haven't had any known number, a statistical number regarding what the efficiency, the very common way that can be efficiency that can be yielded by using this superconducting material for the energy harvesting, especially in the wearable electronics as well and the wireless sensor network. But it should be better. Okay.
Thank you very much, Prof. Andika. I think we have to finish this first session from the plenary session. So please, I would like to invite all the participants to turn on your video. We would like to take a picture together. Please, everyone, just turn on. The operator, the co-host will take a picture for us. Professor Kawai, can you open your video?
Okay, ready?
Oh, ready. Yeah. Okay. Okay.
Kang Denny?
Okay, Panono, please. Yes.
Okay. Please, if anybody the photo is not showing, I think the background is not compatible, or maybe you have to turn off your green screen. if you click the green screen, maybe sometime your face will cover by the background. I think like okay.
Okay, maybe Pak Nono, you can give us the mark. Okay, is it finished, Pak Nono?
One more.
One more. Okay, okay. Dr. Nugraha,
There are
please.
2 slides. So now I'm gonna take the second slide.
Okay. Give your best
3,
smile.
2, 1. Okay, finish.
Thank you very much, Dr. Professor Kawai and Professor Andika, for your insightful presentation. So we have to finish this session, and we will go back again at the 10:40. Maybe we take the break time for about 10 minutes, I think. Yes. About 10:40, we will continue with our next plenary speakers, to Dr. Bambang and Dr. Fatwa Firdaus. Okay. I think I return back to the MC. Please, Dr. Wita. Is there any Dr. Wita now? Okay. So if no, maybe we just closing for this first session. Thank you. I would like to say thank you again. Thank you very much for Professor Andika and Professor Takeshi, and to all the participants. And we will go back again at the 10:40. We will have the break time about 10 minutes. Thank you very much.
Segenap rasa dan tenaga untuk menghasilkan pemikiran terbaik bagi negeri tercinta, kami ada untuk Indonesia. Mewujudkan diri sebagai Lembaga Ilmu Pengetahuan Indonesia yang andal, profesional, inovatif, dan berintegritas dalam pelayanan untuk mewujudkan visi Presiden dan Wakil Presiden. Indonesia Maju yang berdaulat, mandiri, dan berkepribadian, berlandaskan gotong royong. LIPI memiliki berbagai pusat penelitian tersebar di seluruh Indonesia, Deputi Ilmu Pengetahuan Hayati, Deputi Ilmu Pengetahuan Kebumian, Deputi Ilmu Pengetahuan Teknik, Deputi Ilmu Pengetahuan Sosial dan Kemanusiaan, Deputi Jasa Ilmiah dan SDM Pendukung Iptek di bawah Sekretariat Utama LIPI. LIPI berperan dalam proses penyusunan dan kelahiran berbagai regulasi dan kebijakan pemerintah terkait aspek ekonomi, politik, sosial, dan budaya. Selain itu, LIPI juga mengelola data dan timbangan ilmiah dalam rangka maupun produk, maupun pengembangan SDM melalui program Indonesia Memanggil. Untuk mendukung riset, LIPI memiliki 5 kebun raya sebagai pusat konservasi flora ex situ. 2 museum yang memiliki koleksi flora, fauna, dan kesejarahan alam Indonesia. Indonesia Culture Collection yang menyimpan koleksi mikroorganisme terbesar di Indonesia. Infrastruktur riset strategis. Dan beberapa pusat berskala internasional, yaitu Asia Pacific Center for Eco-Hydrology atau APCE. LIPI telah menghasilkan hasil riset yang berkualitas dan bermanfaat bagi masyarakat. Meliputi keanekaragaman hayati, lingkungan dan maritim, ketahanan pangan, pertanian, dan peternakan, kesehatan dan farmasi, material maju, energi, teknologi, informasi dan komunikasi, pertahanan dan keamanan, dinamika sosial, kemanusiaan dan kebudayaan, kebencanaan, inovasi teknologi dan pendayagunaan iptek, pelayanan, pengujian dan pembinaan ilmiah, serta peningkatan kualitas SDM iptek. Kerjasama keilmuan LIPI dalam negeri meliputi kerjasama penelitian, lisensi teknologi, pengembangan, aplikasi dan komersialisasi hasil penelitian, kerjasama non-penelitian, dan konsultasi kepakaran LIPI. Sedangkan kerjasama luar negeri, LIPI melakukan joint research, workshop, pertukaran peneliti dan beasiswa mancanegara, selain aktif menjadi anggota dan focal point di berbagai organisasi internasional. Melalui kolaborasi bersinergi, menghasilkan riset yang berkualitas, LIPI terus memberikan manfaat nyata, kontribusi berarti, dan turut mewujudkan cita dan asa membangun negeri kita tercinta, Indonesia. Berawal dari cita dan asa untuk membangun negeri, memberikan segenap rasa dan tenaga untuk menghasilkan pemikiran terbaik bagi negeri tercinta, kami ada untuk Indonesia. Mewujudkan diri sebagai Lembaga Ilmu Pengetahuan Indonesia yang andal, profesional, inovatif, dan berintegritas dalam pelayanan untuk mewujudkan visi Presiden dan Wakil Presiden. Indonesia Maju yang berdaulat, mandiri, dan berkepribadian, berlandaskan gotong royong. LIPI memiliki berbagai pusat penelitian tersebar di seluruh Indonesia yang berada di bawah kepala LIPI, Deputi Ilmu Pengetahuan Hayati, Deputi Ilmu Pengetahuan Kebumian, Deputi Ilmu Pengetahuan Teknik, Deputi Ilmu Pengetahuan Sosial dan Kemanusiaan, Deputi Jasa Ilmiah dan SDM Pendukung Iptek di bawah Sekretariat Utama LIPI. LIPI berperan dalam proses penyusunan dan kelahiran berbagai regulasi dan kebijakan pemerintah terkait aspek ekonomi, politik, sosial, dan budaya. Selain itu, LIPI juga mengelola data dan timbangan ilmiah dalam rangka konservasi keanekaragaman hayati. Menerbitkan tanda pengenal unik publikasi ilmiah terbitan berkala, membuat repositori ilmiah skala nasional, dan memiliki kewenangan sebagai pembina Jabatan Fungsional Peneliti Nasional, serta melaksanakan proses pengukuhan profesor riset di Indonesia. Kini, LIPI juga mendukung percepatan penanganan COVID-19, baik melalui riset berupa kajian maupun produk, maupun pengembangan SDM melalui program Indonesia Memanggil. Untuk mendukung riset, LIPI memiliki 5 kebun raya sebagai pusat konservasi flora ex situ. 2 museum yang memiliki koleksi flora, fauna, dan kesejarahan alam Indonesia, Indonesia Culture Collection yang menyimpan koleksi mikroorganisme terbesar di Indonesia. Infrastruktur riset strategis. Dan beberapa pusat berskala internasional, yaitu Asia Pacific Center for Eco-Hydrology atau APCE. LIPI telah menghasilkan hasil riset yang berkualitas dan bermanfaat bagi masyarakat. Meliputi keanekaragaman hayati, lingkungan dan maritim, ketahanan pangan, pertanian, dan peternakan, kesehatan dan farmasi, teknologi dan pendayagunaan iptek, pelayanan, pengujian, dan pembinaan ilmiah, serta peningkatan kualitas SDM iptek. Kerjasama keilmuan LIPI dalam negeri meliputi kerjasama penelitian, lisensi teknologi, pengembangan, aplikasi dan komersialisasi hasil penelitian, kerjasama non-penelitian, dan konsultasi kepakaran LIPI. Sedangkan kerjasama luar negeri, LIPI melakukan joint research, workshop, pertukaran peneliti, dan beasiswa mancanegara, selain aktif menjadi anggota dan focal point di berbagai organisasi internasional. Melalui kolaborasi bersinergi, menghasilkan riset yang berkualitas, LIPI terus memberikan manfaat nyata, kontribusi berarti, dan turut mewujudkan cita dan asa membangun negeri kita tercinta, Indonesia. Untuk menghasilkan pemikiran terbaik bagi negeri tercinta, kami ada untuk Indonesia. Mewujudkan diri sebagai Lembaga Ilmu Pengetahuan Indonesia yang andal, profesional, inovatif, dan berintegritas dalam pelayanan untuk mewujudkan visi Presiden dan Wakil Presiden. Indonesia Maju yang berdaulat, mandiri, dan berkepribadian berlandaskan gotong royong. Penelitian tersebar di selimbangan ilmiah observasi keanekaragaman hayati. Menerbitkan tanda pengenal unik publikasi ilmiah terbitan berkala. Membuat repositori ilmiah skala nasional. Dan memiliki kewenangan sebagai pembina Jabatan Fungsional Peneliti Nasional. Serta melaksanakan proses pengukuhan profesor riset di Indonesia. Kini, LIPI juga mendukung percepatan penanganan COVID-19, baik melalui riset berupa kajian maupun produk, maupun pengembangan SDM melalui program Indonesia Memanggil. Untuk mendukung riset, LIPI memiliki 5 kebun raya sebagai pusat konservasi flora ex situ. 2 museum yang memiliki koleksi flora, fauna, dan kesejarahan alam Indonesia, Indonesia Culture Collection yang menyimpan koleksi mikroorganisme terbesar di Indonesia, infrastruktur riset strategis, dan beberapa pusat berskala internasional, yaitu Asia Pacific Center for Eco-Hydrology atau APCE. LIPI telah
Okay, welcome back again to our ISMM 2020 seminar. I would like to welcome to Dr. Fatwa. Dr. Fatwa, are you ready to join with us?
Yes, I'm here.
Okay, nice to hear you. Maybe in the German now it's very early morning, right?
Yeah, it's 15 minutes to 5 now. Yeah.
Oh, it's subuh time in Indonesia. Subuh. Okay, we are very sorry to disturbing your time, your very early morning time.
No, I'm happy to do it. Thank you very much for the opportunity. Yeah.
Oh, yeah. It's also the honor for us actually that you are accepting our invitation. Okay, Dr. Fatwa, and we also already hear Dr. Bambang. Hello, Dr. Bambang, can you hear me?
Yeah. Yeah, okay.
Okay. Okay, wait a moment, because
my voice is okay.
Okay, Pak. No problem. It's clear. Very clear enough. Yes, it's clear. Okay, for this second session, we have two plenary keynote. For the first time is Dr. Bambang Prihandoko, and then the second one is Dr. Fatwa Firdaus. Okay. Dr. Bambang will deliver his speech about the current research and development on battery, and Dr. Fatwa will share to us about the photocatalytic and water splitting advanced materials status. Okay, without further ado, I would like to starting for the first speaker, Dr. Bambang, but I would like to share his bio, his biodata. His full name is Dr. Insinyur Bambang Prihandoko, MT, and Dr. Bambang finished his study from the TU Delft in the Netherlands, in the Holland, and then he continued again. So he got 2 master from the TU Delft and then from the Universitas of Indonesia, the metallurgical and material engineering, and also his doctoral from the University of Indonesia. And Dr. Bambang have a very tremendous research experience regarding the battery or the fuel cells application for the energy application material since 1999, since the early 2000, the solid electrolyte application until currently, until now. Now is Dr. Bambang many research about the lithium ion battery, and I think for the Indonesian researcher about the battery, Dr. Bambang is already very well known. He has many publications, both national and international. And then I would like to, yeah, and also many the acceptance that already got by Dr. Bambang. Now he also as the head of the consortium battery, research battery for the lithium, and then as the committee, the head of committee for the SNI nanotechnology since 2011, and also for the SNI, other SNI standard since, yeah, for the mobile, the electrical vehicle since 2016 until now. So as the Indonesia, the member of the MITI, and also the member of the Matrix, Masyarakat Transportasi Tenaga Listrik, also MITI, Masyarakat Energi Terbarukan Indonesia, and also as the member of the Listrik Indonesia. Okay, maybe the co-host, please share the PPT of the Dr. Bambang. Yeah. Okay. Dr. Bambang, the time is yours. It's about 40 minutes. Yeah, you can share your presentation. Please.
Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
And good morning or good afternoon. Ladies and gentlemen, I want presented about the lithium battery as key of energy era. This is the new development of new grid of a lithium battery to make a new energy revolution. And next, to make a active material electrode sheet. Yeah, next. My outline of my presentation is really about the first is energy revolution, and second is battery, and the third is lithium metal phosphate, and the last is conclusion. And I want this now about energy revolution in the industrial revolution. This because become industrial revolution need energy, more energy to make a production, mass production, and this it is described to important innovation to meet the industrial revolution and energy revolution. This is the because become an industrial revolution and what the energy revolution. And we can the graphic is between the conventional energy to unconventional energy, like fossil energy. This is very, very high development. And then next, yeah. And the energy revolution is driven by scientific and technological progress. Yeah, this is the first is the progress on the petroleum scientific and technological revolution. The proceed the transition from conventional to operational oil and gas. But this now the limited in the limited years become. And the second energy revolution is to battery energy storage. Yeah. And then there is begin this year to in the golden age of a new energy. Yeah. Next. And this is the from the China from Chinese national and they make a paper and publication, and so talk about the new energy revolution may come earlier than expected, especially to reduce power generation with the new energy and breakthrough in battery energy storage technology, which strongly promote the coming of new energy era. But there is they have a requirement for the new energy era for the technology of battery is if they can be used for mass production of battery, it can be charged quickly and have a long service and good durable. The new energy era will come sooner. This become earlier in this. This is the requirement. Is the first is mass production, and the second is charged quickly, and the third is a long service and good durability. I want one explanation about this requirement for technology battery in the next presentation. Yeah, next.
Next slide.
We want the 2025 and Netherlands as a same, and the last is France and UK, Great Britain. I want 2040. I want to stop with the conventional electric, the conventional electrics. So for the fast charging, then I modified the lithium titanium to sodium lithium then the first and the what is lithium rich nickel metal cobalt is more than 100 as the begin nickel metal oxide, and this is around 280 milliampere hour per gram. And we want the development of lithium and iron phosphate to new lithium manganese phosphate by adding of the cobalt. We want the response of the material is the same as lithium, nickel, mangan, cobalt, maybe more. Next slide. I interested to the metal phosphate is more safety. Metal 1 phosphate was chosen as the best for the development of a lithium red and lithium white battery. We have product as lithium merah putih lithium battery. Next slide. And we have planned to produce the lithium red and white battery. This merah putih lithium battery in Indonesia. Lithium red battery as lithium titanium battery. This is a fast charging battery. The composition is anode is sodium lithium zirconia titanate, electrolyte by lithium PF6, and cathode is by lithium manganese phosphates. And lithium white battery, there is lithium putih lithium battery as a lithium ion battery. The composition is anode graphite, electrolyte 6, and cathode is same as the composition is anode graphite, electrolyte 6, and cathode is same as lithium battery red. Next slide. Therefore, we focus to make an industry of merah putih lithium battery. The value chain is like this, and we produce from ore of mining to chemical material and active material that's converted in anode and electrolyte, and we make produce to electrode sheet, and then we make manufacturing for assembling cell and then battery pack. And then this is my work in the national priority of research per lithium battery. No. Okay. This may be the next slide. 3 developed by the nanoscale technology will be able to meet the challenge or requirement as a new energy in the future. The second conclusion is development of lithium metal phosphate batteries can be expected to increase Indonesian role in the world market of lithium battery. I think this my presentation is next slide. Thank you for your attention. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, Dr. Bambang, for your presentation. I think you should hold on for a moment. We will have the discussion Q&A after the next presenter, Dr. Fatwa, deliver his materials. Okay, Dr. Fatwa, you ready now? You can share your PPT now. Okay.
Yes, let me try.
Okay, but before Dr. Fatwa deliver his speech, I would like to read his bio, his CV. His full name is Fatwa Firdaus Abdi. We are very lucky got his as one our plenary keynote speaker because his well, the education is very excellent. He got his Bachelor of Engineering from the Nanyang Technology University, Singapore, and then he got the 2 master degree, Master of Science from the Master of Engineering from the MIT, and then he got his PhD cum laude from the Delft University of Technology, or same university like Dr. Bambang. And his current position as the Deputy Director of Institute Solar Fuel at the Helmholtz Zentrum Berlin in German, and then group leader previously as a group leader and senior scientist at the same institution. His publication for sure more than 6.
Dr. Denny is the one having problem.
Oh, sorry. Before I'm still mute. Okay. I'm sorry for the connection of mine, Dr. Fatwa.
No, that's okay. I was just
okay. Without further ado, okay.
Can I start
the time is yours. You can deliver.
Okay.
You can start now. Your time is about 40 minutes. Okay, please.
Okay. Yeah. Thank you very much, Dr. Denny, and also for the organizers for inviting me and also providing the opportunity to deliver this presentation to share a little bit about our work. As introduced, I'm working on solar water splitting and Institute for Solar Fuels in general, but I've been working mostly on solar water splitting. And today I'll share a little bit of a story along the value chain from the materials development point of view. Also at the very end, later, just about 5 minutes, I'll share a little bit our activity in transforming these materials that we develop into a large area device, a larger area at least outside of the laboratory scale. All right, so I'll start with a little bit of introduction on where I work, because I I don't think that everyone is familiar with SZB. So the name is Helmholtz Zentrum Berlin for Materials and Energy. So it's one of the research center under Helmholtz Association. So in Germany, the national labs like LIPI is divided into 4 different associations. 3 of them are relatively big. Those are the Max Planck associations. Those are the Fraunhofer as well as Helmholtz Association. So, and under Helmholtz Association, there are 19 different research centers. So maybe one of the ones that is more well known is the Deutsche Synchrotron. So that's DESI. So that's a German synchrotron. It's also under Helmholtz, or the German Aerospace Agency, the DLR. That's also under the Helmholtz Association. We are one of the mid-sized research center in Berlin. We're focusing on materials and energy, as the name suggests. And in Berlin, we are located in 2 different places. One is located in Wannsee, so that's a little bit, let me see, can I show my pointer? There you go. So the Wannsee is in the southwest of Berlin. So if you know, Berlin is already almost out of Berlin, this area, a little bit green. So this is close to Potsdam, the next city. And there we have, we used to have a nuclear research reactor, but in last December, it was already shut down. So now it's being decommissioned. And we have a lot of other institutes doing compound semiconductor photovoltaics, electrochemical energy storage or battery, like the previous speaker has shown, soft matter, magnetic material, and the institute where I'm working, which is solar fuels. And the second location is Adlershof. So that's really, I think it's about 30 kilometers or close to 40 kilometers from Wannsee. So that's really the other side of Berlin, southeast. And that's where we have our synchrotron. So this is a smaller synchrotron than the German synchrotron at Hamburg, but this is still very useful, and it for a lot of materials research that we're doing. So it's called BESI, or Berlin synchrotron. Yeah, was I muted? Maybe I was muted. So we have the Berlin synchrotron, and on top of that, we have the also other research activities on photovoltaics, and also the PV Competence Center that's located in Adlershof. Yeah, so I'll begin by motivating a little bit why we're interested in renewable energy, right? So the previous speaker has already introduced the topic, but I'll restate very briefly, or maybe in order to move towards the water splitting. So the whole goal is actually to reduce CO2 emission. Excuse me. So maybe you've actually heard the narrative of course, the finite amount of fossil fuels, right? But in all honesty, we do still have a lot of fossil fuel reserves. There's enough for the next 100, maybe even a few hundred years. So the main problem with using it right now is really the environmental consequences that comes with using fossil fuels. And there's this relatively recent paper that came out in Science about like 4 years ago now, that actually listed that in order for us to limit global warming to less than 2 degrees, we need to actually decrease the atmospheric CO2 level by negative 10 gigaton carbon dioxide per year by around 2050. That is actually a pretty big and ambitious target. The question is, how can we actually do that as a whole, right, as the world? Now, I write a very simple equation here. Is a definition equation, so it's nothing fancy. So it's the total number of CO2 that we emit. We can correlate it to the amount of population, so how many people are living in a certain land or in the world, right? Multiplied by the GDP, the gross domestic product per population, multiplied by the amount of carbon dioxide that is emitted per GDP, right? So if you see that it's very simple, the populations gets cross here, GDP is also cross, and you get CO2 equals to CO2, right? So that's really simple. So in order for us to decrease the total amount of CO2, one of these terms needs to be decreased. The problem is with population, you know, that it's ever increasing, right? So it's really hard to imagine that we decrease the amount of population in the world, right? And as is the case for the GDP per populations, right? So GDP per capita, all countries would like to get better. So especially before the pandemic, right? I mean, throughout the pandemic, we see a decrease of GDP, but I think we hope that we will get out of this pandemic situation. And again, we'll be back as normal. Every country will want to be more prosperous, which means that the GDP per capita of almost all countries will actually increase. So our only hope is actually in decreasing the CO2 per GDP. If we want to decrease total CO2, we need to decrease the CO2 per GDP. Can we actually do that? Well, the data tells us that it has not been shown. So this data that has been collected here is showing the CO2 emissions as a function of GDP for various countries in the world back in 2016. What you can actually really see here is that the amount of CO2 emitted is really proportional to the GDP that country has, right? So historical data doesn't really support our goal of reducing this. For example, Indonesia is there, right? And somewhere in the middle here. And of course, we want to increase the GDP per capita. And if we actually go along this plot here, unfortunately, it will be accompanied with increased CO2 emission. As another correlation that is shown over here is this is still the CO2 emission on the y-axis, but it's against Human Development Index. So Indonesia is somewhere here, right? And if we want to, of course, we want to increase our Human Development Index. And if we do that, according to this plot, we also will increase the emissions per capita. So now, this is historical data or like the data that we have right now. Can we actually break this relationship? So instead of Indonesia, for example, moving upwards in this plot, can we actually move horizontal instead, right? Being more prosperous, increase our GDP without increasing the CO2 emission. Now let's break down the factor that is going inside the CO2 per GDP even further. So we can actually correlate it with the amount of energy consumption per GDP multiplied by the amount of CO2 per energy that we consume. So the first term we can actually decrease by more efficient use of energy. So basically replacing your bulbs with a higher efficient LED bulb, for example, or other improving the energy efficiency of your engine and whatnot. That can be done with for the first part. But for the second part, we can actually achieve this decrease by transforming to low or even zero carbon energy source. And this is actually the main motivation why we are actually working, looking for alternative renewable energy. So we would like to replace the energy, the fossil fuels that we have right now with something that doesn't emit carbon, so that we don't need to move upwards in this plot over here. All right, so with that introduction, I'll come to show you or share with you 3 facts that I think it's a fact for a search of renewable alternatives. So I don't know if this is a real fact or alternative facts. I think we can argue about that. But I hope I can convince you in the end that some of this is actually pretty true. First of all, I think we know that the sunlight among the various sources of energy that's available to us is the most abundant source of energy. So we have about 120,000 terawatts that is incident on Earth. And 36,000 of it, terawatt of it, is actually incident on the land area of the Earth. So that's so enormous, such that if we actually just take 0.8% of the surface of the land in the world and cover it with 10% efficient solar device, which is already, the commercial devices are already way ahead of this efficiency, we can actually achieve 30 terawatts, which is the total energy consumption predicted in the year of 2050. To give a feeling about how large or how small that 0.8% is, you can see that if the whole map of the world is here, we just need to cover one small part of South Africa. And in the case of Indonesia, to give a little bit more perspective, Indonesia energy use is 250 gigawatts in 2018. And therefore, we actually need about 20,000 kilometers square of area for that. And just as a comparison, East Kalimantan province alone is way larger than that, and even Central Java is larger than that. So of course, it doesn't need to be concentrated, but if we actually spread it out for different area, we can actually cover 20,000 kilometers squares pretty relatively easy. We do have the land area. The problem with solar energy or sunlight is the intermittency. So the availability period of solar energy doesn't coincide with the peak period of energy demand. So of course we have the daily cycle. So sunlight is most available during the midday, the middle of the day, the noon. Demand doesn't work like that. So we need more energy in the morning, in the early morning, and also late early evenings, for example. And it doesn't really match with the availability of sunlight, right? Also, we have seasonal cycles. Mind you, so the chemical fuels such as gasoline, why we like it so much, because it has a really high energy density as well as a high power density. Batteries and supercapacitors are good alternative, but their energy and power densities are nowhere near what we can achieve with chemical fuels. And why is that the case? That's really because we are actually storing energy in chemical fuels in the densest form possible, which is chemical bond. So it's bond between atom. That's how we store the energy. So that's sort of the fact. Batteries, it doesn't mean that batteries and supercapacitors do not have applications, of course, right? But I think this shows that if we actually need to work on all of them, and some applications you cannot actually fulfill everything with just batteries or supercapacitors. The final fact, or more of a situation, so this is an empirical situations that we are facing right now. Unfortunately, electricity is still inaccessible in many locations. So this is related on how we are using energy. We actually do not consume most of our energy in the form of electricity. We only use about 17% in the form of electricity, and 83% of our energy use is in the form of fuels. What does it mean? It means we do have large infrastructure for fuels, but actually not so much for electricity. So now if we combine these three facts together, I think it's not so difficult for us to see or try to conclude that one of the most probably interesting or attractive way of alternative energy is if we actually store or try to make fuels from sunlight. So if we can do that, then we can actually use the abundant source of energy, which is sunlight, that's potentially able to fulfill the whole world's energy demand, and at the same time overcome the intermittency of sunlight. But can we actually do that? Of course, the answer is yes, and that's what plants have been doing in the process that we all know very well called photosynthesis. So plants take carbon dioxide and water and use sunlight to transform them into sugar, here, the glucose, some kind of sugar, and release oxygen. Now, it turns out that although this reaction can be driven by sunlight, this is not the simplest reaction. So this consists of multiple how do you call it? You can break it down to several reactions, and the formations of glucose itself is actually happen in the dark in the plant itself. The simplest reaction that you can do with sunlight is water splitting, or one of the simplest is water splitting, where you take water molecules and you break it down into hydrogen and oxygen. And then when you have hydrogen, you can actually use it directly as fuels in fuel cells, for example. Toyota Mirai or different car manufacturers have actually already producing this and releasing it commercially. Also power generation. Siemens also have already working on this. Or you can actually use hydrogen in order to combine it with different types of reaction in order to make whatever it is that we're already making right now. For example, if we put it in a Haber-Bosch reaction, combine it with nitrogen, we can actually make ammonia. And this is something that we're already doing right now. But the hydrogen, unfortunately, comes from unclean or non-green sources. And ammonia is very important because it's a prerequisite or the precursor for fertilizer, which is important in order for our food, right? So to feed us, actually, basically. And another alternative is actually to combine it with carbon monoxide or carbon dioxide in a Fischer-Tropsch reactor, where we can then make any hydrocarbons that we want: methanol, diesel, plastics, paraffin, naphtha, whatever. This process has actually already been done in a large scale in many petroleum or refineries, right? So basic ingredient over here is that how can we actually split water into hydrogen and oxygen? And one of the easiest or the simplest way, no, I wouldn't say the easiest, the simplest way of doing that is in a photoelectrochemical cell. The process is as follows. So we take semiconductor, the simplest configuration is shown over here, where we take semiconductor and in this case metal counter electrode here, connected with wire, and we dip it into an electrolyte. And a semiconductor, as you know, it has this valence band and conduction band, where we can actually carry, where we have a full of electron below valence band and empty of electron above valence band, separated by a band gap, right? And for semiconductor, the distance of the electron to the back contact and the holes to the surface over here. And once the holes here arrive at the surface, it then can oxidize water to form oxygen, whereas electrons goes to the other side and reduce proton to form hydrogen. So the overall reaction can be shown over here. So the half reaction is we have the proton reduction to hydrogen and the water oxidation to oxygen, but the overall reaction is just what I showed you in the previous slide. Water split it into 2 molecules of hydrogen and 1 molecule of oxygen. As you can imagine from this scheme of how it works, one of the most important component is the semiconductor materials, right? So this has been the holy grail of this photocatalysis field, is actually trying to find the materials that actually fulfill all the necessary requirements for photocatalytic water splitting or photoelectrochemical water splitting. The requirements is as follows. So we need to have good visible light absorption, of course, because sunlight
Halo, Dr. Fatwa.
Hello, I'm sorry. I'm back. I'm sorry. I don't know why it's got disconnected.
Okay.
I'll try to share my screen again.
Okay, please.
Can you see it? Yes.
Yes.
Okay. I'm sorry. Okay.
Yes.
I'll continue. Yeah. So
yeah,
so the requirements, first of all, is good visible light absorption. That's because in sunlight, if you take the solar spectrum, the large part of it is actually visible light. So we need to have high amount of absorption over there. Second, we also need to have a suitable band edge positions, meaning that the conduction band and valence band needs to be positioned well relative to hydrogen and oxygen evolution potential. And that's because the electrons and holes needs to have enough energy in order to reduce or oxidize water. We also need to have efficient catalysis and efficient carrier transport within the semiconductor. We need to have high stability. We want to dip the semiconductor in water, right? And we also need to have the materials that are cheap. Now in our institute, we're interested in complex metal oxide semiconductors as a material class. And why is it the case? The reason is we like to take advantage of its relatively high stability as compared to 3-5 semiconductors, for example, or as well as the low cost, right? So it is not, so it's actually around in our daily life more than we know it as a yellow pigment in paint or printing ink. And it's also photocatalytically active. So we already know this for more than 20 years. Monoclinic scheelite is the photoactive phase, and it's an n-type semiconductor with a band gap of 2.4 electron volts, meaning that it absorbs sunlight up to 520 nanometer, which is why the color is yellow. In our group, we deposit it very simply using spray deposition or a spray pyrolysis, where we prepare a precursor consisting bismuth and vanadium precursor, fit it into this nozzle, and
Oh. Halo, Dr. Fatwa.
Yeah, hello?
Yeah, now it's okay. Okay, please continue, Dr. Fatwa. Hello?
Hello? Yeah.
Yep.
Yeah, so I really don't know. For some reason, Zoom keep kicking me out, and then I'll try coming back in. I'm really sorry for this.
It's okay. Sometimes happen.
Okay, so
please continue.
I try to continue here. So our approach is that we try to identify what's limiting the materials.
Halo, Dr. Fatwa. We're still waiting for Dr. Fatwa. Maybe he had some internet connection loss. Halo, Dr. Fatwa. He's still mute. Yeah. Okay. Maybe your video to lowering the bandwidth. I think I just share your presentation.
Yeah. Okay, I'll try to do that. Right, I'll try to stop my video and then I'll just share my presentation. Okay. Do you see it now? Yes. I'm assuming so, right? Okay, so we try to identify what's limiting the.
Sorry, the PPT not yet shared.
Oh.
Okay. Okay, no, it's okay.
Yeah. So we try to identify what's limiting the performance in our bismuth vanadate, right? So the way that we do it is we try to identify which of the processes that happen inside the material that is limiting. So we can divide it into absorption, so light absorption here, and then carrier separation, so how the electrons and holes are separated, and finally the catalysis that happens at the surface. The first thing that we found out is that these water oxidation kinetics are slow, and that can be actually the slow process prevents our photocurrent for having too high. And the solutions to that, as a way to solve that, we deposit cobalt phosphate catalyst. As you can see on the right-hand side, we have the photocurrent as a function of potential. Without the catalyst, we have this black curve. And as soon as we put this cobalt phosphate catalyst, we increase the photocurrents quite significantly. The next problem that we found is on the poor carrier transport, meaning that the conductivity is not very good. So we try to dope it with tungsten, for example. Tungsten replaces vanadium and introduce additional electron. Or we can also insert hydrogen. Hydrogen goes to the interstitial and insert electrons. So this solves the poor carrier transport issue. And once we solved that, we came into another problem, which is the poor charge carrier separation. And we addressed that by introducing dopant gradient. What we did in short is that we tried to introduce electric field inside the whole thickness of the film. And by doing that, we separate electron to go to one side and then holes to go to the other side. Other peoples have also tried nanostructuring. We actually do not work on this methodology in our labs so much, but this has also been proven very effective. So you try to decrease the amount of decrease the thickness of bismuth vanadate so that the carriers do not need to travel so far. But by nanostructuring, you ensure that the light absorption is still pretty high. And in terms of the progress of bismuth vanadate, it's summarized over here. So the number of photocurrents of the different groups that have been working on bismuth vanadate. And as you can see, in the last 10 years, we have really had a really significant increase of performance, right? So it's such that the highest photocurrent that we have right now is already very close to the theoretical limit. Even so, the oxide-based devices have also been demonstrated. For example, we've shown a device that shows 5% efficiency in collaborations between Delft and SZB. And we also collaborated with our colleagues in Korea, where we show a device of about 8% efficiency. And that's also, of course, not only us, other groups have also been working on oxide-based devices. Now I go back to this plot now, and the other message that I'd like to send is that since the photocurrent is already very close to the theoretical limit, the only possibility if you want to improve the performance more significantly is if we can actually go beyond this limit, right? Or in other words, can we actually shift this limit upwards so that we can go further than this 7.5 milliamps per square centimeter? And one way to do that is actually by decreasing the band gap of bismuth vanadate. And we can do that, for example, with sulfur incorporation. So bismuth vanadate, the valence band is composed of mainly oxygen 2p orbital. And if we replace that with sulfur 2p orbital, for example, that is energetically higher than the bismuth than oxygen 2p, we can increase this valence band positions and decrease the band gap. And when we decrease the band gap, we can increase the absorption, the light absorption that we can part of the solar spectrum that we can absorb, and therefore increase the theoretical limit. So this is the work of Marlene, who was a PhD student in my group. She graduated last year, wherein she did introduce the bismuth vanadate under different partial pressure of sulfur. And as you can see from the photograph here, the film turns from yellow to light brown and then finally to dark brown. And if we look from the X-ray fluorescence and X-ray photoelectron spectroscopy results, we can see that the amount of sulfur, so this is the sulfur to vanadium atomic ratio, increases indeed when we increase the sulfur partial pressure. So this is also collaborations with group at NTU Singapore, Professor Lydia Wong, also Indonesian diaspora, maybe some of you know her, and also my colleague in Kaus who did the DFT calculation. So we, in the end, we shifted the band gap by about 0.3 eV, which then increases the theoretical maximum up to 12%, from 9% to 12%. We confirmed this band gap shift. As you can see here, the band gap moves from about 500 nanometer here to about 580 nanometer. Instead of sulfur, nitrogen has also been reported to be effective, but unfortunately for our particular bismuth vanadate, this has not been successful. Another method is actually to come up with, if we don't want to reduce the band gap of bismuth vanadate, is to come up with a novel complex metal oxide altogether. And one possibility is copper bismuth oxide. It has a band gap of 1.8 electron volts, so it's really good. And the properties are pretty comparable to bismuth vanadate, but the problem is stability. So the copper here, if we put it inside the solution and you do photo reduction of water in this case, it can get reduced to copper plus or even copper metal. Nevertheless, people have actually already been working on it. It's still in earlier development, so we have a couple of films that are shown over here, and the improvement have been quite significant, but we're still a long way to go to the theoretical limit. On this particular front, I also have an ongoing collaborations with Universitas Indonesia, where we try to look at this copper bismuth oxide and nanoparticles of bismuth for a CO2 reduction to formate. Another attractive material or novel complex metal oxide is tin tungstate. So it has a band gap of 1.9 electron volts. So this is also pretty good. And this is a work of Moritz, who graduated last year. He did his PhD, finished his PhD last year. So in this case, we deposit our alpha tin tungstate using pulse laser deposition. As you can see here, we use excimer laser to ablate the target and then deposit it on substrate. So this is under vacuum deposition. Why do we want to do that? Because we want to keep the tin here under 2+ oxidation state. Another problem with this material, though, is that the tin 2+ oxidizes to tin 4+ under photoelectrochemical conditions, which is what you see over here in the red. A bare alpha tin tungstate show a photocurrent at the beginning, but it decreases quite rapidly to almost 0. We can overcome this by depositing a protection layer, nickel oxides. And if you do that, we can actually extend the stability. So this is current as a function of time under sunlight illumination. The performance is relatively stable. And although the photocurrent is still pretty small, so less than 1 milliamps per square centimeter, but this is the record of this material. And we hope that we can actually improve this further. On the other side, the nickel oxide deposition is, on the one side, nickel oxide deposition is good to extend the stability, but at the same time, it actually decreases the photovoltage. As you can see here, this is the photovoltage as a function of nickel oxide layer thickness. And in order to understand this, we went to BESI, the synchrotron in Berlin, where we did hard X-ray photoemission spectroscopy. We want to understand the interface, what's happened at the interface here between alpha tin tungstate and nickel oxide, and we try to investigate it with X-ray with different photon energy. So this is the work of Patrick, who is a current PhD student in my group. So we look at the gist of the study is shown over here, where we'll look at the tin 3D orbital or the core levels as a function of the thickness of nickel oxide. And as you can see, the peak shifted to higher binding energy as we grow thicker tin oxide. It can be interpreted as follows. So we can actually see that if we go to higher binding energy, the tin 4+ contribution is actually increases. So what we see if we deposit thicker nickel oxide layer, we have higher contributions from tin 4 plus instead of the tin 2 plus. And we work with our colleagues at KAUST again, and which shows that if you have tin 4 plus, you actually have a mid-band gap state, intra-band gap state that can actually cause the limited photovoltaic. So we're still finalizing a publication on this, so hopefully this can be released pretty soon. All right, so I'm sorry for taking too much time, but I'll try to finish in the next 3 minutes. So we'd like to switch gear with this last few slides. So in the beginning, I'll talk more on the materials development, but here in the last few slides, I like to focus more on how we translate from the materials that we have to the device, right, to large area devices. So if you look at the situations in the field, is that lots of reports of devices actually have a very small active area, less than 1 centimeter. Only a little bit, only a handful of them all demonstrated active area that is larger than 1 centimeter square. So at SGB, we have this efforts where we try to increase the area from 1 centimeter to 50 to 200 to even meter square modules. So in our group, we participated initially with PECDEMO. So this is a European project where we take a look at the initial part of the scale up. But my colleague, Sonia Kalnan, for example, at PVCOB now coordinate another European project called PECSYS, who is looking at this meter square module. So I'm going to share to you just a little bit on this early scale up. So in PECDEMO, the problem that we have, we can already see within this early area increase. So for example, if you look at the materials that is photoelectrodes that is small, right, a lot smaller than 1 centimeter square, we can get efficiency of about 6% in this particular case. But as soon as we increase it to 50 square centimeter, we decrease the solar to hydrogen efficiency by a factor of 3. And we found out that this is not a material problem. So we spent so much time trying to improve the materials, but actually it turns out that this is due to improper electrochemical engineering. So how we design the device, the reactor itself, it actually matters a lot, and that it can decrease the efficiency by a factor of 3. So the efforts in my group, we try to use simulation, multiphysics simulations, in order to identify the loss mechanism. So this study over here, for example, is a collaboration with EPFL in Switzerland, where we just model now the different losses, be it from the ohmic losses in the substrate, in the electrolyte, as well as pH gradient. So this is mass transport issue in the electrolyte as a function of scale. And as you can see, indeed, the voltage loss increases quite significantly as we increase the scale of the electrode. One example here is that the pH gradient. So the color map here is the pH of the solution. It starts at 7, but due to reaction, it goes to really alkaline solution close to the cathode. What we can do is that we can try to increase the flow rate, so at least the supply of the new electrolyte, in order to suppress this pH gradient. So this simulation is pretty useful in trying to decrease the amount of experiments, because you cannot actually do a lot of all the experiments that you want with designing different devices. So it's very useful in trying to do that. But the other important thing is to validate the simulation. So this we also do in our group. For example, this is a work by Kesuke, a postdoc in my lab, where we look at the pH measurement, pH and the electrolyte in situ using fluorescence technique. So in the video that you see right now, you see that as we start water splitting, we change the pH of the electrolyte to become more acidic. Blue means more acidic, and red means more alkaline. So we change the pH of the electrolyte throughout the bulk of the electrolyte when we do it in unbuffered electrolyte. Now, if we actually do it in a phosphate buffer, we see that we limit this change of pH only to a very small region close to the electrode, right? So this very useful visualizations is actually helping us in developing better simulations and try to validate the simulations, right? Another thing that we can actually detect as well is the oxygen concentration. So this is the simulation, and we compare it with our measurements, and we see that it qualitatively matches what we actually have from the simulation. Finally, we also have other experimental validation technique. We have this particle image velocimetry, where we can actually measure experimentally the velocity of the liquid electrolyte inside the system, so that we can detect convection like this. We also can monitor bubbles using shadowgraphy. So we track it, we determine the sizes, distribution, and the velocities. And all of these are part of the reason why I'm sharing with you is this is part of this Helmholtz Energy Materials Foundry, specifically Solar Fuels Devices Facility, which is like our synchrotron is an open access or like an open user facility. So it's open for users from anywhere, basically. So if they have interesting problems that they would like to tackle with our tools, they can actually just contact us. Okay, I take already too much of your time, so I try to end here with a few take-home messages. First of all, solar energy, I hope we see that it's the way to go. We just need to store it, and solar fuels is one possibility. And we need to have a breakthrough in materials development if we want to push this photoelectrochemical water splitting further. And progress in bismuth vanadate has actually been a key example, but now we need to address this band gap issue by either decreasing the band gap with dopant incorporation, for example, like sulfur, or we develop other novel oxides. And finally, I showed you our initial efforts in scale up. It is challenging, but we believe it's important to develop feeling for this, and we cannot wait until the industry is actually being interested in it. So because no industry probably would be attracted by technology that is only demonstrated in very small laboratory scale. So unfortunately, we as a scientist also need to engage our activities as well in that type of efforts. And I showed you that in our group, we combine modeling and validation in order to determine the limitations in these devices. With that, I'd like to acknowledge my group members, the Institute for Solar Fuels, the collaborators, as well as the funding agency. And of course, thank you all for your very, very kind attention. I'm sorry again for the technical difficulties earlier.
Big thank you. Thank you very much, Dr. Fatwa, for your delivery. Very great presentation. Yeah, this is insightful for us, especially for me, because many inline interesting research with our group in here. Okay, Dr. Fatwa, please hold, and maybe I will give a chance to participant, to all the audience. Please, if you have any question, you can chat directly in our chat box. Write down in the chat box, and then address it to who? To Dr. Bamba or Dr. Fatwa. Okay, meanwhile we waiting, I have many questions actually for both of you. Okay, before we going for Dr. Fatwa, I have one question from Prof. Anna Zulfia for Dr. Bambang first. Okay, Pak Bambang, this is the question from Prof. Anna. So my question addressed to Bapak Bambang, the presentation is interesting and informative. I have a question. You produce lithium-ion battery, namely merah putih, lithium-ion battery. So what is the performance of this battery, such as the specific capacity or energy density in a module? Is it possible for merah putih battery to assembly in electric vehicle? I think next year, the Indonesian government will build the lithium battery industry. What do you think about the mineral resource support in this factory? Pak Bambang, please, time is yours.
Okay. My battery specific capacity is around 160 milliampere hour per gram, or the energy density around 640 watt-hour per kilogram. But the problem is my lithium battery is not good stable. Yeah. Because there is the influence of cobalt in this.
Okay, the influence of cobalt.
Cobalt, yeah. Cobalt can change the other metal to have a double valence. Yeah, and then
I see.
And then become the lithium-ion battery increase the specific capacity around 260 milliampere hour per gram, and we can have the capacity of battery around 5,000 milliampere hour, but it's not stable. This is the problem. The second is for applicable for the application in electric vehicle. Yeah. My active material, lithium manganese phosphate, is good for the fast charging. Yeah. In the application of fast charging battery. Yeah. I think this the merah lithium battery. Yeah. Merah this can be application in electric vehicle. And the third equation is about the extract mining material, and we do with my group in the consortium the prepare of the pilot plan to make a pilot plan for the extract mining material. Yeah, this is more than X material for raw material of lithium battery. Yeah, okay.
Okay, thank you for the reply, Dr. Bambang. Please be hold. I will go to Dr. Fatwa. There is some question for you, Dr. Fatwa. This is from Dr. Gerald. How much is the hydrogen can be produced by the PEC water splitting, and how its efficiency comparison to other method?
Okay,
it's very technical.
The problem of how much, thank you very much for the question, first of all. So how much hydrogen can be produced, that depends on, of course, the area that you actually used, right, in order to capture the energy. Its efficiency, the highest efficiency that is reported for direct photoelectrochemical water splitting is now in the order of 19%, and that's using a higher quality materials than complex metal oxide. So that's 3/5. So with complex metal oxide, the highest is at about 8%, but with 3/5 semiconductor, with silicon, it's at about I think the highest is about 15%, and with 3/5 semiconductors, the highest that's been reported is about 19%. And that is actually already pretty high. The competitor, if we want to go for the green way, like the renewable way, is actually, we can already do it like right now by combining two devices. One is photovoltaics and two is electrolyzer. So we can combine commercial photovoltaics and commercial electrolyzers and do water splitting. The highest that is reported, this is also based on high performing PV, 3/5 semiconductors, and really 3 different PEM electrolyzers, I think 3 or 2 stacks of PEM electrolyzers. The highest that they can achieve, the indirect PV electrolyzer, is in the order of 30%. So it's still higher than the 19% that we demonstrated with direct water splitting, but it's not that far. And the US DOE has already, they have released several targets over the years, and unfortunately, the target keeps on increasing and increasing. And we the value that we target is in the order of 20 to 25%. And hopefully, with the development of materials and further, we can actually push the direct photoelectrochemical water splitting towards that efficiency. And in order to give you a perspective, of how much area is needed in order to generate the hydrogen that you need. So I have is a back of the envelope calculations of a number. If you want to generate 1 kilogram of hydrogen in an 8-hour day, assuming that we have only sunlight for 8 hours, right? So unfortunately, in this northern hemisphere, we have very short sunlight period, right? So assuming that we can only take sunlight for 8 hours a day, and you want to produce 1 kilogram of hydrogen, you need an area of about 41 meters square. So that's like what, 6 by 6 meter, right? So that's like the rooftop of a house. You can actually theoretically think of it as a way to capture that energy, and it's enough to generate 1 kilogram of hydrogen using a 10% system. So now if we increase that efficiency, of course, this area requirements become smaller. And that is the kind of numbers that we need, and how important, or what is how much is 1 kilogram of hydrogen? So 1 kilogram of hydrogen can generate you about 30 kilowatt hours, if I'm not mistaken, and that is in the same order as the daily use of average daily household in Germany, at least. I'm not sure how it is in Indonesia, but here I think we use an annual energy of a family household of about 3,500 kilowatt hours. So per day, it's about tens of kilowatts hour. So yeah, so it's not impossible, so it's feasible, and that is sort of the. I hope that answers a little bit the question, and also the efficiency comparison. Of course, we cannot compare it very easily with the way we produce hydrogen right now. The way that we do it with methane cracking. So we take hydrogen out of methane, for example, steam reforming. Yes. That's a different technique altogether, and efficiency comparison over there doesn't really make too much sense.
On hydrogen.
Yeah.
Okay, so this is the following question. I think you, instead of comparing from your answer, I think you suggest we just make a hybrid, right? Like previously you stated, using the PV and then PMFC or PEM electrolyzer, right? In order to make a good way of hydrogen production.
Yeah, that is the way that we can already do right now. Yes.
Okay, nice. Okay, okay. I will go back to you later, Dr. Fatwa. I have to go to Dr. Bambang again. So, Pak Bambang, this is the question from Prof. Dani Gustaman from Batan. If compare your battery to the battery developed by UNS Solo, yeah. So what is the difference? Please, Pak Bambang.
UNS developed the NCA battery and MNC battery or NMC battery. Yeah, this is different is like the visual incomparable in the slide. We have we develop about the lithium metal phosphate, and the other is around nickel, cobalt, alumina, or nickel, cobalt, nickel, mangan, cobalt. This is different. This is different on the lifespan and safety. This very other results for this. Yeah. Okay.
Okay. I hope it's answered the question, Dr. Prof. Dani. I have to go back to Dr. Fatwa. This is another question from Dr. Nugraha. Yes, Dr. Nugraha have the research interest on the DFT computational like that one. Therefore, the question I think relevant with your material development regarding the So the question is, there have been a lot of theoretical work on the potential of 2D van der Waals heterostructure for photocatalytic water splitting. For instance, MOS2ZNO heterostructure. What is this? I'm not so familiar with the symbol VDW. And TMD
underwall of these materials, although we don't really work on these materials in our institute. And of course, they have quite a bit of a promise, right? And the interesting thing I think about them is that the activity seems to, especially for molysulfide, the activity seems to be determined by the edge side. So if you have because this is a plate, how do you say? Because of the flat nature, or like the layer by layer nature of this material, the edge of this, the basal and the edge, right? The edge side seems to be the most active sides of the material. So a lot of activities in the field have been directed towards increasing the coverage for the edge sides and decreasing the amount of basal plane. So we don't ourselves, we have not really done much on this. I think they could be interesting, but a lot of them are still much in an early development state. Some of them are more interesting than others. For example, like the combination with zinc oxide, I think is probably not very attractive because it's known to be highly unstable. It's hard to actually stabilize, and the band gap is also really large. But the other combinations or other new materials that comes within this class, I think could be pretty interesting. For example, MXenes, I think people have actually looked into this as well for carbon dioxide reduction, but it's still too early to know whether they're good for industrial scale. So I hope that answers the question.
Yes. Okay. Thank you, Dr. Fatwa. I think I have the following question. Yeah, regarding the Dr. Nugraha question. So from your slide, I saw that in your group mainly focusing on the bismuth vanadet, right? Bismuth base. So, but I think I didn't see the doping for the bismuth vanadet. Your research, your group research, mostly on the compositing, like with the tungsten oxide base or other. Why you just focusing on the compositing or mixing the bismuth vanadet?
Yeah, thank you. So now we did do doping. So we did. I think maybe I didn't show it as much, but this presentations. But yeah, we tried to composite it with sulfur, right, with higher concentration. But with doping, we tried using also slower concentration, and with molybdenum or tungsten, or even dope it with hydrogen, and that's in the relatively 10 to the 18, 10 to the 19 centimeter minus 3 concentration, and that does help for bismuth vanadate, but it can only help until a certain point. And people, I think all of the high performing bismuth vanadate that is reported have to combine a few of this strategy. Doping is one of them, and then combine it with the structuring or introducing the internal gradient. But we do doping, yes.
Okay, it's interesting, yeah, because previously I did this material development, but for another application, for the electrolyte for SOFC, solid oxide fuel cell.
Okay.
For the ionic conductive material, yeah, but it's similar, yeah. Yeah,
is it good?
It can perform at the very low temperature, yeah, but the problem, the electrode, we cannot find the proper electrode. The electrolyte good, the electrode we cannot find yet.
Okay.
I think it's very many common that I can discuss with you actually. Okay, we have to go to Dr. Bambang again, and then after that we go back to you. Okay, Dr. Bambang. Yeah, there are several questions actually for you, but if there is still not yet any question from the floor, from the participant, yeah, I can give you many questions actually.
Yeah.
Okay, Dr. Bambang, what do you think about the fast charging status now in our country, or maybe in the global, in the world, the fast charging status, and how fast the charging is for the latest technology one? For the charging, for instance, for the electric vehicle, how fast it is now?
Yeah. How fast is now?
Yeah.
Yeah. type of lithium battery can fast charge by on 10 C capacity, 10 capacity. But for the requirement for the fast charging battery, everyone wants the active material of cathode can charge from 20 C. 20 C. Yes.
20 C.
But the
Okay.
status, 20 C. Yeah. But the status of the station for the fast charging or stationary charging, the charging status is not so high, maybe around 5 C, because the more the station very careful for the fast charging, because the lithium battery can more fast the break of the boom.
Yes, explode.
Explode.
Yeah, I think that's the problem due to the still in the liquid electrolyte, right?
Yeah. Therefore, this in the slide is more than factor of the fast charging, and the more states or more country develop the swap battery swap. Yes.
Okay. So the replacement, not charging.
Yeah, and the charging and the other plates, and I take the new battery in the
replacement.
Replacement.
Yeah, I think that's more visible. Okay, I did go back to Dr. Fatwa. Dr. Fatwa, this is a little bit about policy, not so technical. But I still many technical questions actually for you. Actually, still many. Okay, we have many time in here. We can finish until up to 1. No. 12:40.
Okay.
Dr. Fatwa, what your opinion about the big potential? We know that the big potential of solar energy should be huge for our country, for Indonesia, I mean, as the tropical and also in the equator line. So how did you see or suggest this solar energy, or specifically the water splitting, can be adopted for our government? Please.
So
now you ask the policy.
This is definitely outside of my expertise, and I don't know if I can actually offer. And I don't know how far this recording will go, right? So I don't really want to say something that it's going to shoot me back, right? But I'll share a little bit of my opinion, right?
Okay.
So as you said, the potential is of course pretty high, right? Solar energy, we don't have, although we're in the equatorials, we have a lot of sunshine, but it's not as high as in the desert, of course, desert area, but still it's pretty high. So if you can think that Denmark or Germany or Sweden or Norway can actually tap on this solar energy with the amount of sunlight that we and they have, right, in Germany, and also they in the Scandinavian countries have, I don't see why this is not a possibility or in Indonesia, right? We need to actually tackle that, even take care of that, use that even more. And the interesting thing about that is also it's very how do you say, it's suitable for our geographical conditions that we are actually distributed over many islands, right? And maybe the problem with one of the problem with energy is distribution, right? So we actually can, if when you actually have like a centralized production of energy, you then need to distribute it to various places, and that's probably fine up to a certain point. And if you go across the sea, for example, and whatnot, that becomes more challenging. And this is where I think solar energy or other types of renewable energy that we have, like the tidal waves, the wind, or whatever, can actually offer its advantage for addressing our challenge, and as countries with thousands of islands. So this is something that we needs to go for, a decentralized way of producing energy that it can tackle various places. And in terms of water splitting, yes, it's of course, as a researcher in that field, I'm passionate about it, and I'd like to see it actually being developed more and used. But at this point, unfortunately, I think this is not the. If you want to have like a shorter term policy, this is not something that we need to focus on yet, because even it's still being developed in research. We can go for photovoltaics electrolyzers if you want to store the energy, but I would say even with the basic solar, just the penetrations of solar cell in our country, as far as I know, is not high enough. We do have quite ambitious target, as I see, but we're still behind that target. And if we fulfill that, and not only, especially focusing on regions where otherwise grid cannot reach, I think that's the biggest potential that we have, and something that we need to focus on. But I agree, there are many focus that we need to. There are many fields, or there are many aspects that the government need to look at, and I do hope that this is going to be one of them. I don't know. I try to answer it, try to be politically correct in giving a policy. That is outside of my expertise. So that's my.
Yeah, that's very good. Yeah, diplomatically acceptable.
Thank you.
Now it's a little bit technical, Dr. Patwa.
Okay.
A little bit technical. So what do you think about the hematite base for the PEC? Because in our country, in Indonesia, we have many bauxite. Yeah. So what your opinion about it?
Yeah. So yeah, hematite is, of course, it's one of the, when it came out, it's one of the dream material, right? Because it's actually basically iron oxide, right? Fe2O3, and it's rust. So you actually have it everywhere, and it's highly stable. So, so I think somebody asked about stability in the chat. I can actually come to that also right now. That hematite has shown actually one of the most stable materials that we know. So we took a 1,000-hour test, not us, but our colleague in Porto, in one of our PECDEMO consortium partner, took hematite, tested for 1,000 hours. That's several months of performance measurements. There's really zero decay or zero degradations on the material. So it's really, really stable. Bismuth vanadate, there is not for us, but also there are other groups that showed that it also can be stabilized up to 1,000 hours. And that is, of course, the goal, right, to go even further. Now, going back to hematite, the problem with hematite, it's the band gap is good, band position is okay, stability is really good. The problem for about 20 years or so have been attributed to the poor charge transport property. So the hole or the diffusion, the carrier diffusion length has been mentioned to be very short. And therefore, people have done a lot of nanostructuring, and they can achieve now already the highest one. I think it's like 6 milliamps. So that's already half of the theoretical maximum. But recently, we're still working on a publication on that one. So we are collaborating with our colleagues at Technion, where we looked at the
Technion Israel.
Yeah, fundamental problem of hematite, and one of the main issue right now that we found is not only on this carrier diffusion, but it's actually better than expected. The carrier diffusion is better than expected, but the problem is in the photo generation process itself. So there's a how do you say it? So it has a lot of absorption, but some of those absorption do not contribute to actually current. So we're still finalizing this and see if this is actually the case. But there is a hint that this could be a problem. And if that is indeed the case, the theoretical limit of hematite is no longer of what we can achieve with the band gap, right? So we can. There is some problem with that. We try to see it as well in the other materials if this is a general issue, but I'm afraid the verdict is still out, so I don't know whether that will still be. But yeah, otherwise it's a nice material. Yeah, but unfortunately it doesn't tick all the boxes. Basically, it doesn't tick all the.
I see. Thank you for a very insightful answer. I need to go back to Dr. Bambang.
Yeah.
Okay, Dr. Bambang, another question. So, what do you think? So, what we should pay attention more on the battery safety development, like on the BMS? What the technical that we have to overcome in order to make the battery is more safety? Please.
More safety.
Yes.
This is about the control
BMS.
of state of charge. Yeah.
Correct.
State of this small number. No, this development of balancing.
Okay.
This is charge balancing or discharge balancing. This. Yeah. No. And the new development is the control of the battery cell. Yeah, this we can one by one the BMS can see the battery is good work of no. Is the new development on the PMS. Maybe this is so that the battery can assure there is a safety on can ensure this is good work in the application like this.
Okay, thank you for the answer, Dr. Bambang. Maybe this is the last question for you because we have a limited time. This is not so technical, Dr. Bambang. This is your opinion about a little bit policy. Yeah. So what is your opinion about the big company, as you know, the Tesla, Hyundai? They want to invest to our country, right? For the battery industry. So what do your opinion, Pak? Please.
Your opinion. This is maybe good. And this is the big country is look on me of Hyundai, Toyota, and Tesla, Lamborghini, and Ferrari.
Okay.
Lamborghini and Ferrari. We make a plan to collaboration with Ferrari to make
nice.
to make a electric vehicle like national vehicle with the type from Ferrari, and we want the battery from me because my battery is this different, especially different from the other battery, and we have the lifespan, we have the safety, and so on. Maybe we can the parable is the diameter parable.
Okay.
Comparable diameter comparable is maybe very good in the next future. I say.
Thank you, Dr. Bambang. Okay, I need go back to Dr. Fatwa, but this is not question, Dr. Fatwa. I need your closing statement. We will finish our session. Please give your closing statement. Please.
I don't know. Yeah. So my closing statement would be thank you very much for this nice and engaging discussion. And yeah, so I'm pretty happy with the way discussions goes and looking at the nice initiatives of this webinars. I think the pandemic actually has one of the good things that it has actually brought us is actually the nearness, right? So I've actually engaged with a lot more webinars this year that I could if we don't have pandemic, right? So one of the nice things is that the scientific and also technological delivery have become easier or more accessible to everyone. And I just hope that this will go forward further, right? In the spirit of collaborations and also openness of science and technology, we can continue to do that even beyond this pandemic period, right? And in terms of energy, and I think one of the things that if I look at the programs of this conference or the symposium, is that the final statement that I will say is that we can actually see how important material is in every aspects of our life, right? So we already see just in this session, we have the different applications in energy field, battery, catalytic or chemical transformations in my talk, but there are other topics that have already been discussed this morning. Other applications, right? Superconductivity, ferroelectricity, and further on, right? Even going biomaterials and stuff. And I think this shows the richness of material science, and we need to further improve our collaborations, I think, within the field. With that, I thank you again, Dr. Denny, and also everyone and the organizers, and also if there are any further questions or discussions to me, please feel free to contact me or shoot me an email.
For sure, many. Thank you, Dr. Fatwa. Thank you, Dr. Bambang. And also thank you for previous our speaker, Professor Kawai and then Professor Andika. We have today learned a lot from all of them, from the ferroelectric material for the electronic material application, Professor Andika about the superconductor, Dr. Bambang about the battery, and Dr. Fatwa about the PEC water splitting hydrogen production. Thank you very much for your delivery, very good presentation. And I have to go back. I have to return this presentation to the MC or to Dr. Panono. Panono, please. Or Mbak Wita.
Okay,
so thank you.
We will go to the photo session.
Oh yeah, photo session. Please turn on your video photo session before we finish.
Keynote, please. Maybe. Okay.
Yes, we already took the picture.
Finish?
Finish?
Okay.
Thank you.
Thank you again. So we will come back at the 13th at the 1 p.m. sharply. Thank you very much for your all of attention. That's all from me. Apologize for any shortcoming. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi.
Nanti jangan bosan-bosan ya kalau kami email Pak ya. Banyak sekali inline-nya riset tentang foto PEC yang kami lakukan juga Pak di sini.
Iya, siap Kang Denny. Tahun lalu kan kita ketemu di itu ya, di
Iya.
CKD ya? Ya, siap.
Iya, ini juga kalau nggak pandemik sebetulnya saya mau apply juga ke sana, cuman ya gara-gara ini kami jadi pending dulu.
Iya.
Banyak banget nih kami mau belajar ke Helmholtz nih ke Berlin.
Aduh, mudah-mudahan bisa. Iya, mudah-mudahan segera nih vaksinnya bisa dirilis. Jadi kita bisa.
Amin ya.
Pak,
Berarti jam berapa sekarang di sana? Jam 6 sekarang?
Ya, jam 7:04 ya.
7:04. Oke.
Iya.
Gimana Pak Fatwa?
Enggak, sama siapa namanya? Waktu itu Sigit. Masih ini sama Sigit? Enggak.
Sigit
ya, sama Jovan.
Makasih lah. Bukan saudaranya Mas Fatwa, masih kontak lah.
Ya, loh.
Canda.
Iya.
Itu juga ada ya yang di Komplek Dikbud ya, saudaranya Mas Fatwa ya, yang di Jakarta Barat di Tomang itu ya. Aduh, siapa namanya? Saya lupa. Orangnya tinggi-tinggi juga. Udah lama sekali aku nggak ketemu sama dia.
Halo.
Ayahnya dosen hukum tapi udah pensiun.
Siapa ya?
Saya lihat soalnya di Facebook sama-sama friend kita. Dengan orang yang sama. Bilang, ya ini lihat ini kayaknya Pak Hifni bapaknya. Pak Hifni pernah cerita ini, saya ada saudara di Jerman gini gitu ya. Oh gitu.
Siapa ya?
Ini Pak Fatwa.
Saya
Oke, nggak apa-apa.
Saya nggak ingat, tadi sampai saya cari. Pokoknya yang
berawal dari cita dan asa untuk membangun negeri, memberikan segenap rasa dan tenaga untuk menghasilkan pemikiran terbaik bagi negeri tercinta. Kami ada untuk Indonesia. Mewujudkan diri sebagai Lembaga Ilmu Pengetahuan Indonesia yang andal, profesional, inovatif dan berintegritas dalam pelayanan untuk mewujudkan visi Presiden dan Wakil Presiden. Indonesia Maju yang berdaulat, mandiri, dan berkepribadian, berlandaskan gotong royong. LIPI memiliki berbagai pusat penelitian tersebar di seluruh Indonesia yang berada di bawah Kepala LIPI, Deputi Ilmu Pengetahuan Hayati, Deputi Ilmu Pengetahuan Kebumian, Deputi Ilmu Pengetahuan Teknik, Deputi Ilmu Pengetahuan Sosial dan Kemanusiaan, Deputi Jasa Ilmiah dan SDM Pendukung Iptek di bawah Sekretariat Utama LIPI. LIPI berperan dalam proses penyusunan dan kelahiran berbagai regulasi dan kebijakan pemerintah terkait aspek ekonomi, politik, sosial, dan budaya. Selain itu, LIPI juga mengelola data dan timbangan ilmiah dalam rangka konservasi keanekaragaman hayati. Menerbitkan tanda pengenal unik publikasi ilmiah terbitan berkala, membuat repositori ilmiah skala nasional, dan memiliki kewenangan sebagai pembina Jabatan Fungsional Peneliti Nasional, serta melaksanakan proses pengukuhan profesor riset di Indonesia. Kini, LIPI juga mendukung percepatan penanganan COVID-19, baik melalui riset berupa kajian maupun produk, maupun pengembangan SDM melalui program Indonesia Memanggil. Untuk mendukung riset, LIPI memiliki 5 kebun raya sebagai pusat konservasi flora ex situ. 2 museum yang memiliki koleksi flora, fauna, dan kesejarahan alam Indonesia, Indonesia Culture Collection yang menyimpan koleksi mikroorganisme terbesar di Indonesia, infrastruktur riset strategis, dan beberapa pusat berskala internasional, yaitu Asia Pacific Center for Eco-Hydrology atau APCE. LIPI telah menghasilkan hasil riset yang berkualitas dan bermanfaat bagi masyarakat, meliputi keanekaragaman hayati, lingkungan dan maritim, ketahanan pangan, pertanian, dan peternakan, kesehatan dan farmasi, material maju, energi, teknologi, informasi dan komunikasi, pertahanan dan keamanan, dinamika sosial, kemanusiaan dan kebudayaan, kebencanaan, inovasi teknologi dan pendayagunaan iptek, pelayanan, pengujian dan pembinaan ilmiah, serta peningkatan kualitas SDM iptek. Kerjasama keilmuan LIPI dalam negeri meliputi kerjasama penelitian, lisensi teknologi, pengembangan, aplikasi dan komersialisasi hasil penelitian, kerjasama non-penelitian, dan konsultasi kepakaran LIPI. Sedangkan kerjasama luar negeri, LIPI melakukan joint research, workshop, pertukaran peneliti dan beasiswa mancanegara, selain aktif menjadi anggota dan focal point di berbagai organisasi internasional. Melalui kolaborasi bersinergi, menghasilkan riset yang berkualitas, LIPI terus memberikan manfaat nyata, kontribusi berarti, dan turut mewujudkan cita dan asa membangun negeri kita tercinta, Indonesia. Indonesia merupakan negara yang kaya akan sumber daya alam. Salah satu aset yang kita miliki adalah kekayaan mineral. Pusat Penelitian Metalurgi dan Material LIPI hadir untuk mewujudkan kemandirian industri melalui penelitian berbasis sumber daya mineral lokal. Komitmen tersebut tidak pernah berubah sejak berdiri pada tahun 1965 yang disertai berbagai perubahan nama dan struktur organisasi hingga saat ini. Pusat Penelitian Metalurgi dan Material LIPI memiliki 4 kelompok penelitian yang berfokus pada pengembangan baja unggul nasional berbasis biji laterit. Penelitian ini bertujuan menopang kemandirian industri baja nasional sehingga mampu berkompetisi di pasar baja unggul global. Pengembangan produksi baja unggul ini memanfaatkan mineral laterit yang banyak terkandung di Indonesia. Pengembangan material untuk implan medis dan alat medis. Penelitian ini berlandaskan atas kebutuhan akan material implan yang sangat besar di Indonesia. Di sisi lain, selama ini implan disuplai oleh produk luar negeri yang relatif mahal. Penelitian ini hadir untuk menjawab tantangan terhadap ketersediaan produk implan generik yang ekonomis bagi penduduk Indonesia. Pengembangan teknologi pengolahan dan peningkatan nilai tambah mineral nikel, kasiterit, dan magnesium karbonat. Salah satu penelitian dalam kelompok ini berfokus pada riset mineral dolomit yang dapat dijadikan sebagai produk magnesium karbonat untuk aplikasi pada industri farmasi dan kertas. Riset lainnya yaitu pengolahan mineral kasiterit untuk senyawa kimia timah. Pengembangan material untuk industri energi. Penelitian ini dilakukan untuk mencari material
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon. Good afternoon.
Good afternoon.
Warahmatullahi wabarakatuh.
Can you hear my voice? Can you hear my voice?
Yes.
Yes.
Okay.
Okay. Should we start now? We have a program from 1 o'clock. According to the program that I have, We have 8 presenters that will be deliver their presentation, and the first presentation is Dr. Nafizan. Is
Yes,
Dr. Nafizan here?
It will be my presentation, Mr. Agu.
The presentation, Mr. Aga. Okay, yes. Mr. Aga, can you start your presentation now? Before that, I will have some point that I have to mention here, that in this session, the presenter has 2 options to deliver the presentation. The first one is by video presentation, and the second one is by the live presentation. I would like to ask Mr. Aga, which one would you like to deliver your presentation?
I have already sent my video presentation, and if you please share the video.
And yeah, each presentation has 15 minutes, 10 minutes for deliver the presentation, and 5 minutes to Q&A session. Okay, Mr. Aga?
Yes,
okay.
Yes, please.
Your presentation.
Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. Thank you for the opportunity to present our research. First of all, let me introduce myself. My name is Agridova, and I come from Research Center for Metallurgy and Materials, Indonesian Institute of Sciences. And today I would like to present our paper titled Performance of Nanocomposites TiO2/RgO as Compact Layer in Zinc Chloride Modified Perovskite Solar Cell. The outline of my presentation will be first the introduction, continued by materials and method, and then followed by results and discussion, and finally the conclusions. First, for the introduction, perovskite materials is originally found by German mineralogist Gustav Rose in 1839 from calcium titanate. Basically, the crystal structure is in the form of AbO3, and nowadays it is used in the form of halide perovskite to be applied in photovoltaic applications. The most commonly used halide perovskite is in the form of methyl ammonia lead halide. Perovskite solar cell in itself has been in development since 2009, where it reached its first efficiency of 3.8% and is still currently developed with many various parameters and variables explored, and has reached 20.9% in 2018. The significant increase in efficiency is due to the researchers' breakthrough in the elucidation of the principles underlying in the development to overcome problems such as material instability and quality of the perovskite layer. Now, titania has been used widely as an electron transport layer in perovskite solar cells because of its low cost and environmentally friendly. However, TiO2 has a drawback of charge recombination, which could reduce the efficiency of the device. Because of that, many efforts have been performed by many investigators to overcome this problem, and some example will be given in the next slide. In this research, our team also contributed to the many various parameters and variables engineering in the developing of perovskite solar cells. Our team used reduced graphene oxide coated TiO2 nanoparticles combined with perovskite layer modification. There have been many researchers in the field of perovskite solar cell. For example, Han et al. In 2015 have reported that the use of reduced graphene nanocomposite and mesoporous TiO2 in the perovskite solar cell is able to reduce charge recombination at ground boundaries, thus increasing the load collection and increasing significant efficiency from the perovskite solar cells. Jin et al. In 2017 has also reported that by performing a partial substitution of the perovskite layer, in this case lead iodide is partially substituted with zinc chloride, is able to improve the nature of electron transport so that it can also increase the efficiency of the perovskite solar cell. It can be understood that the existence of the perovskite layer plays a very important role in the electron transport process, which also affects the overall device efficiency. And the purpose of this research is now to see how it is possible for the reduced graphene oxide coated TiO2 nanoparticles combined with perovskite layer modification will increase the electron transport to increase the efficiency of the perovskite solar cells. Next is the materials and method. Firstly is the preparation of TiO2/RGO nanocomposite. In short, a 2 cm by 2 cm conductive electrode made of fluorine-doped tin oxide glass was prepared. The semiconductor layer was prepared by adding an amount of methanol into TiO2 nanoparticles along with 2 drops of tritron X100 and mixed it to obtain a homogeneous solution phase. The solution was then spin-coated to obtain the first layer of semiconductor. Nanocomposite TiO2 and RGO was then prepared by using variation composition of 0.3125, 0.625, and 0.9375 moles of TiO2 dissolved and ultrasonicated in variation composition of 0.4, 0.5, and 0.6 volume percent of RGO. This layer was then dried at 450 degrees Celsius for 30 minutes before being ready for the next step and characterizations. Next, the semiconductor layer TiO2 and RGO prepared from the previous step was further spin-coated with chloride-modified perovskite. This perovskite was prepared by mixing methyl ammonium iodide, lead chloride, and zinc chloride in dimethyl sulfoxide under a magnetic stirrer for 2 hours. The specimen was then dried and calcined in a muffle furnace at 90 degrees Celsius for 1 hour. The whole transport layer was further deposited on top of the perovskite layer, which consists of spiroometate followed by spatter coat of gold metal electrode. The perovskite device cell was then ready for performance characterization. Now we go to the results and discussion. For the morphological structure, figure number 1 is the secondary electron image of pure TiO2 P25 degussa, and the second image is the compact layer at various TiO2 and RGO concentrations. In the figure number 1, the morphology of pure TiO2 P25 degussa is shown having a globular shape with an average particle size of about 50 nanometers. And we can see in figure 2, A, B, and C, the morphology of 0.3125 molar TiO2 coated with 0.4%, 0.5%, and 0.6% volume of RGO. In figure 2, D, E, and F, the morphology of 0.625 molar of TiO2, and in figure 2, G, H, and I, the morphology of 0.9375 molar TiO2. In all morphological structures shown, the particles are almost evenly distributed and coated by a thin layer of RGO with relatively uniform in size and shape. This uniform distribution will affect the electron transport characteristic within the layer. For the X-ray diffraction, in all compositions, the carbon from RGO pattern dominates the peaks except at 0.3125 molar of TiO2 and 0.4% volume of the RGO. It seems that at this composition, the RGO layer does not homogeneously coat the TiO2 layer, and thus only small portion of the RGO phase that can be detected in the X-ray diffraction pattern. For the TiO2 crystal structure, 2 coexisting phases are detected in the diffraction patterns, namely anatase and rutile. In our previous work, these 2 phases have been also reported to coexist. The performance characteristic of the perovskite solar cell devices fabricated using TiO2 RGO variation concentrations were measured through an IV curve generated by a semiconductor parameter analyzer at room temperature. As seen in the figure, the filled circles are the experimental data, whereas the solid line is the fitted results. The performance of the device is based on power conversion efficiency calculated based on this curve, and the result is shown in the table. Based on the characteristic given in this table, the maximum efficiency is found to be 3.42% obtained at the ETL fabricated using 0.3125 molar of TiO2 and 0.5 volume percent of the RGO. The main reason of this small value is expected to be caused by the environmental condition during the fabrication. In this instance, the perovskite solar cell device was fabricated under an ambient condition with no control over humidity nor the pressure. Some other researchers have found that the formation of a perovskite crystal in a perovskite solar cell is affected by the environmental condition, in which an environment proved to give the best performance rather than an ambient condition. Now we have finally reached the conclusion. The performance of TiO2 RGO nanocomposite used as a compact layer on perovskite solar cells has been examined. The morphology of TiO2 RGO deposited on FTO glass showed a homogeneous distribution proven by the secondary electron image, whereas the crystal structure examination showed the presence of RGO and mixed phase of anatase and rutile TiO2. The maximum efficiency of 3.42% was obtained from variation composition of 0.3125 molar of TiO2 and 0.5 volume percent of RgO. The efficiency is still low, possibly because the environmental effect during the fabrication. However, this obtained value is promising in terms of future development for TiO2 RgO-based perovskite solar cells. Now, this is the reference for our paper. And thank you for your attention. Assalamualaikum warahmatullahi wabarakatuh.
Good afternoon, ladies and gentlemen. At this time, I will present a topic research of superconducting material.
Maybe Mr. Hendrik? Mr. Hendrik?
Yes.
Mr. Hendrik, should we go to your presentation or we have to go to Q&A session?
I think for the Q&A session first, really dive into the testing of the stability itself. So we haven't really tested the performance in different times or day, but we only have tested it in one time and one condition only. So maybe that's one of the things that we are considering to do in the future.
Okay. Is that all? Okay. Mr. Gerald, do you have a response?
Hello, can you hear my voice?
Yeah.
Yes. Yeah. Okay. Thank you very much for your answer. I want to ask, how about it's still about the stability actually, because usually in the perovskite, after it contact with air, it will be really fast to be degraded. So in your case, I think you use Cl, not iodine, right? So maybe it's so more stable in the air. But so how about in your case? Is it readily degrade after? So you made it in the ambient temperature. So it's actually it's interesting if you can find the good method to make in ambient temperature.
Okay, thank you for the response. For the perovskite, in this case, we made the perovskite itself in the ambient temperature based on one of the previous researcher that already did in the ambient temperature. But I think in this case, the perovskite solar cell is not really stable. But and as you said before, that it degrades over time. So when we haven't really tried to measure the second performance after we tried it the first time, but I think it also contributes to the low performance that we achieve in the first try. So in my opinion, maybe if we try it the second time, maybe it will maybe become lower, or how is it going to be? We haven't tried it yet. Maybe in the future we will try to do the stability test. Thank you.
Okay, thank you.
Mr. Gerald, is that?
Can I still have another question?
Yeah. Okay. Just one question.
Okay.
Okay.
I just wonder, what's the color of your perovskite?
The color.
Is it
the color of the perovskite is golden brown, brownish golden brown. Golden. After
is it
still what?
Is it still golden brown after several time?
After several time, it's still golden brown, but we have coated it. The first layer that we dropped and calcine, it was golden brown. But after we put the spiral method and then the gold electrode, we don't really know how the color change after some time.
I see. Okay. Thank you very much.
Thank you. Mr. Aga, one question. Did you measure the thickness of the thin films?
No, not yet. We haven't really got the time to measure the thickness itself. But yeah, we haven't tried it yet.
Okay. Thank you for your presentation and your answer. Please give the applause to Mr. Aga.
Thank you.
And then we go to next presenter, Mr. Hendrik. Mr. Hendrik?
Yes.
Are you ready to deliver your presentation? Okay.
Okay.
You will presentation by video?
Yeah, right. Yes.
Okay. Please deliver your presentation. The time is yours.
Good afternoon, ladies and gentlemen. At this time, I will present a topic research of superconducting material. This research is facilitated by Indonesian Institute of Sciences and synergized by some researchers from superconducting material group and non-ferrous group. This research, entitled Development of Magnesium Diboride Superconductor with Nickel Dopant by in situ method. The outline which have been used in China. In addition, the medical equipment such as MRI have superconducting wire which can be used as coil because this equipment is very expensive and imported from Germany. So why magnesium diboride? With critical temperature 39 Kelvin by Nagamatsu, it can be enhanced microstructure morphology and electrical properties by dopant. It can substitute niobium titanium and niobium tin with relatively lower cost. Previous research is related with impurities, porosities, and lower critical temperature that is affected by dopant carbon base. Among others, it can use dopant silicon carbide and carbon nanotube, which can increase current density but decrease the critical temperature and increase porosity, which inhibits connectivity between particles. As a result, the scope of this research consists of synthesized magnesium diboride, dopant nickel with PIT method or powder in tube. Characterization use SEM, X-ray diffraction, cryogenic resistivity measurement. Next, the synthesis method have 4 samples with different temperature intervals like 700 and 800 degrees Celsius. So why nickel dopant? From previous research, Qian Chao 2012 and Chai et al. 2012 used nickel dopants that results in increasing superconductivity and decreasing porosity. The dopant nickels is abundant in Indonesia, especially located in the eastern of Indonesia. So why is stainless steel from the previous research, Vergos and Nelson 2007 utilized different type of stainless steel, copper, nickel, ferrous. And from their research, the optimized material are stainless steel and ferrous. So because of that, the materials doesn't react with magnesium diboride.
Okay, the next, let's go ahead to the result and discussion. Let's see for the figure, the XRD pattern of all samples has been analyzed using HiScore Plus, and pattern show the change in the XRD pattern as a function of sintering temperature and weight composition of nickel dope. And if we see the table, in all samples, the superconducting phase is formed, and the formation of an additional phase has occurred. The result is in accordance with the study by Zhao et al., who report the formation of an additional phase can be detected after a sintering temperature of 600 degrees Celsius. Okay, this is calculating of crystallite size using the Serre equation. Crystallite size will be affected the superconductivity properties, and the crystallite size this is increase on N3 samples around 400 Armstrong crystallite size respectively. And then this is next the diffractometer, namely magnesium nickel boron. This is the new compound, and due to diffusion of the nickel dopants. Okay, this is N3 samples. MgB2 superconductor phase as the dominant phase with 94.6%, and this is still the same. The new phase is detected. This is magnesium nickel boron. The for the A and B figure show the small and agglomerate grain of MgB2 compared to the other samples. For the figure C, show the porosity of MgB2 sample as a dark cavity, which can affect the mechanical properties of MgB2. And for the figure D, shows the agglomerate and grain in hexagonal and spherical shapes. Okay, this is EDX result. EDX is the mapping of samples, and that nickel typically distributed in all areas of the samples. And then magnesium oxide decrease at 700 degrees Celsius. The nickel is more dispersed and homogeneous than the others, with the distribution of this element. For the last characterization material, we using cryogenic resistivity measurement on metallurgical and material. Indonesian Institute of Science is the one of have this instrument, and this is the graph resistance versus temperature result for the sample MgB2 with Ne dopants. Let's look the graph. The TC onset value has a high value of 43 Kelvin in a sample with 10% nickel and sinter at 800 degrees Celsius. It shows that higher sinter temperature has a lowering effect on TC0 value, and the best result of superconductivity properties show the most differences of TC onset and TC0 on number 2 N2 sample with 10 addition of nickel. Okay, the last but not least conclusions. We conclude the effect of superconductor properties show significant differences of TC onset, in which TC0 value on N2 sample having 10% is 20 0.35 Kelvin. The differences of nickel addition and sintering temperature affect the microstructure include grain boundaries, particle size, the distribution of nickel and its oxide element. The X-ray diffraction analysis result show that the superconducting phase was successfully formed with the highest 94% in the sample with nickel dopant 10% and sinter temperature at 100 degrees Celsius. Okay, this is our reference to be cited, and thank you for your attention.
Hello.
Yes.
Hello.
Yes.
Okay.
Yes, sir.
Thank you, Mr. Hendrik and Mr. Satrio, for your presentation. We have not much time, and I will open one question for this presenter. Is there any question? If not, I will ask the presenters. Actually, did you? I will write the question. Actually, did you analyze the reason of the decrease of TC due to any dopant?
Okay.
Mr. Satrio? What is the reason? Or what is the...
Okay, I think I think we need to elaborate with the RRI value of the resistivity, because sometimes the TC decrease due to the impurities, and from the XRD pattern, we show that some impurities form in the superconducting material. I think it's likely due to the impurities.
Yeah. Some impurities, some particle maybe has effect to increase the TC, and some particle has effect to decrease the TC. What is the difference between that particles? Why what one particles make the TC increase, and why some particle make TC decrease?
Okay. We don't analyze the porosity. I think some characteristics like the porosity.
Good afternoon, ladies and gentlemen.
Hello? Hello?
Yes.
Yeah, okay. Okay. Okay, hello?
Yes. Okay.
Okay. Yeah, okay. Thank you for your answer. I will go to next presenter. Next presenter will be Mr. Lukman.
Yes, sir. I'm ready.
Lukman, are you ready?
With video.
You will go with video?
Yes.
Okay. Please start your presentation.
I'm Lukman Faris Nurdiansyah from Postgraduate Program of Mechanical Engineering Mercubuana University and Research Center for Physics LIPI Serpong. In this conference, I will present my research with title Magnetic Adsorption and Oxidation from Mill Scale for Textile Waste Water Treatment. This is the introduction of my research water pollution in Bengawan Solo watershed with textile wash at December 2019. The growth of textile factory, especially by throwing away to river, lake, and sea that polluted these water sources. When the polluted water bring into water sources, it needs complex treatment to clean it, and the dye is difficult to degradable naturally. This water wash contain chemical substances like dye, sodium silicate, sodium alginate, and salt. If the water is used, the human health is threatened. The increasing demand for metal and steel products increases mill-scale wash, metal wash. So the management of and processing of waste, especially textile and the metal steel industry, is an important theme from the perspective of environmental regulation. Mill scale is the wash of metal production. It contains high of oxide materials such as bauxite, hematite, and magnetite. Mill scale has characteristics such as high density magnetism and the ability of the attract a charged molecule particle through electrostatic field or hydrogen bond. Many metal oxide synthesis methods are applied to produce high-quality metal oxide powder which have controlled level of purity, size, and shape. The absorption is defined as the process which a material is concentrated on a solid surface in a liquid or gas environment. The absorption rate is influenced by the condition of temperature, pressure, concentration, surface area of the adsorbent, and the chemical condition of the adsorbate. Adsorption more specifically can be affected by the charge of the adsorption particle. Water purification is performed through filter method, adsorption, ultraviolet radiation, distillation, ion exchange, and biological treatment. The equipment and the material of my research is mill-scale powder, graphite, textile dye, aqua dash, beaker glass measuring cylinder, high temperature furnace, 400 mesh size sieve, electronic centrifuges, then test by X-ray diffraction, vibrating sample magnetometer, particle size analyzer, and camera. The experimental method in this project is, first, the mill scale is separated by using magnetic fields. Then mill with 4 and 10.1 watt ratio during 10 and 1 watt ratio during 20 minutes. Then mill scale shift by 400 mesh. Then calcine in with adding graphite at temperature 300 degrees Celsius with half 1 and 2 hours holding time variation. Then characterization with vibrating sample magnetometer, XRD characterization, and particle size analyzer. The calcined powder then adding with 50 ppm textile dye solution. 15 ppm is mixed and separated with electronic centrifuge. Then comparing each solution with photograph. From the accepted test result, the powder is consists of magnetic as a main phase, then posted and hematite as minor phase. With ritual refinement analyzer, the phase result to the effect of holding time of calcination to magnetic peaks percentage, so the optimum one is 1 hour, then 2 hour and a half hour. The crystallization size is 14.35 nanometer with Scherrer equation. From free-betting sample magnetometer of test, the remanence and coercivity is more increased. The magnetic saturation number in this work is 47.14, 46.3 and 48.08 m per gram. The magnetic powder has such a superparamagnetic behavior at room temperature, where the Hc value is near zero. The average result of particle size of oxidized my-scale powder, the biggest is in...
Okay. No. I just want to ask the another participant. Is there any question for Mr. Lukman? I think we have a question from participant. I will ask Mr. Lukman.
Yes, sir.
One question.
Yes.
Why you measure the magnetization of the samples? What is the purpose?
The magnetization is from the magnetization is from.
What is the purpose?
From VSM, sir.
Yeah. I know. I just want to know what is the purpose of the measurement, because hello. What is the purpose of the VSM measurement?
Oh, okay. From VSM,
yeah,
you can see that the material is super paramagnetic that can see by the coercivity is near zero.
Yeah.
That the material is super paramagnetic, sir. This material.
Okay, Dr. Agung, can I help to answer the question?
Yeah.
Maybe
okay.
Dr. Lukman have some difficulties to understanding your question.
Yeah.
So we developed this magnetite in order to absorb the heavy metals.
Yeah.
The behavior it should be in the paramagnetic, like in the present, like in the slide, showing that the hysteresis loop is the very thin, meaning that's already in paramagnetic, almost zero. Actually, we want to address into the super paramagnetic. So, meaning that material is easily influenced by the magnetic from the external, and also can easily release the magnetic force also when it's off, when the magnetic force is turning off, like that one. So when it applied for the wastewater treatment, so it can be easily trapping the heavy metals, or actually the dyes also, the color can be trapped easily. In order when we compare with just the normal carbon active or whatever in the treatment wastewater.
Okay.
Yeah, Dr. Agong.
Yeah. Okay. Thank you.
Yes. That's
okay. Thank you for your answer.
Okay. I'm sorry, sir. Thank you, sir.
Yeah. Okay. I just want to. There is another question. How much absorption capacity? How much is the absorption capacity?
Maybe in the next research I will measure the absorption capacity, sir.
Okay.
Yeah, because the
capacity.
Yeah.
But yeah, that's a good question. Yeah, correct.
But
that's a good question for our current.
Okay.
But the dye can see that the absorption is success by magnetic, sir. By photograph.
Okay.
Photograph.
So maybe I can try to help again.
How much the absorption capacity? Maybe it is like how many percents or how many?
Yeah, the capacity
volume. Yeah.
From the figure that previously shown by Lukman, you know, the dyes, the water previously is very colored. Okay, so when it we just put about 10% from the volume of the 10% volume from the colored volume. Water. Okay. Yeah, so the water we put some dyes, something that make like the waste in the batik, like that one. After we just in this research we use the method using centrifugation, using centrifugal without external magnetic. Without external magnetic, so you just using the mechanophysical process, and as the result, the water become clear. Using 300 RP, 200 or 300, I forget. Maybe Lukman can correct me. About 200 RPM or 300, I forget. But with the time only a few minutes, less than. 400. How long the time, Lukman? I forget. Only 3 minutes, right?
2 minutes.
2 minutes. So only for the 2 minutes, the water become clear, very clear again. Yeah.
Okay.
So but for the capacity, we cannot tell for now, but for sure, from very colored water now become very clear water.
Okay.
Only in the 2 minutes.
Okay. But actually, for now, you haven't measured the absorption capacity, right?
Yeah, not yet, Dr. Agong. Yeah, this is for our future work. Yes, good question. Yeah, good suggestion. Yes.
Okay. This is the question from Mr. Dani.
Okay. Actually, the idea is like this, Dr. Agong. This material should be sustainability. So after we adsorb, and then we can use actually another approach. I cannot tell you now. Actually, so after it adsorbed until saturated, and then we can regenerate it again, the material.
Okay.
So in our focus, our current focus, the capacity we are not focusing yet, because we try to how fast we can adsorb the faster. Yeah, and then we can regenerate. That's our focus for now.
Okay. Thank you, Mr. Dani, Mr. Denny, and Mr. Lukman.
Okay, thank you, sir.
Mr. Eddie.
Yes.
Mr. Eddie.
Yes. Can you hear me?
Are you ready to deliver your presentation?
Yeah. Actually, I prefer to use my video that I sent.
A video. Okay. Yes. Please start your presentation.
Very much for the moderator and the organized committee of International Seminar on Metallurgy and Materials, Ismm 2020. Hello everyone, my name is Edi Suprayoga. I come from Material Theory and Computation Research Group, LIPI Research Center for Physics. Today I will talk about a comparative study of thermoelectric properties of monolayer, bilayer, and bulk chromium 3 iodide. Let's get started. First of all, distribution by temperature gradient and the ability of the material to generate the electrical voltage from the temperature gradient can be expressed by so-called Seebeck coefficient, which is voltage difference over the temperature difference. And other parameters that can be measured by experiment are electrical conductivity and the thermal conductivity. From those parameters, we can evaluate thermoelectric performance and efficiency that defined as power factor and dimensionless figure of merit or ZT. And the preferable thermoelectric materials that have a high Seebeck coefficient, high thermal conductivity, high electrical conductivity but low thermal conductivity, so that ZT is larger than 1. And there have been a lot of proposals of the material which are good for thermoelectric materials. One promising candidate is from the class of 2D materials. And this figure shows the comparison of the band gap value for different 2D semiconductor. And the gray bars indicate the range of band gap value that can be spent by changing the number of layers, straining, or doping. And the requirement to the best 2D thermoelectric materials, it should be semiconductor, high charge mobility, but lower thermal conductivity. So in this case, the best candidate for thermoelectric materials is in the red region. And in this research, we propose to investigate 2D chromium 3 iodide as a candidate for thermoelectric materials. We also compare the thin film with the bulk materials in order to obtain which structure that have the best thermoelectric performance. This class of materials is interesting because its flexibility to manipulate the electronic and magnetic properties by changing the number of layers or by doping. The crystal structure of monolayer chromium 3 iodide view from the top is shown in this figure. In this structure, the chromium ion is from a honeycomb network where 6 iodine ions surround each atom in an octahedral form, and the optimized lattice constant is around 6 angstrom. And in bilayer, the slabs are stacked by van der Waals force with the distance between the plane is about 7 angstrom. Interestingly, the magnetism in this system depends on the number of layers. Is ferromagnetic in monolayer, antiferromagnetic in bilayer, and back to ferromagnetic in the bulk structure. In this study, we investigate the possibility of those layer magnetic system for thermoelectric application. So here is our research aim. First, to investigate the electronic and transport properties of chromium 3 iodide by first principle DFT calculation. Second, compare the thermoelectric properties of monolayer, bilayer, and bulk chromium 3 iodide. And finally, find the optimized parameter to obtain the best thermoelectric figure of merit. Here is our method. First, we perform the DFT calculation by quantum espresso software package to obtain the electronic structure. From the obtained electronic structure, we can calculate the transport properties using Boltzmann transport equation under constant relaxation time approximation or CRTA as implemented in the bootstrap code. In this scheming, the transport distribution T is used to calculate the moment of generated transport coefficient, or we call thermoelectric kernel, or L as function of energy and temperature. Accordingly, the Seebeck coefficient as thermal conductivity sigma and thermal conductivity kappa from the electron contribution can be evaluated for given material using this formula. From those output, we can calculate thermoelectric performance such as power factor and figure of merit using this formula. And here is our calculation result. And the electronic structure of chromium 3 iodine was computed based on the relaxed structure. The electronic properties on this material were computed using the PAW method or projector augmented wave, and the PBE pseudo potential was applied to describe the electron exchange in correlation interaction, and cutoff wave function was set to be 60 Rydberg to achieve the convergent in self-consistency field calculation or SEF calculation. And the Brillouin zone integration for SEF calculation was sampled by 8 times 8 times 1K point mass grid for 2D monolayer and 8 by 8 by 8 K point mass grid was sampled for bulk chromium 3 iodide. And spin polarization calculation was also taken into account with ferromagnetic states for monolayer and bulk, and antiferromagnetic state for bilayer. And we obtained the band structure of 3 samples, monolayer, bilayer, and bulk chromium 3 iodine as shown in this figure. Respectively, for spin up is blue line and spin down is red line. The ferromagnetic semiconductor state in monolayer and bulk chromium 3 iodide were confirmed with a band gap around 1.3 and 1.4 electron volt respectively. And the valence and conduction band in monolayer chromium 3 iodide are occupied by spin up electron. In other case, bilayer chromium 3 iodide is antiferromagnetic semiconductor with larger band gap is around 1.76 electron volt. And from the this electronic structure, we can calculate Seebeck coefficient, electrical conductivity, and thermal conductivity as function of mu or chemical potential. And we plot this transport coefficient for temperature 300 Kelvin or room temperature. From the result, monolayer, bilayer, and bulk chromium 3 iodide almost have the similar value of the Seebeck coefficient, and it indicates that Seebeck coefficient in those systems are independent of the number of layers, and theoretically it can reach up to 2 millivolt per Kelvin by shifting the chemical potential which involve the carrier concentration of the system or by doping. And from the electrical conductivity, we can see that the electrical conductivity near the energy Fermi is almost 0 for all materials due to the absence of conduction band at the energy range, moving away 0.5 eV from the Fermi level. The electrical conductivity start to increase to change for all materials at 300 Kelvin. Interestingly, the electrical conductivity of bulk chromium 3 iodide is larger than bilayer and monolayer chromium 3 iodide because the electron can move more freely on 3D crystal rather than 2D system. And the variation of thermal conductivity from the electron contribution in the system is as function of chemical potential is shown in this figure. And the thermal conductivity appears to follow the trend of electrical conductivity, and this correlation between thermal conductivity and electrical conductivity is consistent with the Widerman-Franz law. To study the electrolyte transfer properties of the system as function of temperature, we plot Seebeck coefficient, electrical conductivity, and thermal conductivity at Fermi energy state. From this figure, it can be observed that Seebeck coefficient of each system has different behavior. The absolute value of Seebeck coefficient of monolayer is almost 0 below 200K and suddenly rise to 3 millivolt per Kelvin at 200K, then continue to decrease by increasing temperature. In bilayer case, the absolute Seebeck coefficient has optimum value at 300K, whereas the in bulk system, the value is still increased by increasing temperature. It can be justified that the system become metallic at higher temperature, as shown in the electrical and thermal conductivity. And then we can define the power factor and dimensional figure as merit on this system by using this formula. In this case, power factors of bulk chromium triiodide is higher than monolayer and bilayer because it higher electrical conductivity, while the Seebeck coefficient is relatively the same. Meanwhile, the dimensionless figure of merit ZT shows that all of system has the same thermoelectric performance. And when the energy up to 0.5 eV from the Fermi level and reach ZT is reached to a value of 1, and optimal power factor of NZT can be obtained by shifting the chemical potential by 0.5 eV. Here's our summary. Seebeck coefficient in monolayer, bilayer, and bulk chromium triiodide have a similar value. Theoretically, it can reach the maximum value of 2 millivolt per Kelvin. The electrical conductivity of bulk chromium triiodide is larger than monolayer and bilayer, implies that the bulk chromium triiodide has a better thermoelectric power factor, and nevertheless, the dimensional figure of merit of the system remain the same. And thank you very much.
Yeah.
Thank you for this time.
Thank you.
My name is Afinur Hidayah. I'm from Research Center for Physics, Indonesian Institute of Sciences, and I'm also PhD student from Physics Department, University.
Hello.
Yeah.
Thank you.
Okay.
Thank you, Mr. Eddie. I think we haven't the question from participant yet, but I want to ask you about the how about the figure of merit versus temperature? Did you calculate it?
Oh, yeah. Actually, I calculate the figure of merit versus temperature, but not shown in my slide. I haven't prepared the figure. Sorry.
Okay, but you calculated, right?
Yes, already. I have already got the data and just plot it by temperature.
Yeah, yeah. Because if in we know the figure of merit versus temperature, we will know about the operating temperature for the material, right?
Yes. Yeah. Thank you very much for your suggestion. Yes, but basically, it is room temperature, so the best performance is around room temperature, not low temperature.
Room temperature. Okay. Okay.
Yes.
And how about the density of state of the electron? Have you calculated also?
Yeah, yeah. Basically, when we calculate the band structure, we also got the density of steps of this material. Yes.
Okay. Thank you, Mr. Eddie.
Thank you
for your presentation.
Thank you very much.
Please give applause for Mr. Eddie. Thank you. And we go to next presenter, Mr. Afi. Mr. Afi?
Miss Afi, sorry.
Oh, Miss Afi, I'm sorry. Miss Afi.
Yes.
I'm sorry. Are you ready?
Yes, ready.
You will presenting by your video?
Yes, video.
Okay. Okay, please start your presentation.
Thank you for this time. My name is Afinur Hidayah. I'm from Research Center for Physics, Indonesian Institute of Sciences, and I'm also PhD student from Physics Department, Universitas Indonesia. So today I want to talk about my experiment. This is about molar concentration of silver nanoparticle on performance effect of surface enhanced Raman scattering source, glass substrate fabricated by drop casting method. Metallic nanoparticle is almost 20 years have been studied because a metallic nanoparticle is very interesting. They have special optical properties, special electronic properties, special catalytic properties. Metallic nanoparticles have a localized surface plasmon resonance that have a diverse range application like photonics, catalysis, information storage, chemical or biological sensing, and surface enhanced Raman scattering. So this is the example of metallic nanoparticle that the most studied. There are gold, silver, copper, and bismuth. They have a localized surface plasmon resonance Higgs absorption band in the visible region. In our experiment, we focus on silver nanoparticle because silver nanoparticle have better plasmonic that have a narrower plasmonic width than another metallic nanoparticle. Silver nanoparticle have high electrical and thermal conductivity, stability at ambient condition, high primitive character, low cost than gold and platinum. So this is make silver nanoparticle as good candidate for SEARCH. SEARCH is a very interesting because SEARCH can be used as a detection molecule for environmental contamination. In SEARCH system, there is enhancement of local electromagnetic field at a surface of metal. So this is a make enhance Raman signal. Basically, Raman signal is weak, and the SEARCH system can enhance a Raman signal. There is a gap between two nanoparticles called hotspot. You can see that this is hotspot and this is a 2 nanoparticle. So the study of hotspot and study of the nanoparticle is very important because they influence enhancement of local electromagnetic field in SEARCH system. So the quality of SEARCH depends on quality of nanoparticle. In our experiment, we fabricate a SEARCH substrate in different molar concentration colloidal silver nanoparticle. We want to know what the effect of properties of nanoparticle to SEARCH. We use silver metal salt silver nitrate, distilled water, ammonia, PVP, glass substrate, and deltamethrin pesticide. So this is the schema of our method. The first step, we synthesize silver nanoparticle and continue the fabrication of such substrate, and the final, the testing of quality of such substrate using analyte deltamethrin pesticide. Synthesize silver nanoparticle. We must preparation of a silver metal ion, synthesis of silver nanoparticle in water medium in a 5-minute irradiation time. After silver nanoparticle have been synthesized, we characterize using UV spectrophotometry to observe localized surface plasmon resonance. So this is the preparation of silver metal ion. We dilute silver salt, ammonia, and PVP to water medium into 2 different concentration molar. Synthesize silver nanoparticle in water medium. It can be from silver metal ion drop into cuvette and irradiate with femtosecond laser in 5 minutes irradiation time. So this is the set up our experiment. This is a femtosecond laser, mirror, and metal ion solution in using drop casting method. The first step is a colloidal silver nanoparticle in different concentration molar will be dropped and casting into a glass substrate and dry at around 100 degrees Celsius on a hot plate, and then the part spectroscopy. After that, its substrate in different molar concentration is sprayed with pesticide detected, and then a test enhanced Raman signal using Raman spectroscopy. We use Raman spectroscopy from HORIVA using a 532 nanometer laser as excitation source and the power laser of 250 milliwatt and the magnification of 10. This is the result of discussion. This is the graphic of a localized surface plasmon resonance of silver nanoparticle in different molar concentration. You can see that there is a difference in two different concentration of silver nanoparticle. There is a redshift from localized surface plasmon of sample 2 in higher concentration particle decorated as a substrate. You can see that in higher concentration of molar, they have a bigger particle size than lower concentration. And you can see that from the morphology, from the blank glass is without nanoparticle. You can see that in the blank glass there are no delta metrin pesticide have been detected, and in two different molar concentration substrate you can see that there are 6 Raman signal that have been detected, and there is a different peak intensity, Raman intensity. There is Raman intensity in higher sample 2 at some point have higher intensity than a sample 1. So the increase influenced by hotspot in sample 2 because the hotspot area may be influenced by a particle size bigger than particle size in sample 1. The conclusion of my experiment, the number 1, silver nanoparticle in higher molar concentration have bigger particle size than in lower concentration. Number 2, such substrate from silver nanoparticle in higher molar concentration show the Raman peak of delta metrin pesticide tends to higher at some point. Number 3, enhancement factor that affect the increased Raman signal intensity relatively increase proportionally to the bigger particle size of the nanoparticles. And number 4, there are 6 delta metrin pesticide Raman peak have been detected. Thank you for this time.
Okay, thank you, Ms. Afi.
Particle in nanoparticle, the shape is like ball. So the substances is also the shape is like ball because we use the nanoparticle.
Because when I see your result, your measurement result, I just wonder why the small size distribution is bigger.
Oh yeah, because it's influenced by molar concentration in substrates. If you want to,
okay.
Yes, we fabricated such substrate into different molar concentration from two different silver nanoparticle, because such substrate is depend on the quality of nanoparticle. So in my research, we want to know what the influence of molar concentration of quality of nanoparticle to such substrate.
Okay. I see. Okay, thank you,
Ms.
Afi. Please give applause to Ms. Afi. We will go to the next presenter, Mr. Geral. Mr. Geral?
Yes.
Are you ready?
Yes, I'm ready. I would like to use the video that I already sent. Yes.
Video? Okay. Please start your presentation. The time is yours.
Good afternoon. My name is Gerald Insang Timuda from Indonesian Institute of Sciences, or LIPI. and I want to present my study about photoelectrochemical water splitting properties of a vertically aligned zinc oxide nanosheet. So this study is one of the effort to find new renewable energy to overcome the oil scarcity. And one of the interesting renewable energy is fuel cells. These cells takes hydrogen and oxygen as the fuels to produce electricity, and as the side product, will only produce water and heat. So this cell is very environmentally friendly. But the main problem is the supply of hydrogen gas. The main supply is coming from the steam reforming methane. So in this process, the methane is coming from the natural gas, which is non-renewable. And also the process itself will produce CO2, which environmentally not friendly. Another way to produce hydrogen is by using water electrolysis. However, this reaction is the exact opposite of the reaction that happened in the fuel cell. So it will need extra electricity from the outside to produce hydrogen. Another way to overcome this problem is by using other type of renewable energy as the electricity supply, or we can instead directly use the solar energy here, not to produce electricity from the solar cell, but directly used to activate one of the electrode in this system, so that this electrode will produce electron, and then eventually it will be used to produce hydrogen. This is another picture to show the mechanism. The energy from the sunlight is used to excite the electron in the semiconductor here, and the electron will go to the external circuit, and we will see it as the increase of the current if we measure the current here. And the electron here then will be used to reduce water here to produce hydrogen. This is a typical for the current response of the photoelectrochemical water splitting. The dark is the black one here, the light is the red one here. You can see the increase of the photocurrent as the response of the light illumination. And the bottom here is another way to show the effect. When the light on and off, you can see the abrupt changes in the current density. And the picture on the right side here is just another way to join these two type of measurement into one like this too. So this is the photocurrent response. And what are the photoactive materials that can be used as the photoanode? This in this figure, you can see several types of materials. One of them is zinc oxide. Zinc oxide, one of the requirements that is needed is that the semiconductors need to have conduction band higher than the redox potential of the hydrogen production. So the zinc oxide is used in this study. It has Wurtzit hexagonal structure, 3.2 electron volt band gap, mobility much higher than the TiO2, and it's easy to be formed into various nanostructures, such as nanoparticle, nanowire, or nanosheet. It all has its own merit and demerit. And for the PEC water splitting itself, there are several reports that shows the benefit of one of the type of the structures. In this case, the nanosheet shows to be better than the nanotubes and the nano triangle here, nano cone here. So based on that, the motivation of this research is to improve the nanostructure here. From the previous report, you can see the nanosheet is used, and it has higher photocurrent compared to the other nanostructures. However, in this case, here are the papers that you can refer to if you are interested. So in these papers, we already explained the effect of alphonostatic electrodeposition on the morphology, we change the current density and times. We also address the underlayer formation, the origin of the underlayer formation, and also talking the mechanism of the crystal growth. And in this particular recent study, the objective is to implement this type of vertically aligned zinc oxide nanosheet as photoanode in photoelectrochemical water splitting. This is the experimental method. The electrolyte used is zinc nitrate and potassium acetate. The current density that we use is 1, 3, and 5 milliampere per centimeter square. We want to make the cell have the same charge density, so the time is adjusted accordingly. After the electrodeposition, we anneal our samples for 400 degrees Celsius for 1 hour, and then use it as photoanode. The light source here, we use UV lamp, 15 watt, and we record the current response using potentiostat and galvanostat. This is the results. This is a typical top view of the zinc oxide nanosheet that we obtained. And if we compare with the previous study, we can see that these have vertically aligned, the bottom here horizontally aligned, so very much different. Another literature also show some of them become vertically aligned, but there's still much of them which has horizontally aligned. So in terms of alignment, we can say that our cell is vertically aligned, much better than the previous cell that our previous literature that horizontally aligned. So in terms of alignment, we already succeeded, and you can see from here this result also. Beside the nanosheet structure, there are also the underlayer formation for 1 milliampere per centimeter square applied current density. The underlayer type is a dense-like, but for the 3 and 5, there are a particle-like underlayer. This is the XRD of the zinc oxide nanosheet before and after annealing. So before annealing, we can see besides zinc oxide, there are also other phases coming from the formation of zinc acetate hydrate complexes. But after annealing, all of them are completely transformed into zinc oxide. So you can see the zinc acetate complex already disappeared here. And other reaction here between zinc ion and acetate and hydroxide will produce zinc acetate hydrate complexes. This is the one that is responsible for the nanosheet formation. And after annealing, all of this nitrate zinc acetate hydrate complexes will be transformed into zinc oxide. But the result, the nanosheet will become porous, like shown in this figure. Now this is the photocurrent characteristics of the zinc oxide nanosheet. As we can see from the left pictures, the on-off characteristics is like this. So there's an abrupt changes of the current. It means that the response is really coming from the excitation of electron from the zinc oxide material, not from other sources like heat or other thing. And the right side is the IV curve of the photocurrent. If we compare the IV curve with what we can find from the literature, the current itself in our case is still lower compared to the literature. However, we need to consider that in our case, we only use a very low power density light source. We use 15 watt light, but in the literature, they use 150 watt lamp. So if we extrapolate this, we can hope that if we increase our lamp by 10 times, there's a possibility that the current will be increased also about 10 times. If in that case, we can possibly have a larger photocurrent compared to the literature. And this is the comparison between the three samples. The trend that we found is that the zinc oxide 3 is larger than 1 and larger than 5. Between zinc oxide 1 and 3, they have similar height, but the difference is only the type of the underlayer. For the zinc oxide 1 is the dense light, zinc oxide 3 is the particle light. The dense light has a smaller current, therefore the dense light type of underlayer might hamper the electron transport properties. And the opposite is for zinc oxide 5. Actually, this has the tallest nanosheet. However, it has the smallest current. We think that this is because the underlayer type of this cell, not only it has particle light, but also a lot of gaps here between the substrate and the nanosheet. Therefore, this will definitely hamper the electron transfer properties from the nanosheet to the substrate. Therefore, we need to evaluate not only the height, but also the type of the underlayer. It's becoming important in designing the PECN. So for conclusion, we have successfully demonstrated the PEC water splitting effect of zinc oxide nanosheet produced from galvanostatic electrode deposition. In this case, the photocurrent is produced under illumination. You can see the abrupt changes of the photocurrent under on-off light illumination. So the response is really coming from the zinc oxide material. And also the last one, we need to evaluate the underlayer properties of our material, not only the height of the nanosheet. This is the reference that we use, and thank you for your attention.
Thank you, Mr. Gerald. Thank you, Mr. Gerald. Actually, we have.
You're welcome, sir.
One question from Professor Dani, and Mr. Gerald has already answered that. Professor Dani, do you have any response to this answer?
It's enough. Okay, thank you.
It's okay? Okay.
Okay.
Maybe.
Okay, Professor Dani, thank you for the question.
Okay. Is there any question from participant? If no, I will go to next presenter, Mr. Bernardus. Mr.
Hello?
Bernardus. Yeah?
I'm here, sir.
Are you ready?
Yeah, I prefer to use the video.
Okay.
Yeah, thank you.
Okay, the time is yours.
Hi everybody, my name is Bernardus Randy, one of the author of this proceeding. First of all, I'd like to give my gratitude to the committee for the opportunity to present in this conference, and thank you to the audience for tuning in to watch this presentation. This paper was a project of my internship with Dr. Edwin Heskeasteel. We computed through density functional theory an ab initio method for atomistic scale simulation of materials to understand the effect of common strains in zirconium silicon selenide, or ZSSE, which were classified as a new type of a new material class, a topological material. More specifically, it is Dirac nodaline semimetals. Without further ado, let's start with the basic and build upon it. Okay, so in order to understand topological Dirac nodaline semimetals, we have to go back to graphene. Graphene was found to have linearly dispersing band structures, which are called Dirac cones, where each has a meeting point called Dirac node. This linearly dispersing band is similar to light, making electron massless and obeying the relativistic Dirac equation for massless particles. This, in turn, gives a large current density, nearly 1 million times higher than copper. Exotic materials with similar linearly dispersing electronic band structure in the surface, but gapped in bulk, has also been found. It is conducting or metallic in surface, but insulating in bulk. We call it topological insulators. There are also other exotic materials with topologically protected semimetals, such as these 3D Dirac semimetals. Dirac semimetals only have a pair of Dirac cones. Imagine if there are many Dirac cones in Brodin zone, creating a closed loop line. It is called as nodaline. More specifically, it is called a Dirac nodaline semimetals because it has degenerate conduction and valence band, meaning that it has two overlapping band structure with the same energy in Dirac cones. These Dirac nodal enzyme metals has a drumhead surface state. So what's the application of such exotic material? Well, first of all, if we apply electromagnetic field, it has this weird effect of topological current, where the current will be perpendicular to the electric field given. This pave way to new exotic devices, such as topological current rectifier. Above all that, it also have a huge charge carrier density compared to ordinary Dirac semimetals, a potential nonlinear Hall effect, and a large butterfly magnetoresistivity. The butterfly magnetoresistivity means if we apply magnetic field at a certain magnitude and angle, the resistivity magnitude will change accordingly, creating the way for potential application of magnetic sensor. This material might also potentially unravel the relationship between pneumatic and topological superconductivity. Plasmonic excitation and optical conductivity are interesting, fundamental optical properties due to its technological application. Plasmonic excitation is a collective excitation of electrons, while optical conductivity is the excitation of a single electron. Strain has been analyzed for several possibilities of these properties in a similar CSS type material, but a different chemical composition. The studied one is the zirconium silicon sulfide, while ours is zirconium silicon selenide. These properties are defined by the band structure. Yet, it is still unknown how robust is the nodal line and band structure itself in this ZSS type material. So in our study, we aim to understand the robustness of Dirac nodal line semimetal under several types of strains. And so we limit our scope of study to equibiaxial tensile strain, compressive strain, hydrostatic strain, and low indexes strains, such as 100 and 110 strain. These strain might be induced through mechanical, chemical, and heterostructure configuration, such as through lattice mismatch. And so how do we calculate it? We first create the model of known structure of zirconium silicon selenide as shown in the A figure and relax it for every strain. And then we calculate the band structure along high symmetry points in the first Brolin zone. And then we scan through repeated calculation in KZ equals 0 plane of the first Brolin zone because we don't know exactly where the nodal line is. We done this calculation in quantum espresso software using norm conserving pseudo potential from pseudo dojo. And of course, before calculation begins, we tested our parameters for convergence, such that we can trust the result. From a very technical part, we also include the effect of spin-orbit coupling, in which relativistic effect of electrons' magnetic dipole, orbital motion, and electrostatic field of positively charged nucleus are also taken into account. Our first result is in equilibrium state. We found that the Dirac cones are gapped due to strong spin-orbit coupling, as shown in the figure A. Note that the symmetry-protected nodal line is not that one, but this one, pointed by the orange circle. But we're interested in the gap nodal line because it's nearer to Fermi energy. So for the nodal line, we only have to calculate this green line because of its symmetry. And the conduction bands and the valence band associated with it have to be calculated also because it defines the whole KZ equals 0 nodal line in the Brolin zone. And we plot the nodal line in new arbitrary axis in KZ equals 0 plane called K parallel. If we project this green line into KZ equals 0 plane, that's K parallel. From there, we can see the main property that the nodal line is actually sinusoidal rather than a flat. That's interesting. The conduction bands of Dirac cones are always empty in equilibrium state, and its gap varies relatively small amount along this sinusoidal nodal line. In the strain system, we will mostly focus on Dirac nodal line energy and shape rather than the detailed in band structure changes. In fact of equibiaxial tensile strain, just decrease the DNL average energy and gap widening in the middle of K parallel, without significant change in Dirac nodal line peak-to-peak distance. And from this trend, we suggest an alternative way to tune the average Dirac nodal line energy relative to the Fermi energy while also tuning the conduction bands so that only Dirac nodal line present near Fermi energy. And in equibiaxial compression, first, it increased the nodal line amplitude and gap in the middle of K parallel, and then followed by increase in average energy shown by the brown line, and increase in peak-to-peak distance of the node line. There are also some minor changes in band structure, such as several bands energy reduction and Dirac conforming. Uniaxial 100 strain changes the unit cell from tetragonal to orthorhombic, giving less symmetry. We speculate that the ZR bands related in the tension 100 strain is related to equibiaxial tensile strain, because the results are similar in ZR conduction band, and in the nodal line, increasing peak-to-peak distance of nodal line and increase in nodal line energy is similar to biaxial compression. There are also overlap in band structure, giving half-closed gap and changes in band energy. But all of this is still a speculation and have to be proven through chemical bonding analysis. In hydrostatic strain is also interesting because the effects on band structure and density of states are not too significant, but it has increase in nodal line amplitude and energy. It can be used to analyze the effect of nodal line lifting without noise from band structure changes. Uniaxial 110 strain, which is similar to YZ plane's shear strain, changes the tetragonal unit cell into monoclinic unit cell, therefore changing the Brolin zone. The system also experienced inversion symmetry breaking, which could unlock a nonlinear Hall current, in which, under oscillating electric field, consists of photogalvanic current and second harmonic current, which holds the promise of a more efficient solar cells and second harmonic lasers. This strain system also has half-closed gap and significant increase in nodal line amplitude. The Dirac nodal line experienced only minor reduction in cross-sectional area on KX-KY plane or KZ equals 0 plane. The average energy is defined by averaging the energy of nodal line between conduction and valence band. This result suggests that the Dirac nodal line average energy can be tuned using strain. So in conclusion, we can tune band structure and Dirac nodal line using our result to engineer this material electronic structure and its exotic nodal line through strain and symmetry breaking while maintaining nodal line robustness in this material. The changes to the electronic structure in this type of material is easiest to be observed in equibiaxial tensile strain, uniaxial 100, and uniaxial 110 tensile strain. The detail of the results and conclusion can be found in our arXiv. These are the reference for this slide. Thank you very much for the opportunity to present our paper, and we hope you find it interesting and useful.
Thank you, Mr. Bernardes.
Yes.
Okay. We have. I will check the chat. I'm sorry. We still don't have a question yet, but I will ask you, how about the pressure effect? Can we also calculate the pressure effect as well?
The pressure as in hydrostatic pressure, sir.
Yeah.
Oh yeah, hydrostatic.
Like hydrostatic, or if we use the diamond to pressure the material.
Oh yeah, actually, so my study is pretty general. The way that the strain is induced is it can strain, but we pulled it. We apply tensile strain. So in this tensile strain, when the other two axes are able to relax, the effect is pretty unique. That it is the combination of if we strain it in x-axis of the material, if it's a thin film surface, if we pull it or press it, it combines both the shrinking in z direction, of the cell, and so the nodal line itself abruptly changes. So it changes, it changes rapidly to the nodal line will increase in energy for about 10 times than it was from the Fermi energy. Yeah. So that is the result that we found in the uniaxial strain. If we pull the material, if we push the material, it will be, I suppose, reversed, but we haven't checked about it yet. We just checked the tensile strain.
Okay. I just wonder, like the presentation that delivered by Professor Andika earlier. It is about the superconductor phenomena in lanthanum hydrogen that will have room temperature superconductor, but in high pressure. I just wonder if we can calculate the band structure. Okay.
Actually, yeah, you can. So you just have to vary the structure of the materials unit cell. Yeah, you can calculate that.
Okay. Thank you, Mr. Fernandes.
Yeah.
And we go to the next presenter, Ms. Nur Rahmawati. Ms. Nur, are you ready?
Ready, sir.
Okay. You are prepared using video?
Yes.
Yeah. Okay. Please start your presentation. The time is yours.
Good afternoon, everyone. I am Ayu from Institut Teknologi Bandung. The paper is addressed to give an introductory overview of fault-tolerant quantum computing by employing Majorana fermions in a topological superconductor. I am mentored by incredible researchers from LIPI, Mr. Hezki Hasdio and Mr. Hamza Fauzi. First, I want to say thank you to the organizer of Ismm and Research Center for Physics LIPI for giving me this precious opportunity. Quantum computer. The beginning of quantum computing was probably when Feynman first stated about a simulation of quantum evolution facing unavoidable exponential time slowdown in classical computers. Though quantum computer will not replace classical ones, they will revolutionize particle problems that are classically hard to solve, such as quantum simulation and many more. Quantum simulation in particular is able to simulate larger molecules with excited energy state. Generally, quantum computing involves three major steps. First, initialize the state of qubit as input, then perform arbitrary control unitary operations on this initial state, and finally measure the qubits as the output. Nowadays, you can run your circuit freely on quantum computing facility which is offered by IBM. Qubit is a quantum analog for a bit. Bit can be represented by a voltage inside transistor, whereas qubit might be represented by many platforms. One of the most used is superconducting qubits. Suppose we have one qubit, then we may construct any superposition state with the basis of 0 and 1. Before measurement, we will know our state. Once we measure the qubits, we will have collapse state with its certain probability. Another special characteristic needed is entanglement. If we spare these two superposition states, their entangled properties will not change no matter how far. Entanglement will maximize the state to the finite probability. Errors in qubit. Suppose we have fermionic states. We can encode qubits. If it's whole, the state is 0, and if it's filled, the state is 1. However, this state entanglement is very sensitive to errors, which is in the form of decoherence and inaccuracy. This we call our technology today NISQ era. To tackle this, we may use QEC available today. However, it is unclear whether quantum computation can be made fault-tolerantly only by the QEC scheme. Here, the idea of topological qubit comes to rescue. Majorana fermion is a particle that is its own entire particle. We may then encode qubits in a very non-local way because one fermionic state can be constructed from two Majorana fermion. Thus, it's highly entangled and protected from any local disturbance. This idea was first proposed by Kitaev in the form of an ionic exchange. In three spatial dimensions, we only have two types of elementary particles, either boson or fermions. However, in two dimensions, the phase can be anything and we will have a different set of particles for every phase, so-called anyons. Exchanging Majorana is term braiding, and measurement of its final state are done by observing the result of fusion. This braiding turned out to be non-abelian statistics that is similar to the exchange operation needed for topological quantum computation. A non-trivial unitary operation will bring the system to a new quantum mechanical state after each exchange that is similar to the mechanism of quantum gate. Now the question is, how to find Majorana-based topological qubit that exhibit non-abelian statistics? The proposal of realizing non-abelian anyons is pursued in two major systems, superconducting and quantum Hall. In normal metal, we have electron and hole, and it's usually impossible to form superposition of them. In superconductors, we have Cooper pairs that consist of two electrons. If we have a single hole in our system, for example from the normal conductor, and we take one Cooper pair, then they will pair together and look like a single electron. This blurring of electron and hole can be described by particle-hole symmetry. For a particle at energy E, we must have an antiparticle at energy minus E. For zero energy, then we get Majorana bond states. In superconductor, this energy spectrum has a gap. If we have zero energy state, it has to remain there regardless of all kinds of perturbations. Therefore, they are so-called topologically protected. Also remember that Majorana always come in pair to form one fermion, so they are robust. We can thus distinguish two kinds of superconductors. Superconductor with Majorana is a topological superconductor, and conversely, without Majorana, it is trivial superconductor. With MBS being at zero energy, we can have multiple Majorana pairs that all have zero energy. Thus, with n pairs, we have a 2 to the n fold degenerate ground state because each pair can be occupied or 1 or not occupied 0, as in the table. We know that we have Majorana fermion in topological superconductor with zero energy gap in the form of degenerate state, so-called Majorana bond states. Now the question is where to find them. In reality though, we cannot separate the MBS infinitely far from each other. There exists an overlap that is exponentially small so that the state will be very close to zero energy. Also, finding MBS is not as easy as it seems, because MBS might go anywhere outside the zero energy in the gap. Hence, we might consider a vortex where magnetic flux penetrates in superconductor. It will suppress the gap, and as a result, we will have MBS by employing P-wave superconductor. However, this vortex is hard to control. We then might try nanowire out of P-wave. It is predicted that MBS might appear at the end of this nanowire as proposed by Kitaev in 2001. However, nobody knows P-wave in nature. Hence, we have to engineer P-wave from ordinary superconductor. In 2012, a path-breaking work from TU Delft, the Kaunhoven group, claimed that they had signatures of MBS with this ingredient: strong speed orbit coupling, S-wave superconductor, and finite magnetic field parallel to the nanowire. But this is not enough. We have to tune some parameters to get the topological phase. There are many platforms for realizing MBS in topological systems. In 2001, Kitaev proposed the 1D quantum wire. In 2008, a proposal from Liang Fu and Charles Ken in 3D topological insulator that resembles P-wave superconductor. And in 2010, a proposal by Xiaoqing Zhang's group from Stanford. They utilized quantum anomalous Hall insulator and found chiral Majorana signature in 2018. Although this experiment is argued because the evidence can be achieved in similar devices with disordered samples. The nanowire system has gained particular attention though due to ease of realization and high degree of experimental control. MBS are always located at zero energy, and they give rise to zero bias voltage in the conductance that is quantized at 2e squared per h. We call this ZBCP, or zero bias conductance peak. When applying a voltage at the contact between normal metal and superconductor, then measure the current across a tunnel barrier, we will get its conductance. So when electron arrives at superconductor, electron from Fermi Z will pair with the other electron to form Cooper pair and then leaving a hole to the normal metal. If we have MBS at zero energy, then ZBCP will appear. This is the common detection method used in spot breaking work in 2012 by TU Delft. Here, the ZBCP is at zero magnetic field, so no Majorana appears. For finite magnetic field, as the field is increasing, a peak at zero bias is emerging. However, this result is then argued because the quantization is not 2e squared per h as the predictions. Also, other effects known as undrift bound state or ABS might induce the ZBCP if the value is small. In 2016, an experiment which differentiates between MBS and ABS in non-topological phase is performed by a group in Copenhagen. This experiment demonstrates that MBS is coalescing from ABS in a hybrid indium arsenide nanowire using quantum dot at the end of the nanowire. A year later, this experiment is disputed. There is a situation where ABS might indeed come together from MBS. However, these conditions are so difficult to distinguish since they produce similar ZBCP, mimicking the MBS, even in clear disorder-free system. Finally, they suggested more decisive transport measurement to reveal the true non-local nature of Majorana. The suggestion to observe ZBCP from both ends motivated similar experiment in 2019 to establish simple examination of correlations between two sets of ZBCP tunnel data. MBS will give rise to correlated ZBCP at both ends. In contrary, if ZBCP only exists from one end, then it's likely to be arising from ABS. This numerical simulation is then refined by Zhang, which explains various measurement techniques for validating MBS in nanowire system. Therefore, there are two major focuses on achieving quantum supremacy. First, to find superior algorithm which beyond Shor and Grover's algorithm, and second, to perform fault-tolerant quantum computing that is resilient to errors. To sum up, the two most promising methods from topological quantum computation are the nanowire platform and the whole system. The next step is to establish Majorana zero modes in this structure by performing key experiments.
Okay, it's finished. Okay.
Yeah.
Yeah. Before we go to Q&A question, I would like to tell you to mention the participant that the previous presenter in the previous presenting there is one question from Mr. Hesky, and actually it seems that Mr. Bernardes has answered the question. Mr. Hesky, it is enough? Is there any response from you also? Hello? 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 Mr. Hesky, you answer. You have question for Mr. Bernardes, right? Hello. 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 Okay. Responding. Okay. We will go to Q&A session for Miss Nur. I think we haven't have question. Sorry for Miss Nur. But I have. Okay. There is one question. The question is from Mr. Nugraha. The question is. Sorry for asking a basic question. I don't understand why we need superconductor for observation of Majorana fermions. Ms. Nur?
Okay, thank you. Thank you for the question, Mr. Nugraha. So it's not a basic question. So it's quite natural to have Majorana bound states in superconductor because in superconductor, I think I will come to the Majorana fermion itself. So Majorana is a particle that is its own antiparticle. So in Majorana, if it's natural to look in superconductor because in superconductor we have like Cooper pairs, and in the Cooper pairs, if it's combined with a hole, then it will looks like a blurring of electron and hole, which is so a particle that is it's an anti-particle. So actually, one fermion is from two myo. Mr. Nugraha, do I explain it like clearly?
Mr. Nugraha? Hello? Mr. Nugraha? Maybe. Hello?
Yes, yes. Thank you for asking, for answering the question. Yeah, it's clear. Thank you.
Okay?
Yeah, okay. Yeah, I actually also reply by chatting. Thanks.
Okay, good.
Okay,
thank you.
so much.
Thank you also, Ms. Nur. Ms. Nur. Also, I have one question for Ms. Nur. I just wonder, is there any country that already applied the quantum computing?
Is there? Sorry, sir. Is there?
Is there any country or any company or any laboratory?
Actually, nowadays there are a lot of companies collaborating with quantum computing, mainly IBM and Microsoft.
IBM.
And this,
I see.
yeah, IBM and Microsoft. And this topological quantum computing is the approach from Microsoft, and IBM use another type of qubits. So IBM currently has like 65 qubits.
I see.
To run, and you can run your circuit freely on the IBM platform.
I see. Okay. Okay. Thank you, Ms. Nur. And start from I'm sorry. I will check the program.
3:15.
Yes. 3:15. 3. Coffee break is for okay. 3:15. Okay. We will go to coffee break, and then at 3:15 we will start the next session. The next session will be the moderator of the next session will be Dr. Andri Hardiansyah. Okay, thank you for the attention. Yeah. A photo. Before I see. Okay. Before we end this session, we will go to photo session. Please, the participant turn on. Yeah.
Where is the coffee? Where is the coffee?
Coffee?
Well, I can find the coffee. Just kidding.
Okay.
Come to our room, then I can make coffee for you.
Okay. Please, the participant, turn on your video. We have photo session now. Okay. It's all? I don't know. Maybe Mr. Bernardo, Mr. Gerald, Miss Afi, Mr. Nono, Mr. Lukman, Mr. Aga. Okay. Maybe it's all. Hello?
Yes, so everyone is free to do anything.
Okay.
Thank you, Pak Agung.
Okay.
Okay, thank you.
Have you shared?
Thank you, Kang Ridwan.
Okay, thank you. Thank you. Don't forget to attend the next session.
Berawal dari cita dan asa untuk membangun negeri, memberikan segenap rasa dan tenaga untuk menghasilkan pemikiran terbaik bagi negeri tercinta, kami ada untuk Indonesia. Mewujudkan diri sebagai Lembaga Ilmu Pengetahuan Indonesia yang andal, profesional, inovatif dan berintegritas dalam pelayanan untuk mewujudkan visi Presiden dan Wakil Presiden. Indonesia Maju yang berdaulat, mandiri, dan berkepribadian berlandaskan gotong royong. LIPI memiliki berbagai pusat penelitian tersebar di seluruh Indonesia yang berada di bawah Kepala LIPI, Deputi Ilmu Pengetahuan Hayati, Deputi Ilmu Pengetahuan Kebumian, Deputi Ilmu Pengetahuan Teknik, Deputi Ilmu Pengetahuan Sosial dan Kemanusiaan, Deputi Jasa Ilmiah dan SDM Pendukung Iptek di bawah Sekretariat Utama LIPI. LIPI berperan dalam proses penyusunan dan kelahiran berbagai regulasi dan kebijakan pemerintah terkait aspek ekonomi, politik, sosial, dan budaya. Selain itu, LIPI juga mengelola data dan timbangan ilmiah dalam rangka konservasi keanekaragaman hayati. Menerbitkan tanda pengenal unik publikasi ilmiah terbitan berkala, membuat repositori ilmiah skala nasional, dan memiliki kewenangan sebagai pembina Jabatan Fungsional Peneliti Nasional, serta melaksanakan proses pengukuhan profesor riset di Indonesia. Kini, LIPI juga mendukung percepatan penanganan COVID-19, baik melalui riset berupa kajian maupun produk, maupun pengembangan SDM melalui program Indonesia Memanggil. Untuk mendukung riset, LIPI memiliki 5 kebun raya sebagai pusat konservasi flora ex situ. 2 museum yang memiliki koleksi flora, fauna, dan kesejarahan alam Indonesia. Indonesia Culture Collection yang menyimpan koleksi mikroorganisme terbesar di Indonesia. Infrastruktur riset strategis. Dan beberapa pusat berskala internasional, yaitu Asia Pacific Center for Eco-Hydrology atau APCE. LIPI telah menghasilkan hasil riset yang berkualitas dan bermanfaat bagi masyarakat, meliputi keanekaragaman hayati, lingkungan dan maritim, ketahanan pangan, pertanian, dan peternakan, kesehatan dan farmasi, material maju, energi, teknologi, informasi dan komunikasi, pertahanan dan keamanan, dinamika sosial, kemanusiaan dan kebudayaan, kebencanaan, inovasi teknologi dan pendayagunaan iptek, pelayanan, pengujian, dan pembinaan ilmiah, serta peningkatan kualitas SDM iptek. Kerjasama keilmuan LIPI dalam negeri meliputi kerjasama penelitian, lisensi teknologi, pengembangan, aplikasi dan komersialisasi hasil penelitian, kerjasama non-penelitian, dan konsultasi kepakaran LIPI. Sedangkan kerjasama luar negeri, LIPI melakukan joint research, workshop, pertukaran peneliti, dan beasiswa mancanegara, selain aktif menjadi anggota dan focal point di berbagai organisasi internasional. Melalui kolaborasi bersinergi, menghasilkan riset yang berkualitas, LIPI terus memberikan manfaat nyata, kontribusi berarti, dan turut mewujudkan cita dan asa membangun negeri kita tercinta, Indonesia. Indonesia merupakan negara yang kaya akan sumber daya alam. Salah satu aset yang kita miliki adalah kekayaan mineral. Pusat Penelitian Metalurgi dan Material LIPI hadir untuk mewujudkan kemandirian industri melalui penelitian berbasis sumber daya mineral lokal. Komitmen tersebut tidak pernah berubah sejak berdiri pada tahun 1965 yang disertai berbagai perubahan nama dan struktur organisasi hingga saat ini. Pusat Penelitian Metalurgi dan Material LIPI memiliki 4 kelompok penelitian yang berfokus pada pengembangan baja unggul nasional berbasis biji laterit. Penelitian ini bertujuan menopang kemandirian industri baja nasional sehingga mampu berkompetisi di pasar baja unggul global. Pengembangan produksi baja unggul ini memanfaatkan mineral laterit yang banyak terkandung di Indonesia. Pengembangan material untuk implan medis dan alat medis. Penelitian ini berlandaskan atas kebutuhan akan material implan yang sangat besar di Indonesia. Di sisi lain, selama ini implan disuplai oleh produk luar negeri yang relatif mahal. Penelitian ini hadir untuk menjawab tantangan terhadap ketersediaan produk implan generik yang ekonomis bagi penduduk Indonesia. Pengembangan teknologi pengolahan dan peningkatan nilai tambah mineral nikel, kasiterit, dan magnesium karbonat. Salah satu penelitian dalam kelompok ini berfokus pada riset mineral dolomit yang dapat dijadikan sebagai produk magnesium karbonat untuk aplikasi pada industri farmasi dan kertas. Riset lainnya yaitu pengolahan mineral kasiterit untuk senyawa kimia timah. Pengembangan material untuk industri energi. Penelitian ini dilakukan untuk mencari material pengganti industri
buat file season 1 kedua ada lagi. Oke.
Okay. Hello, everyone. My name is Andri Hardiansyah from Research Center for Physics, Indonesia Institute of Science. For this section, I will be the moderators for this parallel session 2 in the ISMM conference, and we will have about 6 presenters. And for the first presenters, for Mr. Everjoy Moniz. Is already here, Mr. Everjoy Moniz.
Yes. Good afternoon.
Sorry, Miss Everjoy Moniz Yeah.
Yes.
Okay.
I'm
Okay.
sorry.
Yes, you can start your presentation.
My presentation is recorded already po. It's recorded already. I
Okay.
sent a recorded version. Yes.
Okay, thank you.
Okay, thank you.
Good afternoon, everyone. I am Evergy Mones, and today I will be presenting a research entitled Fabrication of Transparent Conducting Aluminum Thin Film via Anodization Etching of Thermally Evaporated Aluminum on Glass. So I'm from the Philippines. So in our country, good afternoon is equivalent to magandang hapon in Indonesian, which I believe you are aware of this. Selamat sore. So, good afternoon, everyone, again. The outline of our study, or my discussion rather, will be first. I will be introducing the main material that we use in this research, which is aluminum. Then methodology. The method that we employed in this research is thermal evaporation. Results and discussion. Then conclusion and acknowledgement. So, transparent conducting electrodes have become the key element of next generation optoelectronic devices, such as LEDs, photovoltaic cells, and LCD panels. Transparent conducting electrodes, optimizing the transparent concept and at the same time being conductive, is well utilized in different applications, which includes touch screens, flexible displays, and solar cells. So the popular, or rather common, material used in transparent conducting electrodes is indium tin oxide. So we have here in this figure an indium tin oxide coated on glass. However, indium tin oxide there is a so-called scarcity in the amount of indium tin oxide. Aside from that, it can be easily damaged because of its ceramic nature. Previous study shown that indium tin oxide also showed degradation in its conductivity when stress is applied, again, which can be attributed to its ceramic nature. And aside from that, indium tin oxide is relatively, or rather has a relatively higher cost compared to other materials. So research has been conducted, it's here. Indium tin oxide, it is conductive, it has high transparency, which is good for transparent conducting electrodes. However, there is a scarcity, and at the same time, it is expensive. So research has been conducted by researchers to find an alternative to indium tin oxide. And one of these materials is aluminum. So aluminum is known to have a low resistivity. It is less expensive, it is abundant, and however, it is opaque. So our objective is to fabricate aluminum on glass film that are both transparent and conducting, so that they can be used as a transparent conducting electrode. So for the methodology, first, we perform thermal evaporation to deposit aluminum on a 1x2 centimeter glass via thermal deposition method. Then after annealing, after the deposition of aluminum on glass, next we annealed our samples under nitrogen atmosphere for 30 minutes at 450 degrees Celsius. Next is the anodization process. in 0.3 molars oxalic acid at 30 volts. So the anodization times that was employed in this study is 10 seconds, 20 seconds, 30 seconds, 60 seconds, 90 seconds, and 120 seconds. Then the etching, after the anodization, the samples was etched to remove the oxide layer using a 6% of phosphoric acid. So to characterize our samples, we performed scanning electron microscopy or SEM, UV-Vis spectroscopy to obtain that transmittance to test its transparency, then 4-point probe measurements to determine the conductivity or resistivity of the sample. Now we move on to the results and discussion of our research. So we have here the SM images or the top view. The aluminum oxide was removed and the remaining. So we assume that there is the aluminum remained. So aluminum on glass has a mesh-like structure. So by increasing the anodization time to 20 seconds, discontinuities were introduced, thereby nano-islands were formed or island-like structure, as shown in this figure. So we have here an island-like structure. So for longer anodization time, so starting from 30 seconds to 60 seconds, there were formation of gaps between the nano-islands or the island-like structures. It has become wider, which indicated the removal of the higher amount of anodic aluminum oxide. Next is the sheet resistance of our samples. So we have here the sheet resistance of aluminum thin films for different anodization times. So as observed, the sheet resistance increase with anodization times. So in this in this part of our results, the sheet resistance of the aluminum thin film samples were obtained for anodization times 10 seconds, 20 seconds, and 30 seconds. So sheet resistance increases with increasing anodization time again. Then after 60 seconds, it is possible that the whole aluminum layer is converted to anodic aluminum oxide or AAO, since the thin films are no longer conductive, as can be shown. It has a higher, or as can be shown, so a higher anodization times leads to higher sheet resistance, so less conductivity of our samples, which is just shows that the anodization is effective. Then the samples obtained from anodization time of 10 seconds has the lowest sheet resistance, as can be shown again in our graph. Then samples with 20 seconds and 30 seconds anodization time had sheet resistance of around 37.03 and 142.85 ohms per square respectively. Next is the transmittance. We have here the graph of the optical transmittance of aluminum thin films prepared at different anodization time. So the anodization times considered are 10 seconds, 20 seconds, 30 seconds, 60 seconds, 90 seconds, and 120 seconds. So the sample with the lowest sheet resistance had the lowest optical transmittance, as shown, of around 13.2% at the wavelength of 550 nanometers. Next, the samples anodized at 60, 90, and 120 seconds reach a maximum transmittance of around 62%, which corresponds to the transmittance of anodic aluminum oxide, or AAO. So to summarize my presentation, transparent conductive thin films were successfully fabricated through anodization of thermally evaporated aluminum thin film on glass substrate. So we tested our samples, we characterized our samples via 4-point probe to obtain the sheet resistance. Next is anodization time affected and contributed to changes in sheet resistance and optical transmit. Using SEM, we were able to find that the aluminum deposited on glass had a particle-like morphology. Next, the sheet resistance of the aluminum thin film increased with increasing anodization time, which can be attributed to the reduction in the thickness of the remaining aluminum layer. Increase in the anodization time resulted in an increase in the optical transmittance as well. Lastly, as we have observed or seen in the previous slides, longer anodization times caused the complete conversion of aluminum layer to anodic aluminum oxide layer. So longer anodization times again resulted to higher sheet resistance. So I would like to acknowledge the following: the OVPAA BPHD 2014-01, the PMIL from one of the labs in University of the Philippines, Diliman, then Micro and Nano Innovations Laboratory of UP Baguio. So here are my references. So that's all. Thank you very much for listening and paying attention. So maraming salamat and terima kasih.
Okay, thank you for the nice presentation, Mr. Everjoy Moniz, about the fabrication of transparent conducting aluminum thin film via anodization, etching of thermally evaporated aluminum on glass. And here we have some question in chat. What is the purpose of anodization? Since the longer the anodization increase the resistance, so should it be avoided instead? Maybe you can answer the question.
We did anodization to determine the optimal anodization time with the matching transmittance of the sample. So what would be the optimal value of anodization time, and at the same time it has to meet the transparency, the transmittance value of our sample. So since it is a transparent conducting electrode, so ideally the sample should be transparent, and at the same time the sample should be conductive. So we did this research to determine the optimal values of a sample using aluminum.
Okay, thank you for the answer. And then maybe the second question. The second question is, how about the tightness of the film film on the glass? How about the tightness of the film on the glass?
Wait. What do you mean by the tightness of the? Okay, I get it. Unfortunately, it is not part of the scope of our research to determine how tight is the aluminum film on the glass. So I think it will be an interesting continuation of research in the future. I hope I answered the question. Sorry.
Okay. I think the time is
Good afternoon, ladies and gentlemen. Thank you for the opportunity to share some results from our work. My name is Teguh Julius Surya Panjaputra from National Nuclear Energy Agency, awarded to researchers who dedicated their hard work on the innovation and development of lithium-ion batteries, which we enjoy to use to power our daily appliances, such as smartphones, laptops, etc. And hopefully, in near future, we can enjoy electric vehicle. In early development, the lithium-ion battery designed by M. Stanley Whittingham had a titanium disulfide cathode and a lithium metal anode, as illustrated here. John Goodenough and Akira Yoshino improved on the technology by replacing the cathode and anode with lithium cobalt oxide and graphite respectively. This figure illustrates the main components of lithium-ion batteries, which comprise of cathode or positive pole, anode or negative pole, and electrolyte. This battery works based on the reversible demobilization of lithium ion from cathode to anode during the process we know as charge and discharge. There are several types and choice of lithium-ion battery that can be applied, such as lithium cobalt, lithium manganese, lithium phosphate, lithium nickel mangan cobalt or NMC, lithium nickel cobalt aluminum or NCA, and lithium titanate. All of us this type is named based on the applied electrode with their different characteristic, which includes specific energy or capacity, specific power, safety, performance, lifespan, and cost. Related to the shape, there are several common types of lithium-ion battery, such as cylindrical, prismatic, and coin. With all of these options, lithium-ion battery is widely used as energy storage for many applications, from consumer appliances to industry and transportation. Recently, electric vehicles become more viable as alternative to sport transportation and personal mobility, will of course use lithium-ion battery module as energy storage to power the vehicle. For example, which applied on Nissan car and available for Indonesian market. Indonesian government in recent years show interest and initiate a national program in the development and manufacturing of lithium-ion battery, which include the exploration of basic materials such as rare earth metals and development of EV, which will use Indonesian lithium-ion batteries. Regarding the development of lithium-ion batteries, the studies and characterizations usually involve the aspect of synthesis, composition, and cathodic properties. One method that basically used to study lithium-ion battery is neutron scattering technology, particularly neutron powder diffraction. Neutrons interact with matter in different ways compared, for example, to X-ray diffraction. Several properties and capabilities of neutron are: neutron interact with nuclear through nuclear force, or we know as lattice vibration. Neutron penetrate sample containment deep into the matter. Neutron see light atom next to heavy atoms. Neutron probe the entire sample, even inside complex sample environments. Therefore, the development of materials for lithium-ion battery use neutron technology as a backbone to study, modify, improve, and create better materials. Neutron can be produced from several sources. Neutron diffraction is the determination of low temperature structure of LMO as cathode materials. The study showed that LMO with oxygen deficiency have a tendency to show a phenomenon known as Jahn-Teller distortion in manganese O6 octahedron, which will affect the structure of LMO and practical use of LMO batteries. Been used to study the possibility of doping elements in order to improve the stability of structure and physical properties of the material, for example, doping of tin in lithium titanate. Neutron can also be utilized to study lithium-ion battery cell during charge and discharge process known as in situ method. The structure, phase transition, and chemical reaction of the component in the battery in relation to the battery performance can be investigated while the battery is in use. Ladies and gentlemen, in order to support the government program to develop and utilize domestically manufactured lithium-ion battery, we have been and continue to develop and study our laboratory-made lithium-ion batteries from raw materials, components, system, and practical lithium-ion batteries. Based to our knowledge, this is the first time for a study of domestic laboratory-made lithium-ion battery cell using domestic neutron diffraction instrument. One of our study is involving the utilization of neutron diffraction method. We use our laboratory-made cylindrical 18650 type lithium-ion batteries with practical capacity of 1200 mAh and under various state of charge of 0%, 25%, 50%, 75%, and 100%. We utilize neutron high resolution powder diffractometer or HRBD-DN3 at Neutron Scattering Laboratory of NSL of Center for Science and Technology of Advanced Material Batan in Puspiptek, Serpong. The neutron beam source is multi-purpose reactor GA-Siwabesi. The HRBD consists of monochromator, collimator, slit, 22 detectors, and sample holder. Battery will place and position in line with neutron beam for maximum neutron flux. Ex-situ experiment was conducted at room temperature with 2 theta range from 2.51 degrees. The pattern and the peaks evolve with different state of charge, and it is related to the transformation of graphite into lithium graphite. It is also related to the lithium iron phosphate to iron phosphate reversible transformation. Phase and structure analysis have been done by considering 7 phases with their respective phase group of lithium iron phosphate and iron phosphate, both related to cathode materials, carbon and lithium carbon, both related to anode materials, aluminum and copper as materials for current collector, and iron coming from stainless steel casing material. This is the result of phase and structural analysis based on Rietveld refinement method for batteries with different state of charge from 0 to 100%, and the fitting result is fairly well. The enlarged Rietveld refinement pattern as shown here cover the anode window and show the evolution of graphite anode from carbon to lithium C12 to lithium C6. When the battery was fully discharged, the anode is completely in the form of C. The highest state of charge is related to the transformation to lithium carbon 12 shown by these prominent peaks and to lithium carbon 6 when the battery is fully charged. This figure on the right is an enlarged Rietveld refinement pattern covered the cathode window. The composition of LFP and FP is also evolved, depend on state of charge of the battery. This the 3-dimension refined structure of lithium iron phosphate showing the atom's arrangement NMA and a pathway of lithium ions. And this figure in the middle is the refined structure of C, showing the distance D between graphite layers as host for lithium ion. And this figure shows the composition or relative percentage of graphite lithium CN in anode and FP in cathode as a function of state of charge. And these are some conclusions from our work. The most important thing, perhaps, to be concluded here is that we are successfully produced functional lithium-ion battery in our laboratory from raw materials, and we use it in our facility to study the relationship of phase, structure, and physical properties of our battery. This work is important in order to support national program in research and development of lithium-ion battery. Thank you for your attention.
Okay, thank you for Mr. Teguh for the nice presentation. Is there any question? The presentation is about the evaluation of LFP battery performance performed by high-resolution neutron diffraction techniques. So maybe my question is there any challenge in order to evaluate the LFP by using this kind of techniques?
Yes.
What is the challenge?
So basically what I want to present here is that the relationship between the lithium-ion battery and neutron, because we understand that maybe neutron technology is not so familiar in Indonesia.
Yes.
In fact, we have a nuclear reactor. All the research and development in lithium-ion battery around the world is based or usually basically involve the neutron technique. This is very important. Why? Because it's back to the nature of the lithium-ion battery, which consists lithium, which is a light atom, and it's among heavier atom. So you know that the lithium-ion battery our appliances is based on the mobility of lithium. So it is very important to understand the mobility of lithium and of course the structure. So in this case, perhaps one challenge is that for if we want to study the battery as a system, it have a multi-phases here. As I show here that there are at least 7 phases here. And it's not easy, I think, if we use only XRD. Because XRD, for example, I mean X-ray diffractometer, and neutron have a different way to see matter. Maybe that's my answer.
Okay. Thank you for the nice explanation for us, at least for me, to know a little bit about the high resolution.
Indonesia. I would like to thanks to ISMM 2020 organizer for giving me time to present my work and evaluation study of size and aggregation effect on colorimetric spherical gold nanoparticles. This is my presentation outline from introduction until summary. Let me start by saying that gold nanoparticles are very applicable due to plasmon effect. The appearance color of colloidal gold nanoparticles depends on size and aggregation. We know that the top-down and bottom-up procedures can be used to synthesize gold nanoparticles. These procedures create not only monodispersed gold nanoparticle, which is good for most applications, but also aggregated gold nanoparticle, which is also useful for some specific application. Usually, we utilize transmission electron microscope (TEM) to check size, monodispersion, and aggregation of synthesized gold nanoparticles. However, TEM is expensive and time-consuming. The challenge is to create simple technique to monitor synthesized gold nanoparticles. Colorimetric could be the answer, since color of colloidal gold nanoparticles describe their size and aggregation. Until now, there is no standard procedure to do this colorimetric technique. Therefore, in this study, we computationally studied the colorimetric of gold nanoparticles due to size and aggregation. To display the true colorimetric results, we use color diagram CIE 1931. We assume that this work can produce simple colorimetric technique to observe colloidal gold nanoparticle. In order to simulate colloidal gold nanoparticles, I use MNPBEM toolbox from Hohenester from University of Graz, Germany. This free toolbox utilizes boundary element methods to simulate extinction cross-section curve of any given size, shape, and configuration of gold nano curve. In practice, this reflection and transmission are what we can see by our eyes. This curve was then used to calculate color coordinates using color matching function of CIE 1931. This is a common procedural technique for displaying color using CIE 1931 color diagram. Thus, we can plot the color coordinates in the color diagram. Every color coordinates X, Y describes specific color. This is a simple colorimetric standard. First, I will show you the result of spherical single gold nanoparticle simulation from 5 nanometer until 200 nanometer. The extinction curve consists of absorbance and scattering peaks for larger size of gold. The calculated color coordinates are plotted in the color diagram. We can see that color of monodispersed gold nanoparticle changes from red to purple to blue when the size of gold changes from small to medium to big. The middle photo is real appearance of 30 nanometer gold nanoparticle that we synthesize using laser ablation technique. This color change agrees with some experimental results. The extinction curve changes when we use aggregation configuration. This is example of 30 nanometer gold nanoparticle with 3 different configurations. Monodispersed gold nanoparticles, the black extinction curve, give red color appearance, dot 1P on the left figure. Triangle and line aggregation produce different extinction curves, the red and blue curve respectively, of gold become purple, denoted by point 3 PT and 3 PL. This is the overall simulation prediction of monodisperse, triangle aggregation, and line aggregation of gold nanoparticles from 5 nanometer until 200 nanometers. This is a little bit complicated, so I will describe it in detail. I will discuss small particle, 10 nanometer gold, medium particles, 80 and 130 gold nanoparticle, and large particle, 200 nanometer gold. On the left figure, we can see that the small 10 nanometer gold nanoparticle produce red color and the color changes into purple when the particles are aggregated. The medium size of gold, 80 nanometers on the right figure, the color change from reddish purple for monodispersed gold nanoparticle to bluish color when the particles are aggregated. This color change is mostly due to change and additional scattering peak on extinction curves. Mostly, the scattering is in longer wavelength or red color. Thus, the appearance color that we can see by our eyes is blue. A little large size 130 nanometer gold nanoparticle, left figure, shows the color change from purple for monodispersed gold to bluish color for aggregated gold. However, the large size of gold, 200 nanometer, in the right figure describes opposite trend. The color of monodispersed gold, blue color, changes to purple when the particles are aggregated, denoted by 0.3 pt and 3 pl. In summary, the simulation of monodispersed and aggregation of gold nanoparticle from 5 until 200 nanometer can be simulated and further calculated and displayed in color diagram CIE 1931 to observe color change due to size, monodispersion, and aggregation configurations. Due to aggregation, the color of small gold nanoparticle become purple. The color of medium-sized gold nanoparticle become blue, but the color of large gold nanoparticle become purple. This result can be a new and simple colorimetric procedure to monitor synthesized gold nanoparticle. I welcome for any feedback and comment. Thank you very much for your attention.
Okay, thank you, Dr. Isnaini, for the nice explanation about simulation study of size and aggregation effect on colorimetric spherical gold nanoparticles. And there is some question in chattings. Is there any opportunity for research collaboration to investigate the gold nanofluids for us to be used in heat pipes application? The question from Dr. Anggito.
Okay, thank you very much for the question, Dr. Anggito. So yeah, sure, it will be very lovely to collaborate with your team using gold nanoparticles. So we can provide gold nanoparticles in different size and aggregation if you like to. We can also produce a large quantity of gold nanoparticles that can be applied in a long pipe or something like that. So it's very welcome. We also, it's also possible to try to functionalize a gold nanoparticle if you need a functionalized group on the surface. That's a good thing. Thank you.
Okay, thank you. And has it been confirmed by experiment, Dr. Isnaini?
Okay, thank you. Thank you for the question. Yes, from the references literature study, so we have confirmed that some big gold nanoparticle is really blue. In our lab, we also try to make a aggregated and a big size, and also getting blue color instead of red purple color. So experimentally, it's already proven that they of course use a TEM technique to prove the size of the nanobulb. Thank you.
Okay, probably the last question is any effect of the medium of the colloids?
Oh yeah, thank you very much for the question. Yeah, of course, the medium of the color also affect the appearance a little bit. For example, if you use the water and also another liquid, probably the organic solvent, also make a little shifting of the appearance color. If you use the organic solvent in the synthesis process, the result could be different. But if you transfer from, for example, transfer the gold from water into organic solvent, so the appearance could be changed a little bit only. Thank you.
Okay. Thank you for the explanation of the answering the question, and thank you for the presentation, Dr. Isnaidi. And we will move to another presenter. The next presenter will be Professor Perdamaian Sebayang.
Hi, Pak Andri. Can you hear my voice?
Yes.
Yes. I'm sorry, Pak Perdamaian cannot attend the Zoom presentation. Therefore, on behalf of him, I will present the research. Previously, I already sent the video, so I will use the video as the presentation. Thank you.
Okay, thank you. Okay.
Okay, thank you for coming to this online presentations. Today, I would like to present preliminary investigations of nanofluids of water magnetites for PEM fuel cell cooling applications. My name is Anggi Tertuko from Research Center for Physics LIPI. I would like to begin with an introductions. What is a nanofluid? Nanofluid is a fluid or base fluid where particles of materials is dispersed in the fluids. The purpose is to improve or increase the properties such as the physical and the thermal properties of the fluids. So we can see in these images presented in figure 1, we can see that on the left hand side is a very poor nanofluid where the particles is sedimented as a result of agglomerations between particles. On the other hand, on the right hand side is a very good and stable nanofluids. We can see that the particles stables and disperse in the water fluid. This occur as a result of the surface modifications of the particles, such as by using the polyethylene glycol and also by adjusting the pH level. We are planning to use the magnetite nanofluids to be used as a cooling system in fuel cells. So for those of you who are not familiar with fuel cell is an electrochemical device that can convert hydrogen and oxygens into electricity, heat, and water vapors. In order to maintain the optimum working temperatures, particularly for PEM fuel cells within the range of 60 to 80 degrees Celsius, the heat that is not needed in the system have to be removed from the fuel cells. Based on the literature review, we can see that several researchers have used several cooling system types, such as the air cooling, the liquid cooling, the pyrolytic graphic sheets, and also heat pipes. This is an image of a cooling plate that is inserted in the fuel cell stacks. So we can see that in the cooling plates there's channels where the liquid or the nanofluid will flow to absorb the heat from the fuel cells to remove the heat and to maintain its optimum working temperature. So in this research, we're going to do two types of investigations. First is the experimental investigations by synthesizing the water magnetite nanofluids, and the second one is the models or the analytical models to calculate several parameters that is needed for designing the PEM fuel cells cooling system using nanofluids. So in the synthesis of the water magnetite nanofluid, we use polyethylene glycol or PEG to use to modify the surface of the particles into hydrophilic surface. Therefore, the particles first in the water as the so it as a layer to reduce the agglomerations between the magnetite parts. The sonification method going to calculate the thermal conductivity of the nanofluids affected by the and also the volume fractions of the nanofluids. The coefficient convections and also the outside. Later on, we're also going to where the nanofluid will flows inside the channels and will absorb the heat and remove the heat from the fuel cell stack. This is the characterization from the TEM. This is a TEM image of the magnetic particles. We can see that the average particle size of the magnetite particles is 130 nanometer. We also measure the stability of the nanofluids, where the magnetite particles is dispersed in the water as the base fluid. We can see that the nanofluid is stable at the zeta potential value of 32.1 millivolt. We also measure the thermal conductivity value of the magnetite nanofluids, which is a very important properties that affects the overall heat transfer inside the cooling channel of the PEM fuel cells. Based on the analytical model, we can vary the thermal conductivity as a function of the particle diameter. We can see that in figure 8, the increase of the particle diameter will reduce the thermal conductivity of the nanofluid. On the other hand, if we increase the volume fractions, which is the ratio of the particles that have been dispersed in the nanofluids with its base fluids, the increase of the volume fractions will enhance the thermal conductivity, where this thermal conductivity will affect the overall heat transfers. Therefore, when we synthesize the magnetite particles to be used in the nanofluids, we also have to consider these parameters as one of the factors that affect the overall value. Based on the analytical model as well, we can calculate the output voltage, which is one of the parameters to calculate the amount of heat that needs to be removed from the system. Based on the analytical model as well, we can calculate the output powers that is also needed for calculating the amount of heat that need to be removed from the system. Okay, after we obtain the output voltage and also output power from the fuel cells that also have been validated using our previous experimental investigations, we can calculate the amount of the cooling load, which is the amount of heat that is not needed in the systems and need to be removed from the fuel cell stack. Based on the informations of the cooling load from the PEM fuel cells, we can vary its values and we can plot the mass flow rate of the water magnetic nanofluids that will be flown inside the cooling channel of the PEM fuel cell. Therefore, we can predict the optimum mass flow rates to remove the heat from the fuel cell stack. Okay, this is another parameter, which is the Nusselt and Reynolds numbers that can be calculated from the models. Those values are very important in order to analyze the heat transfer and fluid dynamic properties. Okay, based on the Reynolds numbers and also the Nusselt number, we can calculate the coefficient convections, which is the another important parameters in order to analyze the heat transfer inside the cooling channel. Also, based on the models, we can also calculate the effects of the thermal conductivity to the overall coefficient of convection inside the cooling channel of the fuel cells. We can see that the increase of the thermal conductivity will also increase the coefficient of convections. As I mentioned previously, that this thermal conductivity of the nanofluids is also affected by the particle diameters and also the volume fractions of the nanofluid. Okay, as conclusions, the nanofluids of water magnetites has been synthesized using polyethylene glycol as a layer to reduce the agglomerations and also to modify the surface of the magnetite particles into the hydrophobic surface. Therefore, it can be easily dispersed in the water. The zeta potential measurement suggested that the nanofluid is stable. The additions of the magnetite particles could improve the thermal conductivity of the nanofluids, where those value of thermal conductivity was affected by the particle size and also volume fractions. And heat transfer model confirmed that the thermal conductivity of the water magnetite nanofluids can be used as a coolants that influence the heat transfer, particularly the coefficient convections inside the PEM fuel cells. Therefore, this type of nanofluids is suitable to be used as a coolant in the PEM fuel cell cooling system.
Okay, thank you for the presentation, Mr. Anggit. And then there is some question related to the presentation. Why the pH is basic, but the zeta
Okay, thank you
potential
for
is
coming
positive?
to this
What
online
is the effect
presentations. Today I would
of
like
the
to
pH
present
on
preliminary investigation.
Nanofluids. For the other one, for the zeta potential, because it's we have some people that involved in this research. So maybe I will pass these questions to my colleague because I'm not the one who are working with the zeta potentials. But for the collaboration, I think it's an honor for us. Pak Dani is expert in nanofluids, so it will be an honor for us to collaborate. So maybe I will ask the committee of this conference to ask the Pak Dani email, and also we can continue this research for collaboration. Thank you, Pak Dani, for the questions. Yeah.
Okay, thank you, Dr. Anggito, for the question, for the answer of the Prof. Dani questions. And have you measured the diameters of the PEG magnetic nanoparticles by using maybe
Yeah, I think we have the data, but I'm not included in these presentations. But I will double check for the size of the magnet. Okay. Yeah, for the PEG particles. So thank you for your question.
Yes. Okay. Thank you for the presentation, Mr. Anggito. And then we will move to the next presenters. The presenter will be given by Miss Amanda Atanasia Septevani for present the research.
Yes, I am. Can you hear my voice?
Yes.
My apologize because I haven't prepared the video yet, so I will give live presentation. Is that okay?
Yes, please go ahead.
Okay. Can you see the slide?
Yes.
Okay. Okay, thank you, the committee, and also Mr. Moderator, Bapak Andri, for the times. In this opportunity, I would like to share one of our projects in collaboration with the Center for Physics, entitled of Facile and Low-Cost Reduction of Titanium Dioxide Nanoparticles using High-Energy Milling for Dye Degradation. My name is Amanda. I'm from Research Center for Chemistry, Indonesian Institute of Sciences. So yeah, the massive industrial activities, as well as the mine and also the fast growth urbanization through the transportation, residential and agricultural activity are responsible to the deterioration of our environments. In fact, it is reported that in West Java, for example, that the the Citarum River is polluted by the dye degradation because over 1,000 textile factory was out every 2 hours, causing the dangers of our ecosystem in the water as well as also for human life. So there are technology called as photocatalytic degradations. Basically, the principle of the photocatalytic degradation is when dye can be decomposed into the stable products in the presence of first appropriate wavelength, for example, usually UV light, and the second one is semiconductor. Usually we use the oxide. So when semiconductor can absorb the appropriate wavelength, at a certain degree, it can generate it and transform from the valence gap into the conduction gap, and then it will create some excitation that reacting with oxygens as well as the waters to create some radicals. So these radicals is actually responsible to attack the short toxic dye, which is a complex structure, into the harmless or the good molecules that is not dangerous for our environment, such as carbon dioxide and also water. So one of the particular example of the promising semiconductor is titania, also titanium dioxide, is one of the promising semiconductor because this is abundantly available as well as this is non-toxic. So basically, titania can be used for various applications. So there are 3 types of phase that are well known with regards to the titanium dioxide. First is brucite, and then anatized, and then rutiles. So from these 3, mostly researchers are focusing on anatized because it is reported to give a more effective in dye degradation in particular. So when we can transform the micros titanium dioxide into the nanosite, of course, as we know, in the nanosized particle, it will create some unique properties. In particular, it will give some higher surface modification that can help in the dye degradation. So there are types of the approaches that we can use to produce. There are 3 steps of the methodology in this project. First is the preparation of titanium dioxide using a ferrite melt speed at 300, 400, and 500 RPM, and then followed by the characterization of the melt titanium dioxide, and then we compare to the titanium dioxide that is produced from the commercially available, which is in this case is sigma Aldrich, and we do characterize the particle size analyzer, scanning electroscanning, and then X-ray diffraction. After that, we also do the photocatalytic degradation of dye in order to understand whether our approaches is suitable for the dye degradation in order to solve the environmental problems. So yeah, this is the result. In terms of the dimension, we do the particle size analyzing. We can see in this graph that the increasing milling speed, it can gradually reduce the size of the titanium dioxide optimum at 400 at about 300 nanometer, which was, you can see in here that comparing to the commercial nano titanium dioxide, that the size is pretty similar, showing that these approaches, it can produce the similar size in comparison to commercially available nano powder. And from the morphology study, you can see here that the A is the technical grade of micro powder titania. Oh yeah, I forgot to mention that the source of the titania, technical grade titania, is just from Bratacam. We can easily buy at a very cheap, at about 80,000, I think, rupiah. And then after the milling, you can see here that we can produce the well integrated of the sphere particles that is actually also comparable with the commercial nanopowder titanium dioxide. Okay, next. is the crystallography analysis. You can see here that the top graph of XRD, this is the raw, the technical grade before the treatment, that it consists basically both the rutile plane at 110 is about 11.7% mixed with the dominantly anatase at about 101 planes. And when we do the milling, there was a disappearing of the rutile plane into the pure anatase, indicating that this process can help us to achieve what we want, which is the anatase changing in crystal phase. Okay, now this is the dye degradation activities. You can see in here that the top two colors, blue and orange, is the activities of the titanium dioxide between the nano and also the milling materials. You can see that these two types of the materials can provide the similar results that can achieve up to 100% dye degradation in the presence of the rhodamine B dyes. While for the methylene orange, it is a little bit lower than the rhodamine B, but basically I can see here that both titanium dioxide that we use in this work was also comparable to the nanotitania dioxide. So the color change, you can see in here that the photo of the process before and after the process of the photocatalytic process, you can see here that from the color change, for the color change into the transparent color, meaning that this photocatalytic reaction is successfully conducted. So to conclude that the low-cost and commercially available technical-grade titanium dioxide was successfully produced by using high-energy milling to obtain the nano-sized titanium dioxide, which was comparable to the commercial nanotitania, that is in terms of the particle size, and then we also can produce well-defined nanostructure, as well as this disappearing of the rutile plane into the anatase planes, which is, this is the one that we want to produce the purely anatase phase that can give a high removal dye degradation up to 90% removal, both for the rhodamine B and also the methylene orange. So to end this presentation, I would like to thank the financial assistance from International Environment Research Institute South Korea for giving the financials for our project, as well as to all of the researchers and members to help this project is accomplished successfully. Thank you for your kind attention.
Okay, thank you, Dr. Amanda, for the nice presentation about vessels and low-cost production of titanium dioxide nanoparticle using high-energy milling for dye degradations. And there's some question, in large-scale application, how to separate the photocatalyst after usage, and then what is the degradation capacity of the photocatalyst?
Degradation, the large-scale application. So if we want to use this type of only titanium dioxide, it is still quite challenging because titanium dioxide is basically agglomerated easily and it's difficult to separate with the, for example, the treated water. So actually this part of project is part of the biggest project that we will use not only titanium dioxide, so we will do some modification to include titanium dioxide, which is good in photocatalytic, and also the other is nanocellulose, because it can help with regard to the problem of agglomeration, as well as also to conclude the magnetic for easy post-separation in the case if you want to use in a large-scale application. So I should say that this is still a long way to go. So in particular of this, only titanium dioxide is quite challenging for the large-scale application because in the lab scale, for example, we need to do the centrifuge in order to separate between the photocatalysis with the treated water. So the second question is, what is the degradation capacity? I can say this is we only do degradation efficiency. That is, if you can see in our previous slide, that it can be successfully remove the dye up to 90% in the case of rhodamine B especially.
Okay, thank you for the answer for the Dr. Dani Gustaman questions. And then we will move to the next presenters. Thank you, Dr. Amanda, for the nice presentation. The next presentation will be given by Dr. Dani Gustaman Sharif about synthesis of alumina silver nanocomposite for nanofluids.
Assalamualaikum warahmatullahi wabarakatuh. First of all, I want to thank the moderator of this session for giving me time to deliver our presentation about synthesis of alumina silver nanocomposite for nanofluids. We are from PSTMT Batan, Bandung. I will explain about the background of our research. There are many systems such as nuclear reactor, automotive, machining, and other systems utilize heat transfer cooling fluid that is known as the conventional cooling fluids, such as water, glycol, oil, and etc. Now there is a need to increase the economic and safety of the systems, but it is conventional methods such as extending surfaces, microchannels, or flows are not economical anymore. Here we need new fluid. Because why? Because the conventional cooling fluid has limited capability in heat transfer. There is a candidate of the new fluid named by nanofluid that is a product of nanotechnology. Nanofluid is a fluid containing nanoparticle with size of 1 to 100 nanometer forming stable suspension. Recently, the nanofluids are widely studied in the world due to high potential economy. But the big problem of the nanofluid now is the stability. Theoretically, the stability can be improved using many methods, such as adding dispersion, for example. But now here, we use silver to improve the stability of the nanofluid. So why we did synthesis alumina silver nanocomposite for nanofluids. For the synthesis of nanoparticles and nanocomposite, here we mix aluminum chloride with urea, water, and silver nitrate, and then the mixture was heated as of the nanoparticle or nanocomposites, and using DET to know the specific surface area of the nanocomposites, and using TEM for particle size measurement. For the preparation of nanofluid, actually we can use two methods, namely single step method and two-step method. But here we use two-step method for the preparation of nanofluid. Here alumina silver nanocomposite was dispersed into the water, and the dispersion then ultrasonicated for about 1 hour using a UV bath. Then the product named nanofluid then characterized by pH measurement, visual examination, and zeta potential measurement using a zeta sizer. Now I want to explain about the XRD analysis result. If you look at the picture, you can find that the Composite crystallizes in gamma alumina with broad peak. That means that the particle size of the nanocomposite is very small indeed. If we move to the crystallized size data, we can identify that the crystallized size is around 7 nanometer, and it tends to increase with the increase of silver concentration. However, the lattice constant of the nanocomposite remains constant with the increase of the silver concentration. Now I want to explain about the surface area and FPIR data. If we look at the table, we can see that the surface area of the samples is very large enough, and the surface area tends to decrease a little bit with the increase of silver concentration. If we look at the right side figure, we can identify that the silver tends to change the characteristic of the nanocomposite. Here we can see that the OHP decreases with the increase of silver concentration, but there is an optimal value of the concentration that is at 0.5% silver. Please let me now explain about that, about 10 images of our nanocomposites. As we can see from the figure, that the nanocomposites consists of two kinds of particles. First is elongated or rod-shaped particle, and another is spherical one. And it's very difficult to differentiate between particles. This is due to the low calcination temperature. But typical nanocomposite size is 25 nanometer in diameter and 1.33 micron in length. Now I will explain about characteristics of nanofluids. Is functioning, quenching, and ECCS, emergency cooling system, and RPCS, reactor cooling system of the nuclear reactor, except primary cooling system due to very tight requirement of the system. Finally, I conclude that number 1, alumina silver nanocomposite with gamma crystal structure was successfully synthesized using the hydrothermal method with urea as a trapping agent. Number 2, the synthesized nanocomposite form a cluster of rod-shaped particles with typical 25 nanometer in diameter and 1.33 microns in length. Number 3, the addition of silver increases crystallite size and particle size and decreases the specific surface area. Number 4, the alumina silver nanocomposites can be made to produce highly stable nanofluids with an average zeta potential of 41 millivolts. Number 5, this nanofluid has the potential to be used as a cooling fluid for ECCS, RPCS, computer, refrigeration, and metal machining process. Thank you for your attention. Assalamualaikum warahmatullahi wabarakatuh.
Okay, thank you for the nice presentation, Dr. Dhani Gustaman Sharif, about the synthesis of alumina silver nanocomposite for nanofluid application. And maybe this is the question from me. Actually, how's the alumina and silver interact each other? Because you said that you use urea as the capping agents, and then how it's the mechanism of is it the silver attached to the alumina or?
Okay, thank you. Can you hear my voice?
Yes, yes.
Okay.
Yes, please, Dr. Denny.
Okay, yes. Actually, urea is used for challenging agent as we done in the previous work, and it was very good to make the stable nanofluid. And then now we want to increase the stability by adding silver, and silver here with alumina form a composite. The silver exists in the surface of the nanoparticle, and then change the surface characteristic. As we can see from the FTIR data, the silver changed the peak of the band. So, for nanofluid, the surface characteristic is very important. So, but here we cannot judgment if the nanofluid good for heat transfer or not, because we not yet measure the thermal characteristics such as thermal conductivity and heat transfer coefficient. But from the data and zeta potential, our nanofluid now is very stable. So, because here we didn't use any dispersant or surfactant. So this is very good indeed, because the nanofluid at least until 10 days is very stable. Okay.
Okay, thank you for the answer for my question actually, and it's very interesting research related to the alumina and then the silver nanocomposite for nanofluid application. Okay, I think that's all for the presentation today. Thank you for Dr. Dhani Gustamansyari for the last presenter for today's sections. And also I would like to thank for all of presenters for the parallel session 2 for this conference. Okay, so
picture.
Yes, so probably we will have a photo section. So please turn on the camera video. The committee is okay.
Please go ahead. Ya, berarti tanya lagi nih.
Okay, the photo session is completed. So I would like to thanks for all for coming for the parallel session 2, and then thank you for all of the presenters that present the research today. Thank you. Good afternoon. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam warahmatullahi wabarakatuh.
Okay.